itinerary, bingo and gambling and our gift shop, the most expensive handbag. In your pocket.
It's ours
All
now.
it was spending. That was. So with the Pixum, how does do you turn them on?
They're on right now. Cause I'm just gonna. It's coming. I see it on those ones, but you want the camera to like track up. Cool.
I got on 4, but you want me to do 3?
If you'd like.
Three is the
Someone.
one in your left hand, I think.
Yeah.
I'll never forget the time I was headed.
Yeah.
I was down to Campinas. I forgot to my last trip. And my visa had expired to get into Brazil, so I needed to send it off to Brazil, but I also had to. As I went to send it off, the passport agency told me the embassy in Chicago had the database and they couldn't really process visas. So I only way to get the visa, drop it off in person in New York City. So I hopped on an airplane, I flew to New York City. Way to get to New York City, discover like the next day's a bank holiday. I spent an extra night and then I picked it up as soon as it was done. So rushed it through. As soon as it was done, put on an overnight interview and arrived just in time for me to leave the next day to go to Europe. And I'm like, every delay is going to yeah. And then I also
Yes, the last time we did it, line number. Line number. So, what are the chances? Oh. Like you know, previously it was just one time, right? So to give this file. Your slides are already up, so now we need to be. Previous life was like if it was not the same order, slot. So we can like the same line, like counters, let's take out. It's not high sensitive. What else? I did something like
It's not my fault.
I felt better when I saw you again. I feel like if you got it every time, it feels like it's starting. For the thing now, this big side project that's not very true. Yeah, but you're right. Saying you're a little.
Yeah, and that's what I heard. It takes like upwards.
¿Cómo se llama, Matthew? ¿Todo bien, Bob? ¿Está bien? So are we. I was gonna say, yeah. Surprise, surprise. Historically, the area where. Oh, yeah? Cool. So it's basically at the binary level, we get I agree. I was just talking to this straight up yesterday about like, we had customers was like, oh, I want to do 10,000 probes. Yeah. Hey, how are you doing? How are you? Good. I can say that we can do it. I would write it. It's not a problem. Yeah. It's still very well. But 10,000? This customer was like, I don't want to rebuild my application. Okay. They're like, but I need 10,000 instruments in probe points. They're like, okay. 10,000? Yes. Easily 10,000? We're talking an overhead per probe of around 30. So what's the under the hood? What's the fundamental for the injection? So for the injection of the probe, typically during patching of head of instruction, then calling on border to organize the program, and then touching the body of the instruction. And then releasing the heads by doing the final for merging three instructions involved into a single trampoline. The trampoline simply lowers the breaker and called the handler. Including exit and state. And then it's called get the structures. All of this is and one you can modify the registers. So are you dynamic and rewriting? Yeah, but we're not rewriting. It's like yeah. It's like that, but guidance technique. Yeah. Right. Yeah. Why? Memory usage is very high on this because yeah, it's actually we have a Dynamics backend for.
Good morning, everyone. Welcome to the second day of BPF track at Linux Plumbers Conference. And we are starting with the BPF time presentation.
Okay, thank you. Good morning, everyone. Thank you for joining me today. I'm excited to talk about our latest project, BPF Time, our user space eBPF runtime. My name is Yushen. I'm currently working on some open source projects related to eBPF. This is the first time I've spoken at Linux Plumbers. I'm very excited to be here. This is the topic we are going to decide about today. I will start with a brief introduction to why we need a new user space eBPF runtime. There may be kernel UProp performance issues, kernel eBPF security concerns, and limited configurable. And other user space eBPF runtime limitations. And after that, I will start to introduce to our BPF time and talk about how it works and some examples and benchmarks and our roadmap. Let's start is why we felt the need to create a user-based eBPF runtime. uProbe is short for user-based dynamic tracing. However, the kernel eBPF uProbe has some performance issues. It's attached to the uProbe is attached to a user-based function and run eBPF program, which when a function is executed, is widely used in production, like tracing the SSL, TLS, HTTP2 protocols and monitor the memory allocation or tracing bash scripts and like Python scripts yesterday. We've seen performance issues with kernel uProbe, and the current implementation requires two kernel context switches, lead to a significant overhead. The uProbe is like 10-fold overhead than a kernel uProbe, than a kernel kprobe. Also, the kernel trace points will hook all syscalls and require filters for specific process, which is not very flexible. And also, there might be some security concerns or configuration. Running eBPF in kernel requires root access, and this will introduce a more larger attack surface. This chart shows a lot of CVEs from recent years. This is because the verifier, which is supposed to be the gatekeeper ensuring only safe eBPF program running, is actually where the most CVE were found. And we also talk about the configuration. This is the verifier restricts eBPF operations quite a bit. If we want to make more complex logical in the eBPF code, like make it Turing complete or extend some helper mode or new features, we need to recompile the kernel and redeploy it. There are some current user-based eBPF runtime, like the eBPF, RBPF, and also some, but they can't quite keep up with all the workloads we want to do. Like maybe we can have some user-based observability, like the uProbe I just mentioned, and some user-based network, user-based configuration plugins and filters. This typically we may use like a WebAssembly. However, despite the uProbe has something like Git helpers and simple hash maps and like ELF parsing, they still need a complex integration and usage. They cannot use kernel eBPF loaders and tool chains like libBPF and clan. There's no attached support. They cannot dynamically attach to any running process. They cannot attach to syscalls and user-based functions. And there's no inter-process maps or kernel map support. They cannot access like maps in kernel. So that is limited functional in use space. There are also some existing no kernel eBPF use cases like the QMU and eBPF, like we can combine user-based eBPF with DPKK and use for smart contracts, and eBPF is also for eBPF for Windows. They can bring eBPF tool chains and runtime to Windows kernel. There are also some papers related to user-based eBPF. For example, the RAPI patch, which is about quick fix or for firmware in real-time systems, and some thermal containers, which are about making tiny, efficient visual space for IoT device. So putting all together, we can go some use cases like networks, plugins, and like edge computing or smart contracts. They can also be used in other systems. So here comes let's talk about our BPF time or user-based eBPF runtime. With user-based eBPF runtime, our user-based eBPF runtime uprob can be sped up to 10 times faster than traditional kernel uprob, and not just like general uprob. You don't need to do any manual instrumentation or restart the process. They can trace the user-based function, syscalls, or modify user-based user function behavior. BPF time is also compatible with kernel eBPF toolchains and libraries, so there's no need to modify the eBPF applications. Then you can just run in use space. There are also some inter-process map supports or kernel map supports. They can we work together with kernel eBPF, so maybe we can offload the kernel eBPF to use a kernel verifier to verify it. We also bring a new LLVM JIT comparer to eBPF. This is the feature we currently support in user-based eBPF runtime or BPF time. We can support a large number of shared memory maps that are entirely in user space, and some maps we can interact with kernel. Like a perf event, we can send the events from the tracing target process to the tracer. And we can also submit the event back to the kernel, and kernel will submit them to the tracing tools like the LPC tools. We can also dynamically attach to the program types in the user space. They are mostly about the syscalls and uprob. You can also define other static trace points and program times in the user applications easily. There's like 22 helper support we can now implement in user space, and we can support using a kernel verifier or another stay-along user space verifier. There's two modes for BPF time. The first thing is we can run eBPF completely in user space. They can even run without a kernel and on some non-Linux Unix systems. However, it's not very suitable for large tracing programs because they may need a mix of kernel kprob and user-based uprob. Because the maps in shared memory can only be used by user-based eBPF programs, it cannot be used by kernel eBPF programs. So we'll introduce another approach. We may run eBPF in user space with kernel eBPF. We'll introduce a new BPF demo. It's similar to the fields. It can be compatible with kernel uprob in behavior. It can attach to a new process or running process automatically and support a mix of uprob and kprob. They don't need to modify the kernel. We use like eBPF module to monitor or change the behavior of eBPF syscalls. These are some basic examples. To use the uprob to monitor user space mlog function in libc. This example can be working in kernel and working in user space, or partially working in kernel and user space. So you can use a BPF time load to load the eBPF programs and start tracing with another running process. You can also dynamically inject or attach the eBPF program to a running process. Then you can see the output is similar to what a kernel does. And you can also start running a BPF demo, and you can just use the mlog like what's used with kernel uprob. You can just running it and load it to a kernel, and the demo will automatically load it to use. It's ready to use space, and you can trace in the target process. So let's discuss how BPF time is working, like running first mode is running eBPF in use space only. This is our original kernel eBPF design. It requires compare eBPF program from source, use skin eBPF tool trends to compare the bytecode and like using a use-based library to load into the kernel with the verifier or JIT. They can attach to events. The uprob is attached to use-based applications, use-based functions, but it will require context switches when the target process running into these functions, you will trap into a kernel, execute the eBPF programs, and return to use space. This is where the overhead often comes. This is where BPF time completely working in use space. This is similar to the original kernel eBPF. There's no change to it, but we modify the BPF syscall to a function call and use a library to interact with the syscall use-based library, execute, and then we will load the programs and maps to a shared memory. And we can verify with a use-based verifier and JIT compile the BPF program and running another process. You can use like tools to inject the run. This is a shared library. You can use some tools to inject the shared library into the target process. Then it can attach to the functions or syscalls via binary rewriting. This is how the injection works. We can support two types of injection runtimes. Runtime is a shared library for running process, so we don't need to stop or restart the process. We can just inject the library into the running process via the ptrace approach. This is similar to FlyData, and we use the tools FlyData provides, and we can also start tracing at the beginning of the new process. We can use load preload to LD preload to load the shared library when the process is running. This is our trampolines. We use the inline hook is based on FlyData gene, and the syscall hook is based on zipline or other syscall hook approaches. They can also be easily extended to new trampoline methods. The inline hook is to modify the start of a function, and when the control flow reaches the start of the target function, it can be branched to our tracing programs, and when our tracing programs finish, they will branch to the original function. The second mode is we can run in BPF use space working with kernel. We will introduce another BPF daemon to they will inject a BPF kernel code, kernel module writing eBPF. They can change the behavior of syscall via the BPF probe write user, and also monitor the BPF programs and monitor the uprob events and doing the attach process in use space. They can like unload the program to use space and running it with the target BPF time agent. Then you can use man map or ring buffer to interact with eBPF maps. There should be no syscalls in this point. If we use syscalls to interact between the kernel and use space, it will be very slow, and there's no need to change the uprob to the use space. This is the attach point overhead. We can see the kernel uprob has 10 times overhead than the use space uprob, and however, our use space syscalls in hooks introduce a slightly more overhead. And you can also define some steady trace points and embed runtime in user-space applications. You will resulted in similar overhead like the kernel syscall trace points. We also did a simple benchmark for JIT, like micro benchmark compare eBPF runtime and WebAssembly runtimes with some with some small cases. LLVM JIT can be the fastest. The lower this is for time, the lower the bar is, the performance is better. So from left to right is like uprob, uBPF, RBPF, or BPF time, and like WebAssembly and native. If LLVM JIT is heavy to deploy, we are also developing a half-time comparer for LLVM JIT. We also evaluate our eBPF time on some existing eBPF use cases. They can be run directly without any modification or with some minor fix. We have tested with some BCC tools like BPF trace and eBPF exporters. They can trace use-based functions or like syscalls, and we can also evaluate with difflow more complete application used for observability. This is a BPF trace. This is a BC tools. With our BPF time, we are able to run the tools from the syscall interface applications, libraries, and runtimes. We have put some tools related to it. It's from the top half of a picture and can be entirely run in use space. We have also put and test some like BPF trace and Prometheus exporters for they can run as expected, or the BPF requires some minor fix. We also test about the performance of SSLS Sniff. It's a BCP tool to capture the SSL data, unencrypted data in use space. It's widely used in production for observability. Compared to no SSL interception, the kernel will reduce the request second by like nearly 60%, and our use space is SSL Sniff only reduce like 12%. We tested with Nginx and WAC. The higher is better. Yeah. The blue is the original. Orange one is the kernel, and the green one is the use space. We also test with complete observability workload, like the difflow agent is deployed in production and like publish like a paper. And the uprob in LT observability might be slow, so the kernel here we enable all features in the difflow, so the difference is not very strong, but we are thinking how to configure it. We are not very familiar with difflows, but we can run it without any modification. The user uprob only reduce the this is partly in kernel and partly in use space. If we move the kernel uprob to use space, you will reduce. The kernel will reduce like 20%, and use space will reduce like 15%. This is because they are also tracing like the syscall layer and socket and a lot of kprob. So we only move a small part of uprob functions to use space. The others remain the same in the kernel. Here is our low mass. We are also think about possibly new use cases like networking related eBPF in use space because there are already someone using eBPF related network space in use space like GPK, but there's no control plan for it. So you cannot use existing eBPF to translate XDP or AF for it. Maybe can also be used with programmable use-based network space with existing eBPF network applications. We are also considering, can we use like use-based eBPF to spin other fields? We can install some filters in use space. They cannot limit it to the tooling compute and put a lot of logic inside the use-based eBPF. The use-based eBPF can also be used like hot patch use-based functions. Maybe. There are some improvements we need to do, like doing more benchmarks and evaluation, because this is a relatively young project. We also trying to think how to make it work better with kernel eBPF to improve its compatibility and introduce more maps and helper support with the kernel or in use space. We also need to optimize the performance for LLM kit and bring LLM a half-time compare for eBPF. We also need to consider security model of it to make sure the eBPF is not attacked in use space and bring some more tests and CI to it. There are still some open problems because the BPF map currently only works for arrays. We use the main map to map the kernel maps and use-based maps, so to avoid syscall overhead. So how to make a better performance hash maps between a kernel and use-based is still need to think about it and work in the future. Can we introduce like new hash maps types or implement hash maps based on the array maps, or like let the kernel eBPF program assess the use-based maps? We also need to think about error propagation. Can use-based kernel eBPF wait for the use-based operations to load and attach the tagging process, and also can we make the BPF time to another unprivileged BPF runtime? So to summarize, use-based uprob can be 10 times faster than kernel uprob. The shared memory maps and it can have shared memory maps and dynamically inject into the running process and attach to the functions just like a kernel uprob. It's compatible with existing eBPF tool trans libraries, and we can run existing applications on it on your space. It can also work together with kernel eBPF like maps and others. So, is there any questions?
Hi, I have a couple of questions. Can you go back to slide 11 first?
Okay.
So I'm just wondering, when you attach with BPF time, this is in pure user space. Why do you need to use sudo for that?
Use like command line tools.
Yeah.
Because the underlay of it is like a load preload, and we need to load the library to the. Okay. We need to load the syscall processing library to the eBPF applications. And if we want to start the target process with the eBPF runtime, we can use the load preload to load it inside the target process. And you can also use like a ptrace to inject it into. Okay.
I just think that a tool for instrumenting user space and user space should not require root to do it. That's just my point.
Yes,
So
thank you.
Probably you could rework that part to make it, I don't have to use root to instrument my own process.
So the second one is we can use a daemon to control the kernel and load it automatically.
Okay. If you can go to slide 15. So I see a line between the kernel verifier to the JIT compiler and user space. Why is the verifier of the kernel used for user space instrumentation? I personally wouldn't want to use the verifier made for the kernel when I want to instrument my own process.
So this is why we use kernel verifier. Use kernel verifier is in this diagram because the kernel verifier is more complete and have more functionality than user-based verifier. The user-based verifier is an experimental project.
Yeah, but it's made for the kernel to prevent, I guess, malicious program in BPF to halt the kernel.
Yes.
While in user space, I want to instrument the process. I know what I'm doing. I shouldn't have to pass through a verifier made for another program. I know that you mentioned there's some user space verifier also. So
If I make that. So I've seen that in the code base, the verifier that you have in the user space code is MIT licensed, and it's very, very simple. So I guess one of the reasons why you use the kernel verifier rather than copy it over to user space is because of GPL license, right? You cannot
Yes,
use
and
a
this
GPL
project is
program.
MIT license.
So one thing you could do is to move it to a separate server process that would be GPL and would have the purpose of verifying the program. You could also do that rather than use a kernel. That would allow you to run the verifier in user space, in its own address space, in its own program.
Okay, thank you for the idea.
There is a comment from Paul on the chat that Preval is still behind in terms of feature support. But there is also another question on the chat. When you ran BPF conformant tests with the LLVM JIT, did you see any false positives?
Sorry, can you repeat it?
Yeah, so when you ran BPF conformance tests with BPF time and all this, right? Did you see
Yes.
any false positives?
Yes, with some positive like the atomic instructions, but there's less false positive than the RBPF and UBPF. We are still fixing it.
Okay. Any more questions?
yeah.
Oh, sorry.
I have a few more, but you can go ahead.
Well, we are running out of time, so let's give someone else a chance, and then if you have time, come back.
There is also more information in the back of it. If you want to take a look,
So,
please.
so I just wanted to ask about, so in the kernel, when you run the BPF programs, you have access to a bunch of helper functions, and also maybe some K-funcs are becoming more and more useful for different use cases. Do you sort of envision that the user space stuff will start to look at the symbols of the application and expose a lot of functions from the user application to the BPF programs?
Like the K functions?
Yes.
Yes,
Yeah.
we have done that, but it's a slightly different from the kernel F functions. But I think we can make compatible with kernel K functions. The original design of using this is like a FFI. They can call the use-based functions from inside the eBPF runtime. I have done this, but maybe I need to change this feature in the future to make compatible with kernel.
Thank you.
Let's do one more.
Okay. Yeah. In your benchmark, you show that you have improvement of speeds for the hit of the trace points. I would like to see benchmark for memory usage of injecting the agent of BPF time into a process. Also, there's also the latency of inserting trace points. If it's using a stop-of-the-world approach, you basically have 0 processing time of your process for a duration. This is important.
Yes.
So these benchmark could be benefits to your tools.
Okay. Thank you. Thank you for your suggestions. This is I'm going to do. I think this is necessary. We will do it in the future.
All right, we are running out of time. Thank you very much for the presentation.
Okay, thank you.
exciting work.
Yeah. Hello. Thank you for joining. I would like to start my presentation about the use F-trace regs for kernel function tracing. So at first, I would like to self introduction. Maybe most of them are. I hope you are knows me. I'm a co-maintainer of the tracing subsystem and maintainer of the some probes like K probes, F probes, U probes, something like that, and also boot config. And I'm working for Chrome OS platform now. Anyway, today's talk is actually about the kernel tracing layer, not the BPF layer, sorry. But it actually related to the BPF. There is a BPF, let's say that usually that running that the BPF program under under the BPF probes, and that is based on the kernel tracing probes. So that the kernel trace probes change if the interface is changed. The BPF will get some effect. So that here is the current eBPF tracing side layers for the kernel tracing. So the eBPF support that are K probes, caret probes, and kernel merge K probes and merge caret probes, and F entry, F exit. In the K probes and the caret probes, those are running on the K probes, native that are the kernel K probes and the caret probes. But the merge K probes and the merge caret probes, which is recently introduced, is running on the F probes, which is based on the F trace, and something like a caret we call it red hook. So that those are based on the some kernel probes. And here is the PT legs is using for those probes interface. So currently, the PT legs is used for these trace probes. K probes, caret probes, natively using the PT legs. I will explain what the PT legs is. And F probes also need to use the PT legs because it need to run the merge K probes and the merge caret probes. Which is something like tracing the multiple functions at once. So that those are using the PT legs. But actually, that our F trace and our F function graph tracing is using that our F trace regs. It's a bit different one. So that our F probes actually that convert that the F what's it that our F trace regs to the PTX. Or no, it's using that the F trace PTX mode. But actually, that the PTX is what I mean that the PTRS registers. So that it's introduced for abstracting that the registers interface for the PTRS syscall. So that the PTRS syscall is the signal. So it interrupt the user space program or something like that. So that it saves that it can save that all registers by your interrupt handler. So that it is actually in the kernel, the PTX is used by your interrupt handlers. So that it's easy to reuse the PTX in the K-probes because that the K-probes is a software breakpoint handler. And also our U-probes, that is also the software breakpoint inside the user space. So that can reuse the PTX. But however, F-probes also need to reuse the PTX, but actually the F-probe doesn't use any interrupt. It actually using the F-trace. F-trace is something like the function call hook, and just hooking the function call, and by your self-modifying code, so that using that trampoline code. So that causes a problem. So problem is of the using the PT regs in the non-interrupt context is so. As I said, that the PTX is designed for storing all the registers, including the status registers, like a P-state on the ARM64 or flag registers in our x86. So for the x86, it's okay. Actually, that does support to save the current status register. But some architectures, for example, ARM64 cannot save the current status register by manual. So only by interrupt we can save the PTX. So without that, we tried to mimic or that the register saving the routine, but that is not complete set of the registers. So that the PTX anyway, if we try to make our PTX manually, it will be the incomplete PTX. So this is the reason why the ARM64 still not support the K-probes on F-trace and the red hook. So that the F-probe also and the March K-probe and multiple caret probe eBPF probe point doesn't work on the ARM64 yet. So the point is the current parameters. So we can see that the F-trace regs are used on the function graph tracers, but the F-probe has an incomplete PTX, and K-probes actually that's good. So that our function entry by using the K-probes that can make our PTX. incomplete PTX. But in our exit, if we use the caret probe, actually that is using the incomplete PTX. So here, what the F-trace regs. The F-trace regs is actually the handy option for storing the data registers for function entry and exit, because that F-trace regs actually save that parameters, function parameters, and the stack pointer, and also the function return values. So it's a shrinked version of the PTX. And I actually talked with someone working on the ARM64, and they are confirmed that the F-trace regs they can make it on by manual, so that are by your assembler code, the trampoline code. So this one is the repeating the same things, so that the F-trace regs is saving the function parameters, return values, and function calls. That the registers for function calls, hooking that function calls like frame pointers, link registers, or instruction pointers, something like that. And there is some optional date point. But don't include that any status flags or query saved registers. So that is usually don't use do not sorry are not used by your function call. So based on that, currently we are trying to changing that the kernel tracing infrastructure like this. So previously, because we have this trace point, so that the K probes. Previously, we don't have any F probes. So that there is K probes and caret probes, function graph, and F trace. At that point, only the caret probes using that incomplete PTX. That is also problematic, but usually we don't need to care about that, because that's usually function return probe. Even if you use that function return probe, you don't access that data only access that return values. And now we have our F probes, which is based on our F trace. So that as you can see that there are many probes using that incomplete PTX. So and also there is a red hook and F-graph trampoline. Those are doing the same things actually, so that it hooks that return function return, and save that some registers and call that some probes, handlers. So that are doing the same thing. So my plan is to use that change that F probe to use that function graph tracer directly, instead of using the F trace and the red hook. So that at that point, F probe will provide only F trace regs as an interface. And at this moment, we convert that this F trace regs to incomplete PTX for the merge K probes. But as you can see that there are two different function return hooks. So that I would like to duplicate the caret probes. But eBPF caret probe also use that F probe to hook that function return. So that at this moment, in this point, the eBPF interface will not change. But as you see that the incomplete PTX exists, and that is not efficient. So so after moving on to the F graph, all the caret probes users should move to the F probe because there are two same functionality. So that eBPF can move on to the F probe too. But the converting F trace regs to PTX, including that copying the register values to the new buffer, so that is inefficient. So my question or suggestion is can we use this eBPF program direct the eBPF program directly use that F trace regs? So instead of the PTregs interface, for example, that the BPF compiler, if the program only access to the registers, which is used for function call, then we can change that the compiler to use that F trace regs directly. Yeah. So my future proposal is here. eBPF function trace, function entry, and exit tracing maybe can use that F trace regs directly instead of using that PG regs, so that we can avoid copying that F trace regs to the PG regs, and use that the BPF program just accessed from the just access that the registers from F trace regs. It's actually I think that are not hard to change because that the registers are same, but just the difference is that the registers offset in our data structure. So maybe we can export that F trace regs definition to the user space. Then user space can program can decode the F trace regs. Yeah. And I'm not sure that anyone tried to use that eBPF K-probe to probe that the function, not the boundary, but the body, the inside of the function. In that case, maybe PTX is needed, but currently, as far as I know, all of the BPF K-probes are used for function entry. So in that case, that eBPF K-probe also moved on to the F probe function, because that F probe is only for the function entry and exit. Or if someone trying to reuse that the K-probe, or say that eBPF K-probe, put into some function lines or something like that, I would like to help. Yeah, someone is trying to do that. Yeah. So that is my talk. Would you have any questions about this work?
Hi. Thank you, Masami, for doing that. Just not really a question, but more a little bit of background of where ftrace regs came from. I just want to make sure it's, some people may say ftrace regs is part of the whole ftrace infrastructure. Ftrace itself name just really means the function hook thing. I call ftrace, everyone says, oh, this is ftrace, tracing and everything else. Really, that's a misnomer. It's a tracing infrastructure. Ftrace is really just the functionality of the hooking to a function that created function tracing and even BPF hooks. That's all part of the ftrace infrastructure. Now, what happened was with the PT regs, I found out that we save the arguments always for every single function trace. And every time we're doing function tracing, every time you do a hook to a function, in most cases, I know BPF does things a little bit differently, but the hooking to a function requires saving the registers for the parameters. Otherwise, you'll clobber the parameters and you'll corrupt the function you're going to call after you trace it. So you have to trace that. One day, actually, the BPF folks once said, we want to hook into it, but we found out that the only way to get the parameters, we had to use the PT regs version, which saves all the PT regs, which is very slow. And they said the performance was horrible. And that got me thinking, looking at it, I'm saving the registers anyway. Why don't I pass that to all the function call or all the hooks? You got to save it anyway. Why don't we just pass that information? I proposed a patch to just fill in PT regs, just to fill in those things. It got nacked from the x86 maintainers saying that we don't want a non-filled parameter of PT regs. It could cause bugs because people will think that there's a register there that's valid when it's not. So I created ftrace regs, which means just for the hooking of the function. So ftrace regs means everything that you need for a function entry, and we've extended to even exit. So it's very fast. It's what you have to resave anyway to do a generic function tracing. So the point I'm saying is with ftrace regs, it would be nice to use that. If you're saying I'm tracing functions, or in BPF, if you have an interface that says I'm tracing a function entry, the only thing you care about is what's in ftrace regs. You don't care about PT regs. Another thing I'm trying to do, that's the difference between PT regs and ftrace regs, is have a access things. You don't just get a structure of all the data because that's architecture specific. You would have like accessors, like give me the first parameter, or maybe just say the first word of the parameter, because I know parameters could be variable length, but you could just say, give me the first word, second word, third word, and use BTF or whatever to put everything together. I would also love to have a way to pass BTF to a ftrace regs accessor and just say, give me the first argument, or say, this is the argument I want, give it to me, or doing that way. So if we could hook like BTF with the ftrace regs, because it has all the information there. So that's kind of like where I was hoping for, and Masami's been kind of implementing it. So that's a little bit of a background.
I have a question. What's the difference between fgraph trampoline and ftrace trampoline?
Fgraph trampoline and ftrace trampoline is actually that let's say hooking that function entry, so that when our function is called, if we are enabled that our function ftrace, that ftrace change that the instruction of the first summary, let's say that the first instruction of the function, and jump, call into the other trampoline code. That is the ftrace trampoline. And at that point, was in that the trampoline, it called that the summary code and the callback code, and the callback code changed that the return address in a stack or the link registers or something like that, so that it will jump back to another trampoline. That is when the function is returned. Yeah. So that is a function graph trampoline.
Well, today, after I implemented the ftrace regs, everything, I actually converted the function. There used to be two trampolines for function graph and for ftrace. So when you did a graph tracer where you get the beginning and end of the function, that was the graph. Graph does begin and end. A function just does beginning. And I actually had a separate trampoline. So every architecture had a trampoline for all ftrace entry. And then if you want to do the return, you had to exit. When I did this, since I'm passing ftrace regs, which gives you the stack pointer. So now the function graph tracer, if this is supported, will just use the one trampoline. So right now, function tracing will call the first trampoline, call the callback for the function graph tracer, which has access to the stack, which will say, okay, modify the return address to jump to the trampoline at the exit of the return. So when and save the return address into a shadow stack. So at the end of the function that's being traced, when it does the return, it doesn't return back to who called it, it returns back to a small trampoline that will then trace the exit of the function and then restore the return and go back. Of course, we'll have to redesign all this when hardware shadow stacks gets implemented. So, but we're working on that.
Yeah, actually, that are the same. Actually, that the same things doing by your let's say that are K-rate probes. K-rate probes actually that the same doing the same thing, but with the different trampoline code and different shadow stack. So that is let's say messed up that are the real stack.
We have a question on the chat. Does this solve the max active K-rate probe problem? Switching to F-trace or F-graph trampoline.
Wait, what's the question?
Like this whole change, right, to F-trace and F-function graph trampoline, does it solve the max active K-rate probe problem? Because like K-rate probe has like this max active number, like and if you have more than that number of active.
Yeah, that's right. Actually, that is the one reason you'd like to remove that K-rate probe red trampoline, because that the red hook using that summer object list. But the F-graph trampoline actually using the real shadow stack per tasks. So that we need to set that NR max active is we need to let's say pre-allocate that those let's say object for the return stack for the red hook. But that is usually very complicated to set that which one is let's say how many number is enough or not. Yeah.
Yeah, because there's a limit. So with K probes, it was always like you pick a single individual. Function graph tracing said we're tracing every function from every task. So we actually function graph tracer will create a shadow stack for every single task. So everyone has a second stack, and then we do all the tracing. So there's no limit and there's no object limit with the function graph tracer. That's why Masami is kind of switching to try to use the two.
That's great, because I think we are running into the max, whatever it's called, problem in practice, like when tracing like long running sysvals, for example, equal weight, for example.
Yeah.
So anyone has any other questions? We have 2-3 more minutes.
Yeah.
Thank you. So, and I just sort of want to, it's not a question, I just sort of want to mention that we actually do have a use case where we sort of hook a K-probe BPF program onto the body of the function. So yeah, we're working on some sort of BPF-based CFI technique, and we're like in our intuitive design, we're sort of using the K-probe to hook onto those indirect call sites so that we can get the register at that point and then check the caller and callee address.
Actually, that we F-trace already support that such kind of feature. But eBPF will still not have any debugging for let's say that analysis feature or something like that. So that it currently doesn't support the function let's say body probe or something like that. But if someone wanna try, I would like to help you, because that I already do what's it done in our PARF2 probe is actually doing that. So you can let's say check that the feature.
Right. Yeah. Thanks.
You were asking if someone is using K-probes to trace like middle of the function. I think people do, and BPF trace provides you a way to do this. So like even if you do not see like a dedicated C BPF program doing that, like people do it in scripts. So I don't think we can deprecate K-probe, but maybe there is a place for like a new type of probe that will take the F-trace regs directly. And also like, I don't know, maybe we should combine it. Like people will keep asking for having some way to trace both entry and exit of the program, mostly to like capture arguments at the beginning and then like do something at the end, depending on the return code, depending on the latency. So maybe that's kind of like, maybe we can have just generic kind of like multi-K probe, but taking F-trace and actually being called before and after, or maybe it will be configurable. But basically one program that is called twice in general. All right, I think we are running out of time. Thank you very much.
Thank you.
Well, okay. Hello. My name is Jiří Olša. I work for Isovalent. I work on Linux kernel and Tetragon. This presentation is basically how easy or how hard is to lose the execution of BPF program that is attached to some of our tracing probes. So the tracing probes that we have that allow to attach BPF program. So they have like different attach layer. So there's different code being executed for kprobe, uprobe. And so each code has like sort of different, sometimes similar condition where you can actually drop the execution of the probe and the final BPF program will not get executed. It's also important to get some notification. So I will actually show you some of the probes do carry the counter that gets incremented anytime we lose the probe. And I will show you how to get that counter and how to see the stats. The motivation for this actually happened some time ago where we were not very smart in picking up probes in the Tetragon, and we chose to put the kprobe on the put task track. The only problem was that kprobe don't allow nesting. So once you have one kprobe running on the CPU, you cannot get another kprobe running on that same CPU being nested. So what happened was, like, if you read the call chain from the bottom, our first kprobe on wake up new task got executed. The BPF program was running at some point. The IRQ triggered, and part of that IRQ was the RCU cleanup. And RCU cleanup did the cleanup for the task track, and it hit our second probe, which was actually dropped because of the kprobe nesting. Fortunately, as you can see from the last function in that call chain, it did increment some of the counter inside the kprobe object, which until recently we were actually not able to get that counter. It was on the kprobe layer. At the moment, the punch get merged, and we are actually able to retrieve the number from the kprobe objects. So if you run the BPF to link, and if your kprobe is attached to the perf link, so you need to have like link object. Part of the information that now we store at the link is the missed counts, and we allow to retrieve it to the user space. So if you run the BPF to link, if your missed counters is different than the 0, you will actually see it as a missed and the number in the output. The other number, the other counter that we have whenever we fail to execute the BPF program is the recursion misses counter, which is specific for BPF program. And that's actually another sort of check that we have after we actually get through the initial probe execution. Then we have other sorts of check, which if they fail, we increment that number and the BPF program is not executed, but we get notified. I will get to that later. So I will go through some of the probes that we are using and like show where in that code you can actually drop the execution. So let's start with the kprobe. Kprobe is basically perf event, and so you have like perf event object. You create a perf event for the kprobe, and you attach the BPF program to it. You can do it like the old way, using just directly the IOCTL. But if you use the perf link, among other benefits, you will actually get access to the missed counters. So whenever the kprobe is dropped, you will get you will have the way to actually retrieve that number. So kprobe, the attach layer code, that the code that gets first executed is coming in 3 flavors. And basically, it depends what do you want to attach? If you're attaching to the beginning of the function, and you have ftrace on your system, which you probably have, and the object, like where you're putting the kprobe, is compiled with the ftrace flag, so there are the hooks for the ftrace, then your attach layer will be the ftrace code, and it looks like this. So the function gets executed, it goes directly to the ftrace. Ftrace does the magic. As far as I know, it doesn't drop. And there are two checks that we do at the moment. First one is ftrace handler specific check that actually checks if we are nesting the ftrace handler in the execution context, meaning like task, soft IRQ, hard IRQ, NMI. And it should not allow nesting like within one single execution context on one CPU. I'm saying should because at the moment there's a small glitch. It actually allows one nesting of the execution in the same context. It doesn't matter much for the kprobes because the next check right away is the kprobe running, and that's the hard check that will actually not allow like nesting of the kprobes on the same CPU. So even if we nest, it will actually drop the execution on the kprobe running check. It will increment the counter, which we can now retrieve and drop the execution. If not, it continues to execute the kprobe. So that's the ftrace attach layer. We have two more layers, like for everything else. So if you are not attaching to the beginning of the function, or if your object is not compiled with the ftrace flags, there are two other ways of executing kprobe. One is through the breakpoint layer in 3, and that can get optimized to like single jump. So going through the breakpoint code, it looks like this. The checks is basically just the generic nesting check. So basically, it won't allow nesting of the kprobe on the same CPU. The optimized kprobe, if it gets optimized, looks something like this. So there's no breakpoint. There's just jump to the trampoline, which eventually calls optimized callback. And again, there's just this simple check if we are nesting the kprobe on the CPU. So if you get through the attach layer, the handler of the kprobe is actually called, and that one is responsible for executing the BPF program. There are no surprises, like some other drops, other than reaching the reentry check. We have like two types of reentry for BPF programs. I will get to that later. kprobe is actually using the check that will not allow to run another BPF program if there's already like another one being executed. If that fails, we go and increment the per program counter. If that passes, we will actually execute the BPF program. So that was the entry probe. The return probe is quite similar in that case, that to get it actually running, you need to hit the kprobe first. So it follows the same condition as you hit like when you install the kprobe. On top of that, the kprobe, at least on x86, is now implemented through the red hook. So there's this problem that we just discussed in previous presentation, that you can run out of the instances in the red hook, and in that case you will drop the event as well, but you increment the counter, so you actually get some notification about that. If you get through the attach layer for the kprobe, the rest of the code executing the BPF program is basically the same as for the standard kprobes. We do check if there's another program running on the CPU. If there's not, we execute. If we fail, we just increment the counter and go away. So that was standard kprobe. We now have kprobe multi to attach K-probe programs. K-probe multi is based on F-probe, which is based on F-trace. So basically the execution looks like this. You attach only the entries of the functions and you go through F-trace to the callback. And the only check on the attach layer that we have at the moment is that F-trace test recursion trilog function that should prevent the recursion in the execution context. But we don't have any other check like we do for K-probe. So using K-probe multi is on the attach layer, it's more permissive than the K-probe. It is not so permissive when you want to execute the actual program. So when you get through the attach layer code, following code gets executed that's responsible for executing the BPF program. And we have the BPF proc active variable check, which is like won't allow the nesting of the BPF program on the same CPU if there's already one running. So yeah, we get a counter, increment it if we fail, or we execute the BPF program. That was too much. So that's K-probes. For U-probes or U-probe multi, the situation is slightly better. Basically, for entry U-probes, we don't have any missed counts. We don't even have like counter that we would carry. The only glitch is there's also number of nested return U-probes that you can attach. There's like hard-coded number at the moment, 64. If your program is like nesting more than 64 times and gets the return U-probes installed, that counter will actually overflow, and you will get the message in the kernel log, and that return U-probe will be actually lost. But we don't have the counter that we would trace it. So next probe is the trace point. Basically, we have like two flavors, perf and raw. The perf one is basically when the trace point you are attaching to is perf ftrace event. So it basically prepares the buffer of the arguments. To get the buffer, it actually needs to allocate it. It does the static allocation, which can fail, and that function perftrace buff alloc is called like from other processing of software events. So it can actually happen that this one might fail and it just goes away. The rest of is just executing the BPF program with the BPF proc active check. So the same as for the K-probes. The raw trace points are easier, are more lightweight. Basically, we don't use the perf ftrace layer to attach. We take the callback and use the trace point API to attach like directly to the trace point. And there are no surprises there other than we just check the nesting before we execute the program. And this is the other kind of reentry checking that we are doing. So the first one for the K-probes was like, we won't allow nesting of BPF program execution on the same CPU. This one actually allows that unless it is the same program. So we will just prevent nesting of the programs of the same program on the same CPU. If it's another program, we allow it to execute. Perf event, we also allow to attach BPF programs to hardware software events, and the overflow routine basically executes the BPF program, and there are no extra checks other than the BPF proc active. So we won't allow nested execution on the same CPU for that, so no surprises there. And last one that I actually covered but not least is the BPF trampolines. So BPF trampolines works on the top of the ftrace, it's like generated trampoline by the BPF code, and it's generated so it can like execute the BPF programs attached to the function. And so it gets called like from the entry through the ftrace interface. And before executing the program, there's actually check. The only check is there is like for the nesting, which for the per program specific nesting. So we won't allow single program to get nested, but like you can have nested execution of different program on the same CPU. So this is how we go like through the attach layer for various probes. Now about the checks before we execute the BPF program. So at the moment we have like two types of these checks. First one, more permissive, is per program, and as I said, it allows you to execute like multiple nesting of multiple BPF programs on the same CPU as long as they are like different BPF programs. The other check is the per CPU, the BPF protective variable, which is much more restrictive. And once you have like program being executed on the same CPU and it gets interrupted, this check will like prevent of running any other BPF program on the CPU. It's also used by BPF syscalls to actually like disable BPF program while updating maps, or well, map update and map delete from just some particular map types. So yeah, it's used also not to mutually exclude the BPF programs, but also like to disable the instrumentation from the BPF syscalls for some operations. So as it looks like the list of the probes that using the per program and per CPU check looks like this. I recently, some time ago, sent a change to actually move the kprobe multi to have at the moment, the kprobe multi before you execute, it has the per CPU protection, so it won't allow execute the BPF program if there's like another one running. But it looks like we can actually move it to per program, which would actually fix that use case that I showed at the beginning. So what happened there is that we have like two kprobes, one on the wake up new task, the other one on put task track. You execute the first one, and within the first one there's REQ, and you execute the put task track. And at the moment, if you are attached with the kprobe, there's the kprobe running check, and the second BPF program is not executed. If we move it to be attached by kprobe multi, at the moment it will not get executed as well. It will pass the attach layer, like the check. The kprobe multi attach layer is much more permissive. It will actually get to try to run the BPF program, but it will fail on the BPF proactive check, because there's already, like in the task execution context, there's already program running. But if we change it to be per program, we actually would get the other program running. So that's we had some discussion on the initial page that with that change you can get some really weird traces, especially when that ftrace reentry function, the trilog, can allow the nesting. So I guess we need to have the discussion again, and I'm planning to send the patch. One more thing I'd like to mention, while I was actually adding the support for the counter of the missed execution, Andrea asked if we can actually have counters, extra counters for the function. So what happened is that before we had the kprobe multi, the missed counter will be like per kprobe, which means per link. So each kprobe represents a function. So you can actually say which function you lost, like the execution in. For kprobe multi, you can have like 1,000 functions under one link, but there's still one counter if one of those functions actually get lost. So we don't have like, you are not able to say which function you lost. So at the moment, I don't see any other way like there. If you want to keep the counters per the function, if we are going to increment that counter, we actually need to do some hash lookup based on the IP. So that's something I'm checking on. So it's not like cheap to keep that counter. On the other hand, we just lost the BPF program execution, so we saved some cycles. So maybe it's acceptable to actually increment it, or maybe we can just do it optional, and everyone can enable it if needed. And yeah, that's basically what I have. If you have any questions.
Thank you for a good presentation. And I think that you can use that F probe instead of K probes in that case so that are only for the single function tracing, like a single K probes, you can use that F probe. Yeah, then the nested check will be gone. Only use that I'll say the context-based nesting check by your F.
The function is going away?
F trace.
The function is going away, that recursion check will no longer be there?
Yeah. Sorry.
I'm sorry, I might have misunderstood. So you're saying we can get away, like we can remove that check, or?
Yeah, so that are the K probes. Using the K probes, this means that the K probes, let's say, introduce that the K probes nesting check, because that the K probes endured user, let's say that the user program will not be nested. So that the user program can access to some global variable or something like that. Yeah, but if you if you use the F probe instead, then F probe is checking that the nesting check on the same context, like let's say that so that's something like if you call or using that some function which is let's say instrumented by your F probe from the callbacks, that will be your let's say just skipped or ignored. But if there is some let's say that let's say interruption happened inside that the program or something like that, in that case that the context will be switched to the interrupt context.
Right.
Yeah. In that case, that the F probe can nest.
Yes.
Yeah.
First of all, I would not get rid of the F trace recursion lock. I would not get rid of that. That's really after adding that, I stopped getting all these crazy crashes. So a little history before that little one time we allowed 2 recursions. The history is because it's based off of the preempt count. It tells you which context it is. Was it normal context, soft IRQ, or NMI context? And sometimes there's a trace point or a function will be traced before the preempt count is updated. So it would actually, if you actually had a trace that actually happened while another trace is going on, it would detect as a recursion because the context hasn't been updated yet and allowed in. And this showed up as bugs because you'll get, oh, I entered interrupt, and then suddenly I didn't enter interrupt. And I'm like, but you see other interrupt calls and saying like, I'm missing the entering of the interrupt. And that's because trace happened within another trace and the preamp count. But with Peter Zilstra's work that he's been doing with the no instrumentation thing, no function call should be ever called now without preamp count being updated. Last time I checked, I said, so I got rid of it and I found out, no, there's some places that still do. I think they were all fixed. I remember we had a little conversation. Have you tried it? By just removing that?
Yeah, I saw some work, but I didn't get like to, if he has something new about it, like if there are
I mean, I wasn't sure if you tested it to see if it would trigger or if there was places that could actually call in the wrong context.
So I tested just for my use case, which was like that I was able to get like kprobe nested invocation in the same context. Like if I had a task, it hit the kprobe through the ftrace, and that code, like the BPF program, executed another helper that had a kprobe on it. I got it as well, like in the same context.
But that's because you still had this iteration in, right? Did you remove the iteration, the iteration check? So did you change the ftrace recursion check to get rid of that the transition bit?
Yeah, right. No, I didn't check that
I'm
one.
saying, that's what I'm saying is I asked you, could you try that to see if you're still,
okay.
I could do
get
the
it.
test. I could actually get rid of it.
No,
and
I
see
didn't check that one.
if that bug is no longer there. Because it was a workaround for a bug that hopefully has been fixed. So we could get rid of it. So it should not do the recursion bit.
All right.
So I'll let you know. I'll put that as an action item for me.
Okay.
It should not be a problem. That was a workaround. It wasn't part of the design.
Any other questions?
Hey, I just want to ask about this 64 depth limit on uprobes. That is applied to to the new uprobe multi?
So yeah, you mean on the URED probe, right?
Yeah, of course, yeah.
And sorry, what's the question? This one.
Yeah, so the question is if you use the new uprobe multi to attach to the return probe, if does the limit still applies, or you can attach to like thousands of functions?
Yeah, it does. It still uses the uprobe layer to. I mean, the uprobe multi matters for detach, but we still use like the uprobe layer, same as for the single uprobe. So it has the same problem.
Okay, thanks.
Once. All right, thank you.
Well, all right, folks. Today's presentation is about how we're using K-probes and U-probes together to try and enhance observability. Well, how do people even go about understanding why their systems are suddenly slow, right? Well, there are many ways to go about it, but one of the very common ones is that you have a high-level metric or a high-level performance indicator, and that just suddenly shoots up, right? And at that point, you don't really know much more than that. You have to try and use tools, and like it is non-standard the way you have to try to drill down from that high-level performance indicator down to the root causes of why things are now slow. So you can, for example, use CPU profiling, flame graphs, or distributed traces to try and see if any of the functions stand out. And hopefully at the end of this process, you've identified a culprit function, which is definitely taking longer than it should. But even then, it's not obvious at first glance why that function is slower, because latency degradation can have several different root causes, or as we like to call them, the horsemen of latency degradation. Bear with me, I know that there are more than 4, it's just I really wanted to use this reference. So I guess the point here is that a lot of these horsemen are actually outside of user land, and by the usual latency only tracing of functions, you don't really see them at play, so it's not obvious. So really our idea with X probes, which are hybrid U probes and K probes, is essentially just we want to trace them all. What trace all the horsemen, right? And because of the amazing work that's been done by the BPF and the BCC communities, we now can. So let's go with an example. Things will become clearer. So this is a situation you might have found yourselves in sometimes. You know it for a fact that function A used to run well, it was quick, everything was fine, and then suddenly it's slow now. Well, it's not immediately obvious why that is until you start getting more information about what is being done with that latency, right? So when you start being kernel informed, you may get this kind of picture, which is saying that your function is not necessarily doing any more work. It is really just spending time outside of the CPU for whatever reason. So that gets you a little bit closer to the root cause of it. And in this case, the root cause of it is actually pretty silly. I just ran 2 programs on the same CPU core and had them fighting for cycles. So that created CPU contention, and that was the reason for this specific slowdown. But what I really want you guys to think is, I guess, broader in terms of all the cool indicators that we can get, all of the interesting patterns that can emerge once you start getting your traces to be more kernel informed. So you can look at the I/O latency that's being taken by each function, the off CPU latency, the lock latency, all of those kernel concepts that we're currently not getting with latency only tracing, right? But I guess the next question is, how do we even get all of this data? And well, the pieces are pretty much there. I'll enumerate what we have now and essentially the small delta that we did in order to get things working together, K probes and U probes talking to each other. So currently, we all know there are K probes, and they can introspect on all of these events like context switches, mutexes, file system reads, and the sort, locks. But the thing is, they only look at these things from the process perspective, which is the PID point of view. I know you guys are going to say, of course, we can get the stack traces that are running on a PID, but for our purposes, this is not ideal because the stack traces don't give us when the function began and when the function ended, right? So we actually need to know when each invocation began and ended so that we can attribute the resources taken by each invocation. And this is exactly what uprobes give you, which uprobes know exactly when a function begins and when the function ends. And even better, BCC currently has instrumentation that can keep a shadow stack of the process at BPF map space. And that shadow stack is essentially mimicking the stack of the process with all the trace functions, right? So this is all public. This is all on BCC right now. Essentially, our job was to realize that these things are currently not talking to each other and, well, essentially do that. So we created attribution logic for each of the specific K probes that we are interested in. And we make the K probes talk to the shadow stack that's being kept by the U probes. And we can then attribute resources and get all those bars that I showed you. So let's talk about the attribution logic for a while. So essentially, here's an example. We have thread 0 running function A and thread 1 running function X, right? So now events are going to start happening, and we're going to see how things change up from that. So the first event that happens is function A at thread 0 calls function B, right? So the U probes are going to stack function B on the shadow stack of thread 0, and we are going to start the on CPU clock for thread 0 for function B at that point because it's running on the CPU. The next thing that happens is a context switch. So from thread 0 to thread 1, it is pretty straightforward that we now need to stop the on CPU clock from thread 0 and start it on thread 1, so that because that's the one occupying the CPU. That's pretty obvious, right? So fast forwarding a little bit, let's just say we context switch back to thread 0, and now function B exited. So we need to do 2 things now. One is we got to save the on CPU clock somewhere so that it can be useful for any kind of analysis. But a less trivial thing that we need to do is we got to get that on CPU clock and propagate it to the caller of function B, which is in this case function A. And this is because function A can have broadly different resource usages depending on who it calls, right? And we need to profile all of its callees so that we have a good idea of each execution of function A. And this is specifically why it's really useful to use the shadow stack, because then you don't need to trace function B, function A, and whatever functions are on your stack separately. You can just trace the one at the top at all times and then propagate the overheads when it returns, right? Speaking about storing stuff, well, there are many ways you can do that, and this is really where a lot of my research was in, trying to understand why, like how to store these things in a very efficient way, how to get the data that we want to serve several different applications, diagnosis tasks, and that's all fun. But unfortunately, for the rest of this presentation, I'm just going to have to focus on the elephant in the room, which is the overhead. So let's look at a benchmark, and we'll see more about why that is. So I just got Redis, right? Just basic Redis, one machine, my CMU computer, and I benchmarked it. No tracing, no nothing. And the baseline was about 450,000 for GET requests. Their sets are also there, but let's just focus on the GETs right now. And I use memtier. So, and then I ran the K-probes, which are like schedule context switches, mutexes, and I benchmarked that as well. The overhead was pretty good. Like, it wasn't much, right? So emboldened by that, I just said, let's just use our X probes, which are U probes plus K probes, to benchmark everything. And then I was pretty humbled, because tracing all the 5,700 functions of Redis, as you guys can see, or maybe you guys can't see because the blue bar is really small, didn't really work out well for me. We went from 450,000 to 4,000, which is interesting to say the least. So with that, humbled by that, we were like, okay, let's trace just one of these functions. And then we chose zip hash because it was a very hot function. So at least might as well trace a function that happens a lot, right? And we traced it in two ways. We got we traced them with the X probes, which are U probes plus K probes, and we traced them just with the U probes, right? And I guess the takeaway from that is that we can see that running X probes is the main overhead comes from, since X probes are U probes plus K probes, the main overhead comes actually just from running the U probes. This was expected. People told us that this would be the case. But we wanted to also break down why running U probes was so slow. So we just created this new U probe, which immediately returns. So that the idea here is, if the U probe immediately returns, the only overhead that we're going to see in that U probe, since it's not doing any work, is the trap overhead. And yeah, people also told us that that was going to happen, and the overhead was mainly just from the trap. The work being done inside the U probe is actually done really quickly. Just context switching into the kernel to run the U probe, that's where the bulk of the overhead is. So I guess this leads me to the state of X probes right now. We would love to have a fully eBPF solution, just because of all the things that this entails, all the features, all the nice stuff. The wide adoption for observability. You don't need to instrument anything. It just hooks into your program and you can see everything. It's beautiful. We really want that. However, overhead-wise, it's a different story. And well, I guess to finalize this presentation, I'd like to point out the main things that we'd love to hear from you. And this is why this presentation is shorter. We really want discussions that we want a way out of this. Because right now X probes, the overheads are too great for them to be taken seriously at all. So do we want to stick with stick with U probes? Do we want to, well, maybe the BPF time people are going to make them amazing, and that's not even a problem. These lights are outdated and they're going to be awesome. Or maybe we're using U probes where we shouldn't. We should be doing some manual instrumentations and user space maps and just use the K probes to update that. There are several possible designs that we can go about, and we'd like to hear from you. And also, if we missed any of the important horsemen, then please do let us know, because we certainly did. And so I guess, Leslie, thank you all for your time, and let's trace them all.
Okay, while everyone else is thinking about questions, one point that I want to make is that U probes can be twice as fast depending on where you put the probe. If you put a probe in the knob, it will be twice as fast, roughly.
Ooh.
So, but that requires like compiling your user space code was basically what we do for kernel, like leaving five byte knob at the beginning of the function. Which you can instrument, like not instrument, like you can add some parameter to the compiler.
The F entry thing, right? The 5 bytes of knobs. Is it an F entry option to GCC, I think?
So F entry is relying on that, but compiler argument, I don't remember how it's called, but there is a compiler argument to do this. It's actually like kind of configurable and stuff, but
a question. So why do you need uprobe at all? Because like you tracing changes which happens to a process, and everything happens inside kernel.
The what?
So any change to your process happens inside the kernel. Why do you need the uprobe to just?
Well, the uprobes are essentially just updating the shadow stack, which we need because we need to know for each execution when it starts and when it ends, so that we have the wall clock time, which is the absolute time that it took, and you can't really know from the kernel events when the function started. Even if you look at the stack traces, it can be the stack trace it can be the same stack trace, but it can be a different execution, right, of the same function. So that's why we use uprobes, because we know it for a fact when the execution started and when it ended, and we can attribute exactly the overheads that are happening in the context of that one execution, right? And then we store that. We're thinking about the stack trace one, but the problem is many things can happen, and the same stack trace can pertain to different executions of the same function.
Thank you.
No problem.
So Lawrence is asking half of the overhead is instruction emulation in the kernel, and Alexei is pointing out that it's not, well, okay, maybe you can just.
Well, it's probably Young Hong, if he's not the audience, can explain it better. So the uprobe worst case can be 3 traps if you're unlucky, then it will be very slow. In typical case, when there is no knob, there will be 2 traps. And if it's just single knob, single byte instruction, because nothing needs to be simulated, it's only like trap into the kernel, then it's a single trap. So I suspect your numbers is this likely good case of double trap. So if you just put a knob and remeasure, like you will get better results. So your elephant will not be as big.
Okay, awesome.
Yeah, we tested in our production hardware, and like we were getting like 2 million uprobe executions per second. So it's not as fast as we would like, but it's still plenty fast for a lot of things. Maybe not for tracing malloc free without overhead, but. Any other questions?
Anyone want to add a horseman to the pile? I promise I got a bigger picture with more horses.
So I have a question. You're a couple slides back, like because there you're saying you had a couple more, like the difference. Yes, so this one. So X prop and U prop. So what do you mean here by X prop? Because I thought like through the first half of presentation that X prop is just a combination when you use both K prop and U prop. But here you're saying like X prop on this SIP hash. What does it mean to have X prop on SIP hash?
Yeah, it means that you're using the U probe to keep the shadow stack is essentially just the SIP hash in this case, right? But essentially the shadow stack only has one function, yeah. So all the K probes are attributing to that one function, and when it ends, the shadow stack is it's completely empty, and then when it begins again, the shadow stack has one function again.
I see. And uprop is just a uprop.
Uprop is just function latency, for example.
At all.
Yeah, just the usual get the function latency of SIP hash.
Thanks.
Yeah, there. Incoming.
So can we, or I'm not sure that how that eBPF will work, but can we inject some eBPF event from a user space?
Can we what?
Inject, so that like what's the you can recompile that the user space program or something like that, so that you can add some what's it that the system call to call back that the kernel directory there from there, and that callback just invoke that some kernel space eBPF program, then what's it that maybe it will reduce the overhead of use because that using the U probes it actually that forcibly what's it that put that what's it the software breakpoint on the user space program and emulate that the user space program inside it. So that the overhead is coming from that, what's it, that handling that the software breakpoint from user space, so that we need to change that the context and switch context and what's it, that run callbacks and emulate that the instruction. Yeah, that will take a time. And go back to the user space. That will cause that overhead. So that why the NUP what's it that reduce that overhead is we can skip that emulating that the user space instruction in the kernel. Yeah. So that's but if you can what's it that just call that the kernel to invoke that the BPF program, that should reduce that the overhead so much, I guess.
From what I understand, you're trying to
Because that it just takes one system call overhead to call what's it invoke to run the eBPF program. Yeah. But I'm not sure that the eBPF has such kind of feature, like I/O control eBPF or something like that.
Well, I guess we came to the right place to ask.
Yeah. Anyone knows, or can we inject some user space event, eBPF event in the kernel? No.
Just run a BPF program.
Yeah, something like that.
Just saying this proc test run, you could just do a BPF syscall and just say, hey, run this program. That's I guess one option. I don't know if that's quite the shape of the problem you're looking to solve, but it's something in that space.
Yeah, but maybe it's if we can introduce such kind of feature, like injecting that event, injecting probe or something like that for the eBPF. Yeah, maybe it will reduce that overhead. Most of the overhead of the using that U probes. Yeah.
So the problem with this is like the beauty of uprobe is you take some application that was compiled without any expectation that it will be traced by eBPF or any other means, right? And then like you suddenly can see something, right? Like all the solutions like what you're proposing requires like specially instrumenting and compiling the code, which kind of removes most of the benefit basically.
Yeah.
But I'm actually wondering like if you combine a little bit of user space rewriting, right? Like doing the trampoline in user space, which will do like this either special syscall or whatever, right? And go to kernel faster than the interrupt. Then it might be actually a good solution. Like, so BPF time, right? Like one of the limitations that like, if you want to interact with like BPF site maps, you need to do like some sort of kernel interfacing that's slow, right? Or you need to stay completely in user space and both are kind of limiting, right? So maybe the hybrid good solution is like to have user space small trampoline that will just go directly to kernel.
Yeah.
And like will provide you know whatever the IP was and stuff like this. And that might be a good way forward to make uprobes faster.
Yeah.
So like application still doesn't need to know about the instrumentation. It all kind of magically happens, but it's faster. So I would look into that.
Would that be a mechanism for all uprobes or specific like uprobes light, like a subset of the uprobe?
All uprobes. I mean, like it doesn't have to be literally uprobe. It might be some new type of program if you need to. But like basically a little bit of user space, p-tracing or whatever, and then just kernel support, like to have like a very lightweight syscall or something where like you pass, I don't know, one argument, right? So like it takes the minimal amount of code and just.
Or even run the uprobe in user space like they were doing, I think, and writing to a map that is mmap between the kernel and the user space, right?
So that's what BPF time provides, if I understand correctly, right? The problem is like, okay, if you do one map update, then maybe it's on par as far as performance is, because like it's once this call, right? But as soon as you do 2 updates per program run, then like you're losing already. While like if you just switch to kernel once, then everything else is fast.
I see.
And like also you don't have limitations like which map types are supported and all stuff. You just have all of the kernel infrastructure.
Yeah, it's something like a traditional, what's it, asynchronous or synchronous execution program. So that are, yeah.
You still want synchronous though.
No, actually, that the BPF time is like running that asynchronous and synchronize the result on the map, sharing map. So that that need to wait or something like that. But if we directly call back the kernel, we can synchronously.
But that's also limiting, right? Like there are situations where like you actually want to grab like the state of the kernel and state of the user space at the same time, and
Maybe we can have a tail core switch from the user space eBPF program running, and after the tail core to kernel eBPF program running. I'm thinking about this before.
Yeah.
Synchronize. Async.
Yeah, synchronize. Yeah, maybe we can or we can record that the different data and afterwards we can synchronize the recorded data. Yeah.
I see. Yeah, I'd be scared just because functions are changing constantly and waiting to synchronize. If writes are happening on the kernel space and the kernel events are being attributed to something that's not synchronized, then you're gonna start getting stuff that is weird. I think. I don't know. I'm not sure.
Yeah. It could be.
So a comment here. So just based on like what we've seen so far today, the BPF time presentation and the attempts that people try to accelerate like UPROPs and your presentation, elephant in the room, the fast UPROPs is definitely something that like tracing community need. And like the existence of multiple rewriters, the injection frameworks, this like Frida that BPF time is using, that LTNG folks are using LibPatch, I think it's called, and there are like all sorts of various this injection technology. So people need this kind of stuff to inject the code. But all of this user space to user space code injection, BPF time including, and if LTNG folks were in the room, they could explain it better. They all suffer from being in the same context. So if BPF or anything else, LTNG, they're all running in the context of the task that they inject to, they share the same fate, meaning the signals are all the same. They share the same like file table, they share the same memory, etc., etc. So for example, if you're tracing a task that doing like close all syscall, like it will close all file descriptors. And let's say you set up a ring buffer from your like user space BPF program that's supposed to like transfer. The task doing close all will just like kill your tracing. And similar with malloc, because malloc is shared between. So I think like LTNG, BPF time, and everything else, like all of this injection, they suffer from this issue. And in 80% of the cases, it's okay, but corner cases makes it like impractical in many conditions. So I think the design parameters for this like fast UPROPs would be to switch from this task context into some other context, maybe of different task, but if it's different task, it's probably same as switching to kernel. So I think that's sort of main design requirements, taking a user task and switching to kernel as fast as possible with a system call or something else. It's probably mandatory part of the solution. Otherwise, there always will be issues. Even today, looking at UPROPs and especially like URED props, like UPROPs typically don't crush user space, but URED props do. Like even though like kernel is trying to do as accurate as possible, but depending on application, depending on what it's doing, you just put a UPROP in there and it will segfault.
So
Well, it's actually a kind of protection mechanism by the kernel when it detects that it cannot match the return to the entry, which can happen like when the user space like does the stack swap. So like for what is it called? Getting this term, fibers, for example, or maybe even for coroutines. I don't know, but yeah.
exactly, like fibers, coroutines, all of this like fancy compiler stuff, like injection techniques will struggle with this. It's just, but yeah.
I think that's what we're talking about, right? Like even with like code rewrite, like wouldn't like if someone replaces the stack, like isn't that a problem? Maybe I'm just saying like this is another problem to solve. Like,
So all I'm trying to say that like fast UProbes is definitely an excellent problem to tackle, and lots of people in the companies like really need a solution.
That makes a lot of sense. Thank you.
Thank you for the presentation. I have two questions. One is, well, three actually, sorry. One is, does this work with recursive functions?
It should.
Okay. Is there, I believe you. Are there?
It should.
So,
Your data is going to look a little weird, I think, but it should
okay.
work with recursive.
So do you think there are situations in which including this tracing may distort the behavior of the function itself?
Oh, by all means, yeah. The blue one, the one we traced all the 5,700. I think once you are at that level, all bets are off, and you only, several interactions that you would normally get you're not really getting, because most of the time your CPU is just running the uprobe stuff and context switching. So I cannot say for sure, but I certainly think there is a lot of noise from the tracing on the blue case, the trace all.
One more thing that I wanted to mention is that from my perspective, the one thing that I hate the most is debugging race conditions. So
same.
If there is like if you can measure how long it takes for a function to execute on average, it will be cool if you guys had support so that whenever you get into a case in which it's taking longer than the previous profile expected, then you can just assume it's going to be a race condition. And in that case, I will definitely use the tool.
Yes, that's one of the cool things from like using the shadow stack. You know exactly you have a distribution of how much you expect the executions to be, and you can have like a threshold for the P90, P99 latencies, and once that crosses, you can actually get the arguments that were the arguments of the outlier function. You can log the outlier function. You can BPF print K the outlier function. You can actually have this anomaly detector like a watchdog based on the expected distributions of stuff, and have a proactive system that throws you like a warning, hey, this function took a long. So yeah, that is all the cool stuff that we really want to do if this works fast.
I will mention though that from my perspective, overhead is not such a big deal. I obviously don't want to be running experiments for hours and hours, but this is not production, right? This is just me trying to figure out my code. So I wouldn't worry too much from my perspective.
Fair, yeah, same. Thanks.
Thank you.
All right, thank you very much. Clearly, fast UProbes is the topic of the day. Yeah, we'll have a break for 30 minutes. Yeah, and come back after that. Thank you.
Thanks, folks.
I should talk to you. Nice t-shirt. Yeah, that's the way I want to talk to you. This was at the Nice Things Week conference, right? I was going to ask you how you feel about the conference. This one. Yeah, we got Alex said that we should switch the times, right? Switch times when it happens. Yeah. It seems like they will try. What BPF presence? How you mean like whether it's part of BPF? Or whether you but I think it's useful because that's part of the community. It might be a rose for it's very good, I think. The intro guys can. That's some weird stuff in the east. The application for I figured I'd say it to your face. It wasn't available. Do you think it's better for? Yeah, it's not. It's up to you. I don't see any reason why not. It's not that obvious. Anything like that. By the way, it's not hard to stop. Say what?
What's exciting? Not kids. Oh, shut up. You hear BPF? Interesting. If that's the case.
All right, let's get started again.
So, my topic is BPF programmable net devices. So the goal for this talk is really that I said to myself, like, how can we achieve the lowest possible networking overhead for network namespaces? Kubernetes pods, they are basically, you can view them as network namespaces. And how can we get there? So if you look at the typical Kubernetes data path architecture, nothing optimized, default meaning the most compatible with also older kernels. The way it basically looks like, you have the host, there's kubelet running, there's kubeproxy component running, then you have a pod, which you can regard as network namespace. It has Weave devices connected. And if you use Cilium as a CNI, there's basically a Cilium agent and a Cilium CNI plugin. That CNI plugin itself is basically like a standalone binary, which is called from the kubelet when a pod is being added. And it will basically create devices. It will it has some IPAN management. It will assign IP addresses, routes, and so on, and then move them into the target network namespace. And then it will basically have an RPC call to the Cilium agent telling, okay, this process is complete. And then the Cilium agent can move on and, for example, assign BPF programs and so on and so forth, do the rest of the endpoint management. The Cilium agent itself is typically deployed as a daemon set in Kubernetes, and that's sharing the host network namespace. So that's in the kube system. And yeah. So what you can see here is like the routing is done through the upper stack. And there may be some reasons why you stick to this. For example, for regular users, they start out with, okay, like I just deployed it with the defaults, and that's the way it looks. Or for some reason, they cannot replace kubeproxy component, or they have custom net filter rules. So then they need to go with this. What problems are with this kind of architecture? So kubeproxy is basically there to implement Kubernetes services. And if you deploy many services, that's basically like services are basically the main communication thing, because they have like fixed IP addresses as opposed to pods. Pods they can churn, come and go. So all the communication happens in Kubernetes typically through services. So then you can get like really long list of IP table rules, and this can be a scalability issue. That's one thing. In case of Cilium, I'm not talking about this today, but this has been covered in previous LPC conferences. We have a BPF-based replacement for kubeproxy. Interestingly, at the last week's KubeCon, some of the SIG networking folks from Kubernetes angle, they decided that they would move forward with NFT for the kubeproxy component itself. To basically address the scalability issue where you have to walk the linear lists. Then the other thing that is problematic, if you go to the upper stack, so basically when the packet goes to the host Weave device on the ingress, when you logically want to route packets out, you hit the upper stack, and in the upper stack there's this SKB orphan, which is, as I understand, mainly there for netfilters tproxy. But that's basically what you hit when you hit the forwarding path, and that's problematic because it breaks TCP back pressure, because it would evade the send buff limits. And if you look at performance, so basically we have here like a node-to-node over wire. That's basically the yellow bar where you hit for a single TCP stream flow 100 gigabit. Then how does it look if you do pod-to-pod routing over wire? Then you hit 63 gigabits, because mainly because of the TCP back pressure breakage. So yeah, the question became, how can we improve that? How can we reduce this overhead? So one thing we did in Cilium, which has been a while back now, but I thought I mentioned it here for context, is BPF host routing. So basically the idea is add 2 new helpers to BPF and let them route inside the host through the TC BPF layer. For the ingress side, there's this BPF redirect peer helper where the packet basically arrives on the physical NIC on the TC ingress, and it rewrites the device pointers to the device that is inside the pod, to this peer device, and it does another loop through the main receive loop, and then basically we are already in the target network namespace. So this allows for a fast net and S switch on the ingress side. Those are basically the details. We fetch the device pointer from the host-facing weave to get to the peer. We scrub the packet, we reset the device pointer, and then we do this loop, and we can avoid the per CPU backlog that we otherwise have on the weave device. On the egress side, we basically have this helper, which is called BPF redirect neighbor. So you can view it to insert the packet into a neighboring subsystem of the stack so that it can resolve the L2 addressing without having to care about that. So it's utilizing the stack here. And the advantage is that it basically also fixes the TCP back pressure issue because the SKP-SK will be retained all the way to the physical device, and then there may be a queue disk. It might sit there a little bit in the queue, but then really it gets only the TCP stack gets the notification really once the packet has left the node. So that's how the complete picture looks. The nice thing is also that you can reuse the BPF FIP lookup helper, which we do. So we utilize all the routing infrastructure from the existing kernel. If you look at the performance benchmarks, how this looks like, so that same TCP stream benchmark from pod to pod now bumped from 63 to 90 gigabit per second. So this basically really gives a huge advantage. But one thing is, well, it looks nice, but it's still not on par with the host. So we really would like to also get to the 100 gigabit. So there are 2 components like on that journey. What we added and presented last year at the LPC, I'm not going into details here, is basically a new TC BPF based fast path, which we call TCX. That has been merged on the 6.6 kernel, and it reduces the entry point for TC BPF so that we cut the cycles in half compared to the old style TC attachment. And then the other thing that got added with this was BPF link support, which was missing in the TC infrastructure, and which is really crucial, especially if you have multiple users on the TC hook, so that they don't step over each other. So then the next step after that, this was kind of the prerequisite to get the netlink work moving forward, because the TCX basically had a new framework for attaching and describing dependencies, and the same was also needed for Netkit, because people would like to add multiple programs and not just a single program to that. So the next thing was basically a new driver which we can use to replace the weave devices with that. And that's basically, that has been merged recently in the merge window, and that's what we are planning to move forward with for the Cilium CNI. So basically, when this Cilium CNI plugin that I mentioned earlier sets up the devices, it will create Netkit devices instead of the weave ones. And the internal program management is handled through this BPF mproc framework. And the idea is basically to execute that inside the pod at the driver's XMIT routine, so that this basically allows also like a fast net and S switch on the logical egress side. Yeah, and it also implements the NDO get peer def callback, so that you can have both like a fast ingress and fast egress network namespace switch. The devices are configurable as L3. with the option to also have L2 if you really need it. And there's a default drop that you can configure if no BPF is attached. So for example, for the device that is inside the pod network namespace, that is quite useful. So when the CNI plugin sets up the devices, it can configure that no traffic should be leaked until the point where the actual BPF program is set up from the Cilium agent. And the other thing that was important also was basically to, as you can see here, like this device pair is like, it has a primary and a peer device, and all the management should happen through the primary device. That primary device is typically in host network namespace, so that from our side, from Cilium side, we have access to that, and we can manage BPF programs for the primary device itself, for example, if you have policy and whatnot, but also for the peer device. So no application inside a pod should be able to detach or mangle some BPF programs that are sitting on the peer device. So all the management really happens and is enforced through the primary device. Here's how the XMIT routine looks like. I mean, the idea is fairly straightforward. You have a default policy. If nothing is attached, the SKB gets scrubbed. Then we reset the device pointers to the peer device, which implies this network namespace switch, because now the FIP lookup will look up the everything under the host network namespace instead of the pods. Same with the BPF redirect when we pick up and look up the devices. Then it executes the BPF program array that is active on the node, and then depending on the return code, there's either this netkit pass, which is then basically the idea is to push traffic inside the host namespace for local traffic, or if you do the netkit redirect, it can then forward the packet directly to the physical device. Those return codes, they are binary compatible with the TC BPF side. And when the programs run, so they run in a multi-proc array. So there's this mproc for each, which iterates over the different attached BPF programs. And again, like the same style. So the idea was that we can use from Cilium, the BPF programs that we have attached on the host-facing weave on ingress, and we move them into the peer device of netkit. So that was the idea. And then we have this mproc bundle, which you can swap when you update, when you add or remove programs. So a little bit of background. In Cilium, we used to have IP VLAN support. Not anymore, but it was like a limited kind of POC in the past. And back then, the idea was basically, well, the Cilium CNI plugin sets IP VLAN slave devices. It moves them to the target network namespace. And the way we did that was basically to have a very simple program attached, which has a tail call map with just a single entry. And we moved that, we attached that to the IP VLAN slave device when moving the whole device into the pod. And the tail call map was basically accessible from the host namespace, so that the Cilium agent doesn't have to switch network namespaces, because we cannot do that, because we don't really want to map the host procfs into the Cilium container for security reasons. So with that little trick, we were basically able to update the BPF program from the host that is inside the Kubernetes pod. Yeah, and that's where we moved our BPF LXC programs that we have in Cilium. There are limitations with that. So for example, if you're familiar with IP VLAN, so it has an L3 mode. With the L3 mode, you have the problem that there's net filter asymmetry on the logical path into the pod. I think the net filter hook is skipped, but on the egress path, it's not skipped, which can lead to problems. For example, in case of Kubernetes, there are some rules where a packet becomes or has an unknown state and the connection tracker is basically being dropped. So the problem there is we had to switch to the L3S mode, which means for the logical ingress path into the pod, it has to go up to the net filter subsystem and then from there do the network namespace switch. Okay, not the biggest deal, but a problem that that is still there is that when you have BPF programs attached inside the IP VLAN slave device, like inside the pod, they could potentially be unloaded by applications. And that's not really what we wanted to have. So we really wanted to have this inaccessible. Then if you run the BPF programs from inside the pod, you don't really have access to the layer 7 host proxy that we have in Cilium, that we have with the Envoy. So you can really only do layer 3, layer 4 policy enforcement. Some of the service handling, yeah. But then the other question is, okay, with IP VLAN, you have to pick one IP VLAN master device, which is usually a physical device. And then what happens when there are multiple physical devices? So those were some of the limitations. One thing that we probably could have done better in Cilium would be, well, if we don't attach the BPF programs inside the pod, one other option could be that we attach it to the physical device on the TC egress hook. Because that's where then all the traffic that is going out would be enforced. And instead of the L3, L3S default mode, we could have used L3 on L3S private mode, which means that there's no cross traffic between IP VLAN 0 and IP VLAN 1 device. All the traffic basically somehow has to be forced out of the pod. So then basically the idea was to attach or like to have like a large tail call map for the BPF programs that you would have on the TC egress hook. But actually one problem with that is in the case of Cilium, we have enforcement that when a pod sends out traffic, the BPF program that is attached on that container is checking the source IP address. And if there's traffic that it has not the expected source IP address, we will drop that in order to prevent spoofing. And I think that's quite, I'm not sure whether that's actually possible to do here in this case, because like the IP VLAN internal code will basically look at the destination where traffic has to be routed, and then it will just route it out. But then you don't have a concrete attachment point where you can be sure that the source came from that particular pod. So you would have to look at the tuple. Yeah. And one thing I haven't really tried, but like if you would want to be able to support multiple physical devices, which is the case that a lot of Cilium users have, dual port or even more, then I believe, I'm not too familiar with IP VLAN in that context, but I believe one thing you would have to do, please correct me if I'm wrong, is that you would have to attach this to a dummy device or like make a dummy device the master device and redirect the traffic there into the pods. So yeah, anyway, how does this all compare together? So we have Weave devices, IP VLAN, and Netkit devices. The Weave device operating in L2 mode, IP VLAN and Netkit both L3. Then Weave devices come in a pair. The IP VLAN one, as I just described, it has like one physical master device and then different slave devices that are attached to this master device. And the Netkit also comes in a pair. I think this model of having like pair devices is quite nice and flexible. BPF programming, so for the Weave and IP VLAN case, we basically have the TC, TCX, where you have to attach BPF programs, ideally on the host, because you really don't want to have applications inside the pod messing around with that. And routing, I mean, in case of the Weave, you have the, well, it's like given it's a layer 2, it's that's basically the next hop, the default gateway that you go through, and then whatever you have inside the kernel, where you look up the kernel FIP, either through BPF or the upper routing. in the case of IP VLAN, it basically has this internal FIB so that it knows if the destination of the packet is like one of the IP VLAN slave devices, and if it matches the addresses, it will forward them there. And if that's not the case, so if that lookup fails, it will basically fall back to the kernel FIB and then do the routing through for packets that are going out of the node. And in the case of the NetKit device, it's optional what you do. I mean, you can utilize the BPF FIB lookup from the kernel side to get all the addresses you need. So yeah, problems. So in case of the Weave device, I will show this later on some benchmarks. So like there's still this overhead there where you have the per CPU backlog queue that you need to go through. You need neighboring resolution. Like in Cilium, we had an ugly hack where we basically have an ARP responder in BPF to force the traffic out to keep it simple. And there's also this XTP mode where I'm not quite sure, like, I mean, it's useful for debugging and testing, still hard to use. You need to have XTP attached on both devices. And I'm not quite sure, I mean, yeah, up to the use case, I think, where people need it. And then with the IP VLAN, what we basically found were those inflexibilities I described earlier. On the NetKit, there are still some to-dos that I will go into later to elaborate more on that. If you look at flame graphs in terms of the backlog queue, so really in the worst case that can happen with the Weave device, you defer to the case of the AQ daemon, so basically it enqueues and then at some point it picks it back up to process it further. And with the NetKit device, the idea is really simple. Given you do the FIB lookup from the pod, from the pod's peer device with BPF, you can say, okay, if this traffic is destined to be routed out, you can directly forward it. So it will also help in terms of better accounting for the scheduler. In terms of performance, so looking at the TCP single stream performance, we are basically on par with the host. And the same if you look at the latency, so P99 latency here for the request response type workloads, it's also on par. Ongoing work. So obviously, some low-hanging fruit, IPROT2 support, patch has been sent out, and I think there's some 1 or 2 more revisions needed. But the basic idea here with the IPROT2 is you set up the devices, you also get the information back how it was configured. That the BPF attachment itself, that's out of scope. That is basically for the application using libbpf or using the eBPF Go library. And the other plan that I have is to basically add support for the Go-based netlink library. So that one here is very popular and the most frequently used, I believe, so that it will also support the device creation, which we need for the Cilium CNI plugin because it's written in Go. The next one is fixing networking statistics for NetKit. So that hasn't initially been implemented. Patches are now out on the mailing list. And also helping to fix the peer redirection statistics, because one thing that ByteDance folks reported was basically they were running cAdvisor, which is a project from Google to basically gather all the statistics from the devices and export it somewhere for visibility. And that was not implemented with the peer redirection. Jacob suggested to move that allocation of the stats into the core, which is now the case. And we basically have NetKit and also Weave devices both use the T-stats. T-stats are basically there for RX and TX statistics for packets and bytes, so that this can be allocated there, and then the devices will do their thing. And the SKB do redirect will basically bump the RX stats on the peer device inside the pod. The next thing after that I will be looking into is there was a suggestion also from Jacob to basically add just a pointer into the main net device structure of the kernel for peer devices. it will help to basically, I mean, it would basically, right now, both Weave and Netkit, they have this in their private data structure, and moving it out of this in general would help with removing the indirect call. Like on the SKB do redirect peer, there's an indirect call that we have, and as a quick fix, I've been using the indirect call macro, but that is limited when the device is only built in, but otherwise, if it's a module, you cannot really use it. So that's one limitation that moving this peer device into the net device structure would overcome. And the other thing, I don't have data on it yet. I implemented it before LPC, but I will do performance testing afterwards. But one thing that is interesting, what I saw from some of the OVS work, I think that Paolo did some time ago, is that when you add a VXLAN device or like some other tunnel device into the OVS bridge, it will basically also adjust the needed headroom for all the attached port devices onto that, so that you can potentially avoid some reallocation. Given VXLAN and Geneve, they need more headroom than your default direct routing. And similarly, also needed tail room. That is actually the case for WireGuard. It has non-zero tail room because it adds some padding at the end. So if the performance numbers look good, I was thinking to maybe have actually in the RT link 2 new attributes, so you can actually also dump it for the devices to introspect how much they need, and you would also be able to set it. So that the idea is basically we would set it from the primary device, and it will basically adjust this also for the peer device. So internally, it will see which of the 2 devices needs the max headroom or tail room, and then it will propagate this and set this on both. And from the mailing list, like some of the old patches, they mentioned like a performance improvement from 5%. So I think it looks promising to set up performance benchmarking and look into what effect it has today. Okay, fair enough. Okay, I will hurry up. The next one, I was thinking a new NDO for doing something very similar for the big TCP, so that you can set the GSO max sizes for IPv6 and IPv4. The idea here would be also that for big TCP users that would want to enable this on a running cluster, they don't have to restart pods, because right now it cannot be configured for both devices, right? So right now it's just on a per device basis, and Cilium cannot really go into the pod network namespace. So with that limitation, this could be overcome. Then there are some small difference in the redirect peer handling. So for the Weave devices, if you would have like a local pod-to-pod communication, the idea is basically on the Weave to use the redirect peer also for the if you want to have traffic going to the other pod, so you only have like a single time where you go to the per CPU backlog queue. And for the Netkit, it's slightly different. It's maybe more like of a documentation awareness thing, but I will also look into whether something else could be done with that. Some other future work. I would actually love to get Jacob's opinion on that. Yeah. So looking into the BPF FIP lookup for IPv6 in particular, because IPv6 can be built as a module. The problem there is we have, in the really worst case, 4 indirect calls in that single helper. So that's really insane. In the regular case, I think it should probably be more like 2 indirect calls, but that's something we can improve performance-wise. And maybe the idea is like to just have IPv6 going from the tri-state to like the Boolean, so it is always being built in for the majority of users. And then we can get rid of the indirect calls, which would be nice. Then, okay, I'm soon out of time. Where am I? Then one more thing is like the improvements around TCP dump debugging. That's on the to-do list. Reorganizing the NDOs. It's kind of like semi-related, but Coco from Google, he started some work to have like the fast path fields in the core networking data structures better grouped so that you can reduce the cache line access to that. And I think it would be nice, the next logical step, I think, would be to also do the same for the net device ops. Single device mode. This could be something further out in the future. I was thinking the BPF def map could potentially be used for that, so that there's like a pointer to the device inside the pod, and then you can get rid of having one device in the host namespace. Yeah, that's something further out. And then indirect calls, getting rid of indirect calls in the BPF mproc when we execute the BPF programs. That would also be useful for XTP itself, once we would be able to support multiple XTP programs. So we need to look into the BPF dispatcher to be able to support that. And yeah, that's like the complete picture, how it looks. And with that, I'm done. Okay, then we take it to the hallway. That's fine as well. Thank you. John, can you hear us? You're now presenter.
Okay, great. And I have buttons to move the screen, so I think I'm set. Can you guys hear me?
Yeah, we can hear you.
Okay. Even probably do this. Hello. Great. So my name is John. I'll just get going because looks like we're right on time. Yeah. So unfortunately, I was not able to make it. I had something pop up last minute, so apologize. I was really looking forward to see everybody, but I'm happy to talk virtually today. So let's get going. I'm going to talk about application network security in an encrypted future. So this is a problem we're starting to see. It's not something we see every day yet, but I think it's going to become more and more prevalent. So as a quick agenda, first I'll talk about Tetragon. Tetragon is our security tool that I work on, where we're starting to kind of see this problem and we're looking for a solution. We'll show you kind of like what we do with L7 today as far as parsers go and how it works. And then talk about a little bit about why it can break in some scenarios. And then, how we solve it with BPF and so on. All right, so let's get started. So what is Tetragon? A little bit about that. No, I've talked about it a few places, other places. I don't think I've talked about it at LPC before. So Tetragon is a security, observability, and runtime enforcement. This is kind of important because it impacts our kind of viewpoint of the world, kind of especially when we talk about trust domains and stuff in a couple more slides. But the gist is it does all of the BPF filtering and enforcement in the kernel. This is really driven by we need CPU, we need memory, and we need correctness. So the users are really watching CPU and memory usage. So any sort of bumps in CPU or memory usage almost always ends up with a bug. In my inbox, usually a high priority bug because they've just upgraded a cluster and now they see a 5% boost in CPU, which means that I get to work on solving that problem kind of as quickly as possible or roll back their deployment. So a lot of that means that we do as much as possible in the BPF kernel. This avoids sending events to user space over the perf ring, for example, which would wake up user space, cause more CPU processing, and so on. And then as part of that, we move as much state into the kernel as possible. So we have an exec tree, a kind of a mirror of everything that's been executed. We have a whole bunch of socket maps, so we can map sockets to their processes. So if anywhere in the kernel you get a socket hook or a function with a socket, you can then find the process, even if there's no current pointer to the task, for example. We also move all of the Kubernetes metadata into the kernel. So the kernel has a notion of what a pod is. And if you don't too familiar with Kubernetes, a pod is really a network namespace, some C groups and these kinds of things. But there's also a concept of labels and namespaces in Kubernetes, which is like an abstraction of that. A group of pods can be in a namespace. Certain pods can have arbitrary labels. We teach the kernel all of these things so that in the kernel, we can filter events based on pods, labels, and namespaces, or we can enforce certain things based on those as well. You can imagine only certain system calls are allowed by certain pods, or only certain system calls are allowed in namespaces. And a lot of times when you construct a Kubernetes environment, you'll have kind of higher privileged namespaces. Usually kube system is one of them. This is like where you put all your system utilities. Then you might have like one for Tetragon itself, which is its security domain. Then you might have a bunch for different users and different types of users. So by pushing all this in, the kernel, along with all the state that we maintain about sockets and files and exec trace executables, we can then really, really bring down this kernel to user space chatter, which then brings down the CPU overhead. And I think that was a theme that was also brought up yesterday in Meta's discussion, right? We really want to push everything into the kernel. There's also a correctness reasons to do this. You want to make sure that if you require annotations from user space, it can become racy if you're not very, very careful. You also, the next kind of bullet here is we also do a lot of hooks inside the kernel, not just on the system calls. This is primarily to avoid talk-tau kind of issues, where you might want to filter, for example, on a socket address. If you're looking at a connect event, you might want to only allow certain types of connects, for example, connect to certain IP addresses and so on. But that's a user pointer in the syscall, so you can't rely on that, or you're going to race with user space. And again, that goes back to us being a security tool. And so our kind of trust domain, which I'll point out later, doesn't include the user. We can't trust their input. And then the last piece here, a bullet that I think kind of makes it distinctive, is we do all the enforcement in line. There are some BPF-based tooling that, for example, will push the event to user space and then generate an alert and then maybe stop the process or stop the pod, which is kind of a good first step. But the problem with that is that the action's already happened, right? And so we do this through multiple different ways. We use the override to override certain return codes. We often send signals to the application to kill them. And we also use LSMs as well when they're available. So that's kind of the high level overview. I'll show you a couple of things that we can produce with this that we use for it. Kind of from a visibility side, here's kind of a laundry list of things that people are using Tetragon today for. For this kind of talk, the really interesting ones are the last two here, L7 parsing and DNS, HTTP, and TLS. That's what we're going to focus on, but you can also see we can do kind of process execution, which we also support digest and SHA-256 over those through IMA and FS-Verity. But also these kind of other things, namespace changes, privileges, capabilities, CVE mitigation. So there's some ways, if you know a CVE and kind of know the pattern, you can kind of implement a policy that would block that pattern. But like I said, let's talk about the networking side of things, because that's the most interesting for today. And then what we do once we collect all this networking information is we usually push this up either to into cold storage, into a SIM, or into application, some of our UI application stuff that Isovalent has. This is just an example of one visualization that we have. So on the left, you can see we have an exec trace. In this case, node server.js is the kind of the first thing. It's coming from a pod that's called crawler. And you can see the container runtime stuff as you go higher. And eventually you get to a init, which is the kind of thing that starts all this thing. But basically what we're seeing is all the binaries that are executed inside a pod in kind of a tree form. on the left. And then on the right, we have all of their, what they connect to. And you see we get DNS names because we have a DNS parser, and we get ports and TCP information. The DNS names come from that DNS parser as well. And you can't see it here because it's a static picture, but if you kind of zoomed in on these right boxes, you could also see kind of the HTTP requests, what was sent, if it was a GET or a POST or whatever. The idea here is that security operators or platform operators can look at this and they can see things that they don't expect, like a malicious bucket here is our sort of canary that we are highlighting. We don't expect this connection, so that's a problem. But there's also an interesting piece where sort of just basic networking wouldn't solve the problem, where you see a malicious user talking to something like Elastic Tenant jobs here. So this looks like it's an okay connection because the node server is allowed to talk to it. So if you're a system that's running kind of as a middle box in the network, or OVS or something in the networking side, you wouldn't really be able to distinguish these two connections, this one from the good node server.js, and then perhaps one from curl, which you may not expect, right? These are two different binaries, both connecting to a valid source. So that's the advantage of digging deeper into the system beyond just pure networking and tying it back all the way back to the binaries, not just the source IPs, for example. So another example is then, because I want to talk about HTTP a little bit in a second, the other thing we can do kind of at Isovalent when we work with Tetragon data is we can generate dashboards of HTTP events. This is generated from StockMap, basically. It's a pair of programmers and parsers, and I'll walk through that flow in a second, how that actually works. But you can see we parse the data. We can generate pretty graphs with latency metrics. This is a latency graph right here, and also return code. So you can see I got a bunch of 200s or a bunch of 503s you might want to investigate. Or if you see a high P99 latency here on the bottom left middle kind of, you might want to go and take a look. So these are some things we can do with the data. But we have to also do file access, but I'll skip through that slide in the interest of time. So those are some things we do with the data. Then I want to talk briefly about the trust model that we employ, because it's going to become relevant in just a second. This is a sketch that I put together of kind of a typical Kubernetes model. And in Kubernetes, we have these pods. From the kernel side, you can just imagine these are network namespaces and C groups, kind of capabilities, user namespaces, all kind of grouped together in a series of applications and containers. So we usually connect, there's usually a local networking running there, IP tables, a net device, maybe netkit if you followed the last talk. And then on the host, we have another net device. I kind of went with the vEth model here. It's the most standard at the moment, at least that we see on kind of 510, 515 kernels. And then you kind of have a net device out of the system. All right, so this is kind of a basic, straightforward model. Like, we can make it more complex if we wanted to, but it serves our purpose for this. So then we want to talk about, like, what does our trust boundary look like? And where can we hook into the kernel to get our data? So you could conceivably build a library to hook into the data, like an HTTP library that everyone uses to send their data. You could hook into that and put your observability hooks there. Unfortunately for us, that's not going to work from a security standpoint because we don't trust these containers. We're taking the approach that we're on the security team side. We don't want to trust the pod or the container, and it's also the application, which also rules out uprobes, which is unfortunate because uprobes would be nice because you could hook your HTTP library, your Golang libraries, OpenSSL, and so on, and get data directly from those before the encryption, or before they send. Unfortunately, again, uprobes aren't very secure from that side because it requires the user to run the library that we're instrumenting. It requires the user not to modify the data after the hook, and these kinds of concerns. Sometimes people put a sidecar inside the pod. Basically, this would be Envoy or Nginx or any of these kind of proxies. We choose not to for two reasons. One, from a Tetragon side, it means we'd have to somehow get into this application and add a sidecar. We'd have to be part of the pod spec, part of the deployment model. Not something we necessarily want to get into. Also, it means that this group of things cannot manipulate the networking inside their pod. This is a network namespace, like I mentioned, and we just don't want to enforce that this containers over here don't have CapNet for some reason, or somehow escape and get network ability to redirect traffic through the IP table. So kind of take a step back and say, all right, let's just not trust this entire pod thing. It's a nice logical unit in Kubernetes to draw your boundaries around. So given that, then the next question is where should we hook for Tetragon to get networking data, especially application data at the L7 layer? Think DNS, HTTP, TLS handshakes, Kafka traffic, these kinds of things that users of Tetragon want visibility into. Sorry, I jumped ahead there a little bit too quick. And so where we chose is this L7 sock map, sock ops. And the advantage there is that that's going to hook on the socket directly when the container or application sends the data, but it's not going to be manipulated by the pod itself. There's not a hook or a method that the kind of a standard way for that application to detect that it's been attached to a sock map, where we're going to start running our BPF programs on their data. And there's no way for it to definitely no way to detach from it on that side, unless it has cap BPF and has access to the BPF file system. Another viable option is this host proxy. If we could route traffic through the host, the problem with that for Tetragon is it requires a CNI, requires you to be in the networking routing table. In Kubernetes, that would be the CNI. That's the sort of object that manages networking. But for other systems, it's the same principle. We don't necessarily believe that the security team is the same team as the networking team. And so we just want to reduce friction. So that's where we come to the sock ops, sock map thing. Usually people call it sock map as a shorthand. It's actually a series of different hooks to build the system up. And so let's walk through what that looks like today. So if you look at how we do this, kind of today, like I said, application is going to open a file descriptor. It's going to do it with a connect, most likely. When the connect happens, we have a sock ops hook in the kernel that checks the state transition. And then the important thing is we look at if it's transitioning into an active established or a passive established state, and it's a kind of one of these families we care about. We run logic over that to see if we want to hook a parser to it. That logic, again, you go back to those labels, namespaces, pods, kind of information from the metadata of Kubernetes, or it can be as simple as like, if it's port 443, I want a TLS parser. If it's port 80, I want an HTTP parser. And in practice, so that actually is what happens a lot of the times. The most common reason not to have it quite so simple is to do staged kind of rollouts. You may not want to all of a sudden start parsing every port 80 traffic in your network. Maybe you only want to parse traffic outside of your cluster or outside of some kind of safe domain, IP addresses that you don't own, perhaps. So that's the first step. And then after that happens, we connect it to one of our parsers. Like I said, those parsers are sock maps or sock hash objects, so they're just BPF maps. It's a BPF map update with the sock as the value, basically. Because it's a hash, we typically use the file descriptor as the hash plus some extra data in case it's a UDP socket, although we haven't fully enabled UDP yet for Tetragon through sock map, to be honest. And so each one of those has a BPF program attached to them. One is a message program to parse data that's sent, and one is a verdict program to parse data that's received. And basically what those get is the input of those programs is a scatter gather list of the data that's being sent. So then finally the application will send some data, and then we'll get our hook called. And there's some important properties of the hook. The data that we're reading is not in user space. Again, for time of check to time of use. We don't want to like run our security algorithm over the data, all of a sudden find that the user is changing it as we're trying to check it. There's a bunch of helpers here that you can drop the traffic if you want, redirect, cork. Cork allows you to collect a bunch of data. We made the decision very early on that all of our parsers would be streaming parsers for performance reasons. It makes writing the parsers harder, but it gives you a performance boost because you're never blocking data. And then on the reverse, on the receive side, the hook is just before the application receives the data. It's on top of the TCP stack. This is necessary because of retransmits, out of order data. You really don't, I don't think you want to try to write a TCP stack that handles retransmits and out of order in BPF programs. So the sock map hooks, in this case, the verdict program, is after all of that logic from the TCP stack. So you can ensure that what you see is the actual data that's going to end up in the application, not sort of artifacts of the underlying protocol. So then that's our sort of infrastructure for doing this. Then the problem is what happens when the data is like HTTPS or encrypted. We still want to have be able to observe the data and enforce our policies. Unfortunately, it's been encrypted, right? And so the problem is you don't actually see the data anymore. All you see is what's in the TLS payload. The use cases for this are, here's some high-level motivation slides, but I mean, the real gist, I think you can imagine, is you have an attacker in your network, and they're going to try to send data out to some bucket, an S3 bucket, or some account that you have that you normally would allow from the platform, but because it's an attacker, you want to look at the data, and maybe it's if it's encrypted, you might not be able to tell that it's not a valid token or not a valid bucket that you actually own. It might be an attacker-owned bucket, for example, if you're going to cold storage. Or vice versa, if they're pulling from it, you want to make sure that maybe it's a valid bucket for all the known folks to be pulling from, but not a valid bucket for your attacker to be pulling from. Right? In that case, you want to be able to look into the payload or the headers and find that token and find that bucket or URI or whatever the kind of significant thing is that you want to detect. But again, trouble is this works really well, but in general, when it's not encrypted, we can use all of our programs to map to this. But as soon as it's encrypted, now we have this this problematic thing going on here where we're just seeing encrypted TLS data. And so this is just another dashboard we provide that we would like to work in TLS. The idea is based on tokens, you can show how much data is being sent or received. This kind of notion of a token is relatively common. Another thing that we'd like to keep working even in encrypted is to be able to inspect the payload, where we look for kind of maybe compliance reasons that no credit card number should exist on the wire, these types of things. So you can scan the payload data. This is sort of relevant because it means that we also want to be able to look at the payload, not just the headers from a plain text before it's encrypted. The other thing we do is the TLS handshake. This will become relevant in just a second. Basically, we parse the TLS handshake. It works for TLS 1.2. We get SNI names. TLS 1.3 encrypts the cert, so we lose the cert in TLS 1.3. But there's that. So we have all those dashboards, and we sort of understand that we want to look inside of this encrypted data to solve the use cases that we're solving without encryption. But with encryption, basically what happens when we see users turn on encryption all of a sudden is all of their dashboards report 0, and they no longer have visibility into anything, right? And basically they drop back into L3, L4 visibility. So you can see the network connections, but you can't see the data. So how do we solve this problem in roughly 5 minutes? Is first of all, we can tell you not to encrypt, but that's not viable. You're going to be sending traffic to kind of outside of your own network for starters into the internet. You really don't want to have unencrypted bucket traffic out there in the world, so not an option. Some platforms go with the uprobes. It's very convenient. You'll be tempted to try this. You can, like I said, hook OpenSSL with a uprobe and get the data before it's encrypted. Unfortunately for us, as a sort of, again, security tool, like I said, this model doesn't work very well because we have to trust the user. And if our user is an attacker, there's no reason not to believe that they'll just manipulate the data after the uprobe. Or maybe not even use OpenSSL. Maybe they're just going to send the data directly somehow. So that gives us two options that we know of. TLS termination is what we can do with Cilium today, and KTLS and BPF is what I'm talking about from Tetragon's side, our security tool. Just as a quick note on how the TLS termination works. I won't go into it in too much detail, but the basic idea is the curl or whatever the application is initiates TLS normally, but you've injected a certificate into that chain. And so it's using a certificate and sending the data to your proxy, whether that's Envoy or Nginx, like I said, or kind of any, maybe it's a custom proxy that you built. Anyways, it gets there. You can then decrypt it because you injected a cert into that application certificate chain. You can observe the data, then you re-encrypt it with the correct data. This works, and we have to use this today. That's a picture. You can go back and look at it later. But the drawbacks about kind of around this are, one, it requires multiple encrypts and decrypts. So you're encrypting, decrypting, viewing the data, then encrypting it again. So in both directions, you're adding more operations. From our side at Tetra, working on a security tool, we don't necessarily own the networking. So there's a problem about routing integration. Like, how do we get the CNI? The CNI, again, is the component for Kubernetes that does networking. But the problem is really, how do we get the data where we want it? Certificate injection means you're managing certificates, and you need a way to do that. You also need to know what certificates to inject. So you need to know where your applications are going to send packets to, and that's usually by DNS name. So you would need to know all of the endpoints that every application in your network is going to send data. And this can be done, but it's an extra complication. And if you have a rather large network, you can imagine this can get complex rather quickly. And then the last piece, it just requires DNS parser integration usually to make all those kind of pieces work together nicely.
Hey, John, time check, 3 minutes.
Yeah.
3 minutes.
3 minutes. What's up? Or just giving me the 3-minute warning. Yeah, so what we chose to do is use KTLS. The difference in the KTLS flow, this is basically the same thing. The only major difference is we go from a TLS parser initially to an HTTP parser. So we parse the TLS handshake, and then we transition to the HTTP parser. How we do this is we also monitor the set socket options to see if KTLS is turned on. And I hope I mentioned it earlier, KTLS is the TLS offload that pushes the data path of the encryption down into the kernel so that the handshake is just in user space, and then the actual encryption happens in kernel. The reason we like that is because now when you do the send, we get the plain text in the kernel. We do the encryption after the BPF hook. And this way we keep all of our observability and dashboards working really great. I don't think I can do a demo because I don't have any idea how to switch to my laptop from here. So I just stuck it here. Basically, this is we have a gRPC hook for Tetragon. This is hooking up a CLI to it. It just pretty prints the events. And what you can see is I did a curl to eBPF.io/Tetragon. It does a connect. We get all of the DNS info from the DNS parsers, along with the application that's doing it. You get some socket data. This gives you some stats about those UDP connections. The close. Finally, the connect for the TCP. We get the TLS information from our TLS parser, which tells us that it's 1.3 and AES and GCM and all this good stuff. It then transitions to the HTTP parser, where we get the kind of the data on the URI and the method get and Tetragon here. Finally, it's closed and the exit. So that the really kind of critical pieces are the DNS, the TLS, and the HTTP parsers here. All right, I'm over time, so I'll do a really quick slide here. Sometimes people like go, wait a second, this doesn't, like BPF can't do this. I suspect there's not like a lot of controversy in this room. Last week I was at a conference and there was more controversy about what BPF could do. I think a lot of that stems from folks having a kind of a 5-year delay on their BPF kind of world, like what BPF can actually do. But you know, a lot of it is, well, you have bounded loops, you must terminate, you can't do a parser without bounded loops. The feedback on that is, well, I don't know of any parsers that want to run forever. If you look at all of your parsers, usually they're bounded because, well, you don't want a malicious packet to cause you to loop forever and consume CPUs. So that's not really a problem for us. And then there's always this question of like, is the header limits too small? Can you get enough, you know, parse enough data? We're roughly in the ballpark of what Apache does at the moment. There's not too many problems now that we have function calls, now that we have kind of bounded loops, we haven't hit a whole lot of problems. We've not even had to use BPF loop up to this point. We just open coded everything and it seems to work fine. Sometimes we hit this error, the sequence of 8193 jumps is too complex if we get too many jumps. But you know, so far it's been without much trouble. We've done a fairly good job. And then I'll skip through the last, since I am over time. The kind of next things that we're working on are trying to get some of our testing available for folks. We have a fairly significant testing for SOCMAP internally, for at least for TCP. We do a lot of the compliance tests that are required for Nginx and Apache, and they're all passing now on the latest LTS kernels and BPF Next. Unfortunately, we just do that for a very specific TCP configuration. So that's one thing. The benchmarks are looking pretty good, but I hesitated to put them in here until somebody reviewed them, just because I didn't want to claim something that was too good to be true. On KTLS, if you're interested in this, come find me or email me, ping me on Slack or something. I need folks to add more KTLS support to Golang, Java, Python, Boring TLS, and so on. More testing on all the versions. So if this sounds like fun, come track me down. And we're always building better parsers. I want a regex parser, but that's not there yet. And that's it. So with that, I will say thanks. Glad to talk to you guys. And if you want, I think because we're out of time, if you want to put something in the chat box, I'll definitely respond to it there. So thank you.
Yeah. Thank you, John. Let's
Sorry, I
use the
rushed
chat
through
for the
there.
Hello. Yeah, good afternoon, everyone. Today I'm going to share, talk about like how do we use eBPF programs in our network to accomplish our goals of safely sharing the network at Meta. So I'm Bala. I am Balasuran Madhavan. I'll be presenting today along with Prankor, who is virtually sharing the, virtually be joining us. Okay, the overview of the talk, we are going to cover a few things in detail. The first thing that we want to talk about is what is the most common problem that we observe in the network and what do we want to try to solve, right? And this is in terms of data center networking space. So you can imagine short RTT flows and what is it that you want to try to solve. And I'll be sharing one solution that has been effective for us in our fleet. And I'll quickly also go through a bunch of other tunings that we have done using eBPF that has helped us to, let's say, safely share the DC resources, as well as, let's say, help service teams expect better performance on the network. I'll also go through how we use the structops hook point to design our own congestion control algorithm, and I'll also go in little bit into like why do we need to do that. And finally, we'll also be covering on how we actually manage all these BPF features at scale, and like by both leveraging us to, let's say, experiment quickly, as well as, let's say, roll out these features at scale, and then still be able to manage. Who we are, okay. So the work that I'm sharing here today is as a collective effort by a few teams at Meta, mostly teams at host networking, network analytics, and kernel. A partner in basically building things, and then building monitoring, and so on. Okay, so the major problem, if you want to have, if you look at a data center network or a host in a data center, is microburst, right? And I have a capture here that shows us a typical a microburst on a host level, right? So if you look at I think it's clear. So if you look at this, the time scale of this entire burst, or the time scale of this entire chart, is actually just 20 milliseconds, right? And the few things that we have captured here or highlighted here is what accompanies a burst, and or what happens when a burst is occurred, right? So if you look at the first few milliseconds, the first 6 to 7 milliseconds, the link is pretty much idle, right? It doesn't have any traffic, the host is idle, and then you see a sudden burst, the blue line that marks the ingress rate of the traffic up to the next capability. So you could see that within a couple of milliseconds, the ingress rate on the host quickly moved from 0% to close to 100%. Right, and this is possible because the RTTs for intra-region flows are going to be like in close to 100 microseconds or less. So in 2 milliseconds, you have the potential to actually fill up the line rate, right? And if you see, this is sustained for like 10 to 12 milliseconds, and then it starts ramping down as the service has transferred the data. Right. A few things that are also happening along with this is you could see the ECN signals to kick in immediately, and then it tries to pretty much at the line rate as well, tries to slow things down, and and then third is the pink line. I'll come to the green line later, but the pink line, that's the unfortunate event of packet discards. Right. So this clearly shows that the packet loss in the data center happens not just because of a complete 90% utilization of the link, but these kind of bursts that triggers queuing on the downlink rack switches as well as on the receiver or host, leading to drops. Right. So the last line, that is a green line, is basically the number of connection. So the reason we want to highlight this here is this kind of gives us a clue as to like what is causing this kind of a microburst. How can a microburst happen, right? And this helps us to root cause why this could happen and how we could solve it, right? Okay, so just to continue on to the number of connection count that we saw. So this is this is a typical pattern that we can expect from services that are running in the fleet, that in the data center. It's because of the scatter gather operations that is happening, right? So an aggregator sits through, wants to come up with a specific data, like a feed or something, and then it tries to query a bunch of leaf nodes to get the data back. Right. So if you see here, what happens is the receiver is the one that's congested, but we saw that the signals that are given to the sender are pretty much like independent of what's happening on the receiver. Right. The sender is looking at the congestion window, and then it's trying to change it based on the congestion it expects. But we see that the receiver is in a much better position to quickly react to say like, hey, on an incast or a microburst case. So what did we try to deploy here is we try to use the flow control knob in TCP to try to tune this at the host level. We developed a TC program that runs on the TC egress, tries to intercept packets, and then tries to rewrite the receive buffer based on the incast condition or the microburst conditions. If the number of flows goes higher, we advertise a smaller window, and then quickly dynamically change based on the condition of the receiver. So we have seen this solution to be very complementary to congestion control, and it kind of also feeds into the signal of the latest receiver-driven congestion algorithm. So this kind of feeds signal from the receiver back to the sender. And what did we observe? So as we deployed this on top incasty services or even fleet-wide, we clearly observed that this solution was able to quickly mitigate a lot of discards, packet discards, leading to retransmissions. And also eventually we also saw like a reduction because of the reduction in the packets in flight. We also observed the buffer utilization to go down, as well as the RTTs. Right. Okay. So I want to quickly highlight the need for BPF here. Right. So yes, flow control knob is a TCP kernel feature. Why can't we just use it using a set sock op? Right. So if you the key takeaway from this slide is trying to change a specific field within the kernel to what value you want is a challenge in itself, right? The things that we bumped into when we tried to do the same TC program in a set sock opt is like things like, which callback do you want to do it? Do you want to do it on the client side, on the active callback, or do you want to do it on the passive callback as well? If it's in the case of a server, it's a listening socket. How do you know which flow do you want to set this value to? Because you need to set it to specific servers, a different value for different servers, right? So, and also there are other features that kind of decides this receiver window, right? Like there are features like the moderate receive buffer, which the kernel does a lot of dynamic intelligent stuff to adapt your receive buffers based on the receive windows based on the receive buffers, right? So you don't want to go tune your receive buffer just because you want to tune your receive windows. So implementing this using the TC program was pretty independent of the other tunings that were already been done by the kernel and helped us. Okay, now taking a step back here, right? So I had shared one common problem that we observed in the data center space, and how did we solve it from a receiver-driven signal. Here, this chart shares a few more tunings in a similar field. Like the first one, I'll highlight a couple here, and then I'll leave it in the rest for the slide. But if you look at long distance flows, right, the major thing that is causing an impact for services as well as the network are basically the large BDPs because of the larger RTTs, leading to large burst sizes, right? And we have observed pacing and using max pacing rate or limiting the max pacing rate for flows have led to significant reduction for cross-region drops, which are pretty expensive because the RTTs are now in the range of milliseconds, right? So once we tune this, we have observed improvements for service latencies for the P95s or P99s to go down by 2x or even more. A few other things, again, for long RTT, just to complete it, we have seen initial congestion window tuning to have helped with, again, services to optimize their cross-region query latencies. We have observed in order to just improve reliability, right? Like we have seen tuning the connection timeouts to values that are based on the scope. Like let's, for example, if it's a short RT or it's in a DC flow, we would want the connection timeout to be much more realistic to the value that you expect, rather than wait for a second for you to retransmit, right? And finally, the CC selector, I'll go over this in with more detail. Okay, now jumping from network tunings to congestion control, right? So before diving deep into congestion control space, I want to first highlight what are the key aspects that kind of motivates us to, let's say, customize a congestion control. And this is what the questions here are the answers that we need to that answers these questions are going to help us say why do we need struct-ops, right? So like things like, do you want your congestion control to add more signals, right? Do you want to add a delay signal? Do you want to supplement ECN signals with other kind of signals to, let's say, to make your congestion prediction better, right? Similarly, do you want to improve your existing algorithm, right? Like you might have a really good congestion control that might be working really well, but there might be a new traffic pattern that comes up in your network that you would want to handle, right? And then maybe you want to say, hey, I want to change the algorithm to handle this transient burst much better, right? So do you really want to monitor your congestion control, right? Like at a flow level, do you have the visibility of, oh, if it's DC-TCP, what's the alpha, what is the current event, right? Like, do you want monitoring visibility that you cannot get if you're running a base version, right? So these are like few of the key reasons that we started thinking about, and BPF struct-ops was the direct way to get up all these benefits as we built our new congestion control algorithm. Okay. Finally, I'm going to share a bit of a detail here. I'm not going to go through the detailed implementation of delay-based congestion control. That's pretty much a talk on its own. What I wanted to capture here is how we at Meta build our own delay-based congestion control using struct-ops, and like what are the key or the highlights that we wanted to tackle, right? So the first thing that we observe here is we don't want a lot of queuing, which is expected out of DC-TCP. We wanted to set a specific delay, and we need to control like how much delay you can expect for an intra-region flow, right? This has been our aim, which has helped us to reduce queuing as well as like free up buffers in the network, be it rack switches, be it receive buffers, or receiver hosts, right? So what kind of signals did we look at? We looked at RTT, we looked at one-way queuing delay, just in order to make sure that we don't have reverse path congestion. We also had added support to be able to still react to ECN signals, maybe slightly differently than, let's say, what DC-TCP does today, right? So we used, I just wanted to highlight the struct-ops program that helped us to handle this. So let's say we added all our signal collection or sampling in packet stack. Adding here is basically going to give you enough sample set for you to make a decision or that predicts the congestion in the network. Similarly, you could use calls like set state and SS thresh to set state and C event events to basically determine, oh, what is the step do I have congestion driven loss? If so, how am I going to react? Or if I don't have loss, how am I going to additively increase my window, right? So again, as I said, explaining a delay-based congestion control is a pretty wide topic, but I just wanted to highlight like how we use the struct-ops callbacks to quickly implement one. With this, I'll hand it over to Prankor, who will be explaining more on the control plane part. Prankor, yeah, good.
Thank you, Bala. Hey, folks, I'm Prankor from Meta, and I will talk about eBPF control plane that we built to manage 10 plus transport tunings. Each tuning you can think has like various degrees of freedom, which can be like rollout scope, intra-region DAC, DC, rack, etc., or tunings which are applicable for like specific hosts, service, or even connection itself. The diagram below gives a brief idea on like how quickly we are able to like roll out new things with this platform and utilize its common observability and auditing capabilities across features, thus reducing mean time to productionize a feature fleet-wide. Later in the talk, we will go into like specific requirements that we needed to build to roll out our custom CCA built entirely on eBPF, and what challenges we faced and how we solved it. So first, let me double down on like why did we actually needed to build a control plane for eBPF. First and foremost would be for enabling fast experimentation at broad scale, reliably and quickly. Ability to like roll out, roll back in the order of like minutes, and also to reliably configure the right set of tunings and features at the desired granularity. Also, it gave us an opportunity to like build an infrastructure to do common operations which can be required for like a lot of tunings. For example, a lot of tunings want to know the scope of the connection, short RTT, long RTT. So the platform actually calculates it entirely and provides it for like all the tunings. It also gave us the opportunity to like uh, create an abstraction layer for all the BPF related nuances, like managing the BPF objects lifecycle, pinning all the map operations and stuff into a single library, which is provided to all the feature owners so that they can build and iterate on it like really fast. And this also helped us in like adopting a latest eBPF technology very fast. Next slide. Yeah. And now let's take an example of like what we really needed to build in our infrastructure to actually land our custom CCA. So assume you have like two hosts, a client and a server host. These both of the hosts will have two eBPF programs uh, installed. One is like a structops eBPF program that's for registering our custom CCA, and one is the SOCOPS PPF program called the CCA selector for setting the custom CCA for the connection. When the client makes a connection, it is intercepted by the SOCOPS program at two different hooks or callbacks, ECN, active and passive, depending on whether it's a server or a client. The CCSA selector, the SOCOPS program, there's a lot of computation to determine whether to set the CCA for the connection or not. An example of this computation would be like, what's the scope of the connection? So this information is fed to the SOCOPS program via a BPF map, via a scope resolver, uh, a library which is also part of the platform. And also mean like connections can also match a lot of policies, mean like they can have like a flow specific policy in case of a stacking world in which like multiple jobs are running on a host. So after doing all this computations based on like various criteria, CCA selector determines whether the connection needs a custom CCA or not. If yes, which one? How it? So the about the which one, the control plane also programs the one other app for the SOCOPS PPF program with all the information about what all custom CCA it has installed onto the host. It is a very simplified version of like what we did, but I hope it gives you an idea of like how we envisioned and built an infrastructure to deploy this PPF based CCA at scale. Okay, so let's move on to the interesting part. What did we observe while deploying the custom CCA fleet-wide? How did the following things impacted the deployment and how we dealt with them? The first one was long-lived connections. Our entire control plane is a transparent sidecar to all the services. For any new tuning or a change in an existing tuning, we need to make sure all the connections are using the latest version of the tuning. Else we will in a scenario in which like old connections will be using old version of the tuning and new connections will be using new version of the tuning. As you can see, it will result in like where operational challenges, like ability to triage issues. We also need to work on like the interoperability between various versions of tunings, especially for the CCA. And in our fleet, we identified the connection lifetime can be in order of weeks. So we
just 5-minute warning, okay?
So we also wanted to do it without impacting all the services, like restarting it, because we want to like make sure all the new connections or all the connections have the new version of the CCA. So a TCP iter was the answer we were looking for. Like the name suggests, we are only interested in the TCP connections and we want to like iterate over all the active connections onto the host. We do this iteration only once when our control plane starts, and we have collected all the data to make sure this iteration does not impact any regression onto like the CPU or the memory usage onto the host. And next slide. Okay, so how about when our control plane itself is down, maybe because of a restart, upgrade, or a crash happened? A crash of the control plane can happen at any time, or it can go down because of some other system level issues. So in the time where our control plane is down, the services will still operate and they will skip all our tunings and stuff. You can say like, okay, TCP iter can come to the rescue for this also. Yeah, kind of right, but not always. Some tunings require to use some tunings require to use the state. So some tunings depend on like some of the state of the connection which are set at like the connection start time. Example, ECN negotiation, or they are dependent on to like the user space calls of like sets of opt. If those connections are missed or events are missed, a TCP iter cannot make sure we can apply all our tunings onto those connections. In order to solve it, we decided to decouple the lifetime of our data plane with our control plane by pinning our BPF objects, maps, links, and programs. But this way, we were able to like make sure our data plane is executing at a lot higher time than our control plane. But with this solution, we did open a lot of issues or like identify a lot of things which can break. For example, when our control plane restarts, we need to update our data plane, which means we have to like detach our old BPF programs, print stuff, and load it with the new one, which also incurs some of the downtime. Of course, atomic upgrades can help us reduce or remove this downtime, but atomic upgrades are not available for all the hook points which we use. Another point was like, okay, now I need to transfer all these state from my old maps onto the new maps. But what if after upgrading, the map structure itself changed? We need to take care of like all these cases and stuff while doing this operation. And since we are pinning maps, we also decided to share it across processes, because these a map stores some information which is relevant for like other processes also, which added more complexity in like the synchronization and access control issues and stuff. In order to solve all this, we created a BPF versioning manager, but we feel like a lot of things can be solved easily if they are natively supported by the kernel. I think that would be all from my side. Thank you.
Thank you. Any questions?
Are you planning to open this work up, maybe research paper or open source it?
Yes, so we are working on, I don't know which work you're expecting, but
congestion control.
Congestion control, got it. So yes, we are collecting the data needed for the congestion control part, but we have also submitted a paper for the receiver-based tuning, as well as we have submitted a paper for the control plane, like with the details on how do we build the control plane, how to manage it. So I think yes, we will be open sourcing it soon as well.
Thank you.
All right, seems like everyone is hungry. Thank you very much for the talk, and let's gather together at 2:30. Yes, let's spend time. Oh, yeah.
You're the one who's going to talk next time.
Yeah. And then they also work out some of the.
Yeah, I got it.
Okay, I hope all of you have a great lunch. Let's get started of our afternoon session. The first one will be by Kun Fei, talking about the strut ops status and the latest update.
Thank you, Martin. My name is Gui Feng from Meta. Today I will explain a little bit about strut ops and also update what's happened in this year about startups. Also look into some use case. I won't go into details of the startups, but just give an overview. Yeah. eBPF strut ops is a way to define a set of operations that can be performed on a specific type of object in the kernel. It can potentially be used to define the behavior that are managed by the kernel, by the subsystem. Can you hear me? Okay. Such as operation of a network congestion control algorithm, you can define an algorithm and load it into a kernel to do congestion control, or maybe file system and other resource. Here is an example of a strut ops type. eBPF strut ops is a C strut type that include a set of function pointers. These function pointers can be implemented in BPF program that can be called by kernel. That means that if you define a set, to implement these function pointers and register this object, then these objects can be, and the function pointer can be called by kernel directly. For example, here we have a declared type named BPF strut ops, test mode strut ops. There's two function pointer here, test1 and the test2. Once this type is registered to BPF strut ops, then application can implement their own instance and register with the kernel. Once it's registered, just like I had mentioned, that it can be used by the kernel call to call these functions. About the details, how to implement that, we'll see that later. Then here is an example of how to define an object of this type BPF test mode ops that we just mentioned in previous page. Here we have defined the two functions, user test1 and the user test2 in BPF. These two functions need to match the signature of the function declared in the type, the function pointer we just mentioned, test1 and test2. For example, here is user test1, and this function, its signature should match the test1 defined in BPF test mode ops type. And we will assign user test1 to test1 as a function pointer. About how to, we'll mention later how to use that. Okay. Once the test mode 1 we declare in previous page, maybe go back to. here we have defined the test mode 1 here in BPF. Okay, once test mode 1 is loaded and attached, the kernel can direct call this function through the function pointers. For instance, when this line will load user test 1 and user test 2 into a kernel before loading the object. So when we load these two functions into the kernel, it will return file discrete for each programs. These file discrete represent these programs. Then the eBPF will make another copy at the right side button. This is the copy of the original one. And we'll do some replacement. Here we will replace the test 1 and the test 2. As we remember, these two are function point, but it is actually will be replaced as the file discrete return from the kernel. Then we will, eBPF will create a struops map. This map have only one pair of a key value. So anyway, this copy will assign to the value of this map. Then in the kernel, it will make another copy. This copy will replace the function pointers again with the pointer to trampoline created by BPF in the kernel. So far, we have only one consumer in upstream. Is oh no, sorry. Yeah, about more details about how to implement a new struops type or how to use that pre-check this file. This a very simple implementation, a dummy implementation in the kernel. Yeah, so far there's only one consumer in upstream is doing TCP congestion control. This subsystem allow you to implement an algorithm and register it with the TCP subsystem to do congestion control. Unfortunately, we only have this consumer so far, but yeah, now we will see more use cases that are still under developing later. Okay, in this year, we have some new updates about struops. First is BPF links for struops map. Yeah, this feature is rendered earlier this year. Before we going on, we explain a little bit about struops map. Just like I have mentioned, every StarOps map actually have only one, at the most one key value pair. The value part is the content of the body of the objects. For example, here we have test mode 1. We have implemented in previous pages, and that is in type of a BPF test mode. Okay, then there's the whole. This whole value is the one created by eBPF by replace the function pointer to file descriptor we have mentioned earlier. Okay, what we want to discuss here is previously StarOps map are registered to the subsystem like TCP we mentioned before. The map is loaded all of it. The map, not the map, the object itself is registered when the map is loaded or the value is updated. That causes a problem. The instance of the object will activate until someone to delete the value of the map. That means when a program is crashed, you can imagine that if a process registers an object to the kernel, then I have mentioned the object will be deactivated when someone deletes the value. And then this process is crashed, so that means that no one can deactivate this object anymore. So what people do is to pin the map to somewhere in a BPF file system. So later, if the process is crashed and the restart, it will try to recover a handle from that path. And with that handle, it can delete the value to unregister the object, then install a new one. Here is the new way to do that. The new way is very similar to the previous old API. The major difference is here. Can you see the cursor here? No? Oh, yeah. Okay. The major difference is here. Previously is .StarOps. Now it's .StarOps.link. This will make difference. The major difference here is the new API will actually create a BPF link, but the old API is create a fake, not a real BPF link. With that link will behave just like the trace program we have in BPF. That means the object will be registered when the link is created and be unregistered or deactivated when the link is destroyed. So that the object will be deactivated when the link is gone. We have mentioned earlier, if we see the BPF trace program, when you create load and edit and detach, attach a program into the kernel, you will receive a link, the file descriptor link. Then when you program crash, then that link, if no one else is holding that link, the link will gone. Then the program also be detached. Here is the same. We register when the link is created and unregister when link is gone. So once your program crash or die, then the map will be unregistered as well. Yeah. Moreover is also support link update. That means we can update a link with another StarOps map. It provides an atomic way to register and unregister the object. That means, for example, we have mentioned the congestion control algorithm. When you register when you try to unregister an old one and register a new one to update, that means there's a gap between the registration and the registration new one. We don't want that, so we provide this feature that can provide a way for user space to update the link and to update the algorithm with the new one. The other update is StarOps types in kernel module. Now, this one is still under review. Okay, let's see how it is now. Right now, currently the definition of a registry of a StarOps type can only be done in the kernel. This file is BPF StarOps type stage is a header file. We have BPF dummy ops here and TCP congestion ops here. To add a new type, you need to edit this file, add the new type to this file, and recompile the kernel. So that means kernel module cannot define a new type because it's impossible to add a type into this file during runtime. Okay, so this prevents StarOps being used by features that implement as a kernel module. For instance, right now we have Fuse BPF are requesting this feature. They are implementing as a kernel module, but yeah, we don't support that yet. Here is the new approach. The new approach only requires you to call this function to register a new type in the init function of a module or somewhere in the module. So with this page, once this page say is landed, then you can do that in kernel module. So if you implement a new feature like the Fuse BPF, then you can use that in the module to register a new type. Here we are going to see some projects that are going to use StarOps. First one is Fuse BPF I just mentioned earlier. Okay. Fuse BPF, Fuse. I think most people know what Fuse is. Basically, it's a file system in user space, which is a software interface that allows user to create and run their own file system without changing kernel code. Earlier this year, Daniel Rosenberg have presented a Fuse BPF at LSF BPF. It introduced a new type, new StarOps type, allow Fuse T1 to install filter called by Fuse driver in the kernel. So according their number is improved performance. Here is the type that defined. For example, here we have open field pre-filter, open post filter. So this type has defined some function pointer that can be used by the BPF Fuse driver. Here is how the classic Fuse looks like. Basically, every call to the file system fields driver will forward request to the user space daemon. Then that will translate this request to the system call for the lower file systems. Then here is what Fuse BPF looks like. It now, because it defined swap ops up types, so the Fuse daemon can install filters in the object. So it's every request from the application will be handled by the filter in the kernel. And maybe some requests will forward to user daemon, but you also have a chance to translate into the call into VFS for the lower file system. So you just run that in the kernel without forwarding the request to user space. Here is some number they have, Fuse BPF have. Basically, they have improved a lot, but I don't go into the details here. The other one is SchedeX. That is a schedule, allow you to implement a schedule policy in BPF. A SchedeX program looks like this. Here also have a swap ops type. We define an object, and we assign this function point, and the point these functions are implemented in BPF. And then you just load this program into kernel and register it. Then, so you can do some scheduling policy in BPF. Okay, the benefit of using swap ops here is, when we implement a scheduler, usually it's very difficult. You need to reboot your system, recompile the kernel. This kind of stuff will take a lot of time. But with BPF swap ops, you have a chance. You just compile your BPF program and use your loader to load into kernel. And it's easy. You don't need to compile the kernel, change kernel. And also because BPF verifier will verify the program, so it's prevent it to do some stupid things. For example, to prop the memory, that kind of things. So it's safer. So it's easy to experience your new policy or algorithm. So easier to do your test. According some numbers from SchedeX, it can improve the latency or throughput of the system. In one case one example is they try to use a customized policy with SchedeX. HHVM experience a 0.25% to 1% increase in requests per second. Also, 0.5 to 1% improve in the P99 latency. BPF swap ops can be used in various situations to provide extension and the filtering in kernel. So it's checked by the verifier before being loaded into the kernel, ensure that they comply with the security and the resource limits that provide a secure and efficient environment for extending the kernel. So I encourage you, because right now we only have one consumer one user in the upstream kernel. So if have a new feature, maybe you can consider to use shops. It's a very good for very easy to extend and yeah, and do filtering in kernel. That's all. Thank you. Question? No? Okay. Thanks.
Thank you, Kunfei. Anton, we will talk about the static key next. Oops, sorry. That's the one, right?
Yes.
All yours.
Hello, I'm Anton from Isovalent, and I will talk about BPF static keys. So, static key API was added to kernel long ago, like in 2009, and it utilizes a compiler feature called AsmGo2, which lets inline assembly to jump to labels defined outside of this inline assembly region. And of course, we also need a possibility to patch code in a live system. And the original intent for this feature was to use like seldomly used features, like either debugging or optional features with zero cost. And in this talk, I will show how to use this feature from the BPF. So the static key interface in kernel is really simple. We define a key, and it should be defined during compilation. So this is where the name static comes from, probably. In this case, this key is initialized to false, which means that it is disabled by default. And we use it using a helper static branch unlikely, which means that it will be, for the most cases, disabled. So we prioritize the else branch, not the branch itself. In assembly, this looks like this. So if the key is disabled, we replace the jump by an op operation and just fall through. And yeah, it replaced by an op. So if we enable the key, we replace it by jump. It jumps to our branch and then follows to the else branch. And the goal is to use the same, basically the same API from BPF. So here we have a program which uses a static key debug key, which we define later. And let's take a look at how this should look like an assembly in BPF. So the NOP operation in BPF is just go to the next instruction. And this key is unlikely. And the key is off, so we just fall through to the default branch. If we enable this key, we replace it by jump, and it jumps. We get our print K and jump back. And of course, we also can have a likely case. It means that we want to prioritize the branch itself. And yeah, likely. And in assembly, this looks like that if the key is disabled, we do a jump. And if the key is enabled, we do not do a jump. So to summarize this, to provide this functionality to the BPF, we need to provide these helpers, which should compile to this assembly. And then we need to extend BPF API with 2 different kinds of branches. So like normal branch and inverse branch. The normal one is off when the key is off and on when the key is on. And the inverse branch is on when the key is off, and vice versa. So the solution is basically the same. We will just use AsmGo2 defined somewhere like in LibBPF, and we extend BPF API with the ability to pass a list of static branches to toggle and controls to actually toggle these branches. So this looks like this. So on the left we have this awesome go-to thing, and on the right we have the code which was compiled by using this definition. And besides compiling this code, we need to provide some additional information to be able to patch this code. And this is the following things. So we, of course, first need the set of instruction to patch. We need the jump target, to where will we jump when we patch instruction on and off. And also a third thing here is that we need to actually point to the actual static key which will be used to toggle this branch on or off. And in this case, yeah, no surprise, the static key is a map. So like static key is just a variable somewhere, and a global variable in BPF typically represented by an array of size 1. And the only difference is that we pass BPF static key flag here. So when we have this static key and we have the system go-to, we can pass this information to kernel. We do this exactly as like with the minimal amount of information we need. It's pointer to a map, it's instruction of set to patch, it's target of set where to jump, and flags, which is currently just like normal branch or inverse branch. We probably can do something else later. To load it, we just also, it's pretty simple. We just take an array of these branches and do it during program load. And of course, if we use this macros defined, like which I showed before, then libBPF will take all this information from jump section, will go to relocations to resolve the map pointers, and will construct this array and pass it to kernel. And the natural thing to toggle this key on and off is to write 0, 1 inside map, or like 0, non-zero. And what's happening when we write 1, like here we have a static key X. It is used from multiple programs. This topmost program has some static branches. 2 of them are controlled by the static key X. One of them is normal, another one is inverse. So when we write 1 to the map, the first one, normal instruction, is replaced by jump, and the inverse one is replaced by nop. And when we write 0, the opposite thing happens. We write nop to a normal instruction and jump to an inverse one. And another thing is that we only let to update maps from user space, because otherwise a program can just get a pointer to map, toggle the variable voila, and we will not see this. So we need to prevent programs from accessing static key maps as normal array maps. And I choose just to reject programs which try to use this map altogether. There was another option
to let programs to use these maps read-only. And there is currently a way to kind of do this, but it actually has different semantics. So it's probably should be called something like BPF const map because like it's not read-only. In this semantics, we only use it for frozen maps, which means that user space initializes a map and then calls map freeze, and the map from this point can be considered just as a set of constants. And this doesn't work for static key, which we toggle. And like another thing is that like normally BPF programs like are not interested in the value of the static key. They just have this branch instructions which we toggle on and off, and that's it. So if it will be needed to actually access BPF key values, BPF static key values from programs, we can add either slightly change the semantics of this BPF read-only prog flag, or to add something like different kind of pointer, const pointer to map value or something like this. But I'm not sure if it's needed at all. So next, let's look at like in just a few details how what happens to the branch when we upload it during the prog load. First, we take an array of the static instructions. Just consider one instruction, one branch. Then we translate it to map pointers from map file descriptors, and initialize the progaux used maps, which normally was empty. Then we pass it to verifier in the env used maps, which also previously was empty, but now it's not. And then after verification, verifier pushes us back. And another thing is that some instructions in BPF are patched like in the original BPF, not JITed. They're patched with a set of instructions. For example, here we take call to BPF GFIS and replace it just by dereferencing the address of GFIS. And again, like map lookups do the same. So when we do this, the program changes size. So we need to update all the branches which are affected, and it's not a big deal. So verification was actually pretty straightforward. So the jump absolute instruction in BPF from like flow point of view, it's pretty simple. It's just like an edge in graph, and we replace it by just two edges in graph. So when we go through the graph of program, we jump to two places, not one. It's just like when we execute a program, we also like first jump to the next instruction and push the state to stack. So really, it seems pretty simple. No one yet reviewed this patch, but and yeah, that's it.
How does this affect the JIT-generated code?
We need to patch JIT for every architecture to provide this functionality. I mean, the JIT generated code looks exactly as it looks in kernel. So one of the first slides, right? So the JIT code will be looking like this. We replace the nop by jump and jump by nop. The jump in BPF code and jump in JITed code, they're one by one. So they jump absolute. So it's just one by one translation.
Now, do you expect, because the other alternative is to what it's when you do the JIT generation, because with jittered code you have the option of recompiling, of retranslating. So it's a little bit kind of odd to to apply like code patching to code that has been code that's generated through a JIT, where you could benefit from where you could benefit from things like dead code and elimination and so on.
Yeah, like I mean, in my test I didn't see an example where like absolute jump will be eliminated. Like what an example of absolute jump, like J eliminated in JIT?
I mean, the most common use of static keys is you go down one branch. You go down one branch or another out of different set of codes. A diamond control flow, and it's it's very simple to just you're gonna in a JIT you just completely delete the
Yeah, but excuse me, when we JIT encode, we can keep track of the static branches. Like when we JIT in an instruction, we know the original offset of the corresponding BPF code. So we actually know if this jump is like a static key or not.
I understand, but it's you are carrying, you are carrying all the overhead of having to have both branches present and register allocation valid for them and so on and so forth. So that's why.
Yeah, but this is like what I want actually.
Okay, why? Why?
Again, like it's the same use cases as in kernel. I want to have, for example, tracing, like advanced tracing, like, I don't know, static trace points for BPF programs. Or I want to enable disable feature, which I do not use always. Like one example would be, for example, packet recorder, when we have like some non like.
But the difference here is that when you're doing in the kernel we don't have the option of retranslating the code, whereas with a JIT you do have the option of retranslating the code. How often are you expecting these to change on you?
I'm not sure if I understand the question exactly. So,
how often are you expecting the static keys to change at runtime?
it's dependent on use case, right? It can be, for example, like with packet recorder, yes, we can have a signal to record all the traffic for 1 second, for example, if we have something happening. So it can be just a runtime thing, and like alternative is to recompile the BPF program or reattach it, and this is what we do not really like to do.
So how often are you talking? Milliseconds, seconds, minutes, hours?
No, I can imagine milliseconds. For like if you have just not trace, not debug, but something trace and debug as well for some operations. I think about use cases when it is like milliseconds to seconds, and it can be hours as well. But yeah, it also for the sake of like recompiling versus static keys, it has a benefit that the verifier will not reject our program, which can happen. We have to support like multiple kernels, and we have sometimes cases when we enable something and program is rejected, everything breaks, and customers blame us, right? So if my program is already verified, then I don't have this problem. I just enable feature, disable feature, and it definitely works.
So when you have multiple BPF static branch conditions in your program, like how, like if you have multiple points in the program where you're having branch conditions on the same static key, then if you change it, will that be atomic, or you do patch one, jump one knob at a time?
Yes.
So it would be that some of them are enabled.
Good question. Like we have an alternative, right? We either can patch instruction by instruction, and either we can take a BPF program, make a copy, replace instructions, replace the program. And I think in kernel, the semantics is that we only also do it like branch by branch.
Yeah.
So both cases are possible. Probably it can be again.
If someone wants it to be atomic, then
Yeah, I
you
mean we can add a flag to do this or this.
I
So
see.
yeah, for verification, it is simpler to think that they are independent. So we just do like both jumps in every static branch.
Right.
If we say that we replace the whole program atomically, it is harder to verify because on the first encounter of the branch, we need to save the state. And then on every other occurrence of this branch in this verifier path, we need to have the same state. I mean, it's not complex, but it's
But you can do it like on the page that has been generated after JIT, right? You can just replace the x86, like the x86 code. You can generate a new one, copy it, and replace the knobs. Generate a new page and replace whatever the BPF prog is pointing to. Do something like that instead of having to go back to the verifier. Like you have a program text, right? The x86 code, and then like copy it, change all the knobs corresponding to a static.
But if we have multiple pages, I mean, a BPF program can be executed at this time, right? So
so that is why you first create a copy, then you modify it separately. Like it's not visible right now. The copy is not visible.
Yeah.
And then you use the RCU, synchronized RCU. Okay.
Mhm.
And the second question is that where have you used this, and what kind of performance improvements do you see? Like what is the
I didn't do performance benchmarks this time because so in the original static key document there is performance. And basically we just bypass one jump, right? But besides performance, which is like it is like valuable feature, of course, and we really want to have zero performance if like in case for tracing, for example. But the other benefit, as I said, is that we really don't want to recompile programs. So I want to have like the whole code available and verified, and I want to toggle features inside it.
You mean like you set the static key before the program is verified, or after that? After that, right?
What do you mean?
After it's verified.
So the static key is a map, and it can be used from different programs. In case for tracing, for example, I want to use the same key from different programs, so enable or disable the trace at the same time.
I see.
And when you load them, it just uses the same procedure as if we update the map. So it goes to map, takes mutex, and updates its value, and that's it. So in the original API, we have define static key true, define static key false, and in BPF semantics, it's just value of map. We create a map, we assign it 0, 1, and then we load programs, and they just pick this value.
So you can have multiple programs which use a static key, share a static key map.
Yes.
I see. Okay, thanks.
Why do you even need all this infrastructure? Can you do this automatically for like if you have an array map and it's a simple value, you just do this likely, unlikely, or you unroll all the ifs automatically behind the scenes without any helpers, without any flags?
Yeah. I think in the original static key document, it shows that if you just go to take this, so leave this branch in code, it generates something like 20 or 12% more branch mispredictions. So, and this is for every branch, right? Again, like memory reference, right? If you have like fast path, you don't want to do an extra memory for a global flag.
No. What I mean is like
Or even local.
when you see in the JIT that you can do it, essentially if the map is an array and the value is an int, you automatically enroll this branch, right? And you.
But how you toggle it when the program is already existing, like after we JITted it? I want to toggle
I
it.
guess you update the map value from the system call, and then at this point you know that, oh, I've actually enrolled some of the branches. Let me rejit the program.
And this is what we do here.
Right, but you're adding extra annotations, right? You're saying, oh, this is the place. This is, for example, why do you even need those like helpers? This static branch likely, right? That's if you remove the helper.
Because I don't want this map to be accessed from like by normal programs.
Why is it a problem if someone accesses it?
Imagine that program takes. So normally we don't care too much because like if we control it from user space, we just write 0, 1. But then if we allow programs to read this value, we want it to be consistent. And if a program, for example, says, I don't know, I take the pointer to this value and then it sets it to 1, and other programs think that it is enabled, but it's not. So it's just.
Right, so I guess you basically.
We actually do not use it anywhere from the BPF program, so we can just use a normal map probably, but yeah, it's not.
You basically need a flag to enforce that on the BPF side. You don't read and write it, right?
Yeah. This is where I said that we can like either treat this like BPF read-only prog flag differently, or introduce something like different kind of pointer to map value. Yeah, thank you.
Thank you, Anton. Next will be Datadog talking about is eBPF January.
Я просто посылал 100 лет назад, пытался разворачивать что-то в мапе. Эта мапа, если она константная, то я пытался в инструменте BPF эти бранчи разворачивать. Я делал как бы флиппинг этого. Я вижу, что это массив, число мапы константное, на коherent мапу значения.
All right. Hi, everyone. Thanks for joining this talk. So my name is Guillaume Fournier, but you can call me Will, and this is Hemant Smala. So we are from Datadog. Datadog is a cloud observability and security platform. So essentially, our mission is to help customers understand how their infrastructure is doing, how our applications are running, and if there is anything wrong with them, and how to fix it. So today, what we're going to talk about is essentially a bit of backstory around how we use eBPF in a couple of products, and more specifically, gotchas and pitfalls that we fell or not into while working on a security products based on eBPF. And then Hemant is going to talk about a bit of incidents, a few incidents that happened with CDM at Datadog, because we extensively use CDM in our infrastructure. All right, so let's get into it. All right, so before I jump into it, just want to stress the fact that I don't want to say with this talk that we shouldn't use eBPF for security. There are a lot of use cases for which it is totally valid to use eBPF, although it is excruciatingly hard in some cases, and that's pretty much the goal of this talk, which is to bring forward all the issues we encountered as we were building these products over the past few years. All right, so Again, I'm going to talk about a product that is called Cloud Security Management, and I wanted to share a bit of context so that you know what we want to do and why we have chosen eBPF to do it. So the goal, so this project was launched early in 2020, and our goal is to detect threats at runtime using eBPF in cloud environments. Essentially, we have a list of rules that will evaluate pretty much any kind of events at runtime that you may care about. And based on these behavioral analysis, we're able to trigger signals, which are essentially a way to notify customers that something is weird and that they might need to investigate. When we initially started, we had a couple product requirements to target customers and to know what we wanted to support. And initially, the goal was to basically support all major Linux distributions, which is, yeah, a lot. And which also means that we had to be compatible all the way down to 4.12 kernels, which again is a lot, maybe too much. And we also had to be cloud agnostic, so like support all cloud providers, support laptops as well as instances in the cloud, and all container runtime. Also, part of those requirements, we knew what we needed to write the detections we wanted to write, which means that we had to build and monitor a historical process tree. So what this means is we don't want to just have the view of the kernel of the process tree. I'm sure everybody here knows that in some cases, a process can be reattached to PID1 if one of its parents died. And that's an issue because in the context of security, you want to know where this process comes from, and you can't just rely essentially on procfs to tell you this context. So this meant that we had to stream all execution, exit, fork events to user space to build an historical process tree and then run our detections in user space. Similarly, our rules can be written on a wide variety of events, going all the way from execution events to file system activity, network activity, and so on. All right, so now what I'm going to do is talk about 10 oopsies that we encountered while working on this project. And yeah, they will be categorized in 3 different chapters. So the first one is going to be around hook points. The second one is going to be about the data you collect. And the third one is going to be about the environment. All right, so let's go. Sorry, your hook point wasn't called. So yeah, just before I jumped into it, just one more thing. Again, going back to the product requirements, this means that we had to use only kprobes, trace points, and TC classifiers. We could and probably should have used BPF LSM, but because of compatibility issues, unfortunately, this was not an option for us. Also, we need to collect SQL arguments and return values. This is more to give a context around what's happening more than anything else. And what it means is like the way it works for pretty much all our different event types is that we usually have a program on an entry point, so like the syscall entry, and then we have a couple of other programs hooked into kernel internals to collect more data. And all of this is aggregated into an eBPF context map, and essentially we send one final event on syscall exit. This will have consequences in the future, good and bad, but that's important to understand that this is basically how the solution works. All right, so let's go. Oopsie number 1. Yeah, so the first point is like you have missing hook points. Like there are a couple of edge cases where if you're not careful, you can have blind spots and bypasses simply because you're not hooked everywhere you should be hooked to actually catch everything that's happening. A very common one is trying to handle 32 bits programs on 64 bits machines, because if you don't hook on all the different compatibility layers with kprobes for all the syscalls you care about, then you're pretty much just going to miss some of them. So for example, you need to hook on sys_syscall along with compact_sys and like for any other compatibility here that might be in the kernel. Another one is around trace points. So there are specificities with trace points again when it comes to 32-bit syscalls. So normal syscall trace points, so I'm sure you know, but like there are 2 kinds of trace points. Like default trace points, you can have 1 per syscall that is already defined, and also there is the row syscall, sysexit, and sysenter, which is more generic because it will trigger for any kind of syscall. And the point is, the first type of trace points will not trigger for 32 bits binaries. And again, that's an issue because that's another way to bypass the solution if you were to use trace points. So yeah, so essentially what it means is you need to use the raw syscall hook point, and also make sure to translate the syscall IDs to the right values so that you understand which syscall is getting called. All right, oopsies number 2. So also, I forgot to mention, we didn't have this issue within our product because we noticed that it was important. So before we even went GA, like we actually supported the correct hook points. The next one, however, is a bit more dumb, but we did forget about it. So yeah, we need to look out for new syscalls. So OpenNet 2 was added in kernel 5.6. Yeah, and we did not keep up really close enough to the new syscalls API. And the point is, we had a bypass because of this. Another one is IO earring. So I'm sure everybody knows what it is, but essentially it's a way to run asynchronous syscalls in the kernel. And the issue with this is, again, you can run some operations that actually you care about, but because they will not call the functions you are hooked onto, you will not get called, and you will have bypasses again. One small disclaimer: if you eventually hook the right IO ring function that will do the operation that you care about, you also need to make sure that you have a way to match to the correct process context, because otherwise, if you just use the default helpers, you will actually get the process context of a key worker, which is not what you want. All right, oopsie number 3. So this one is around max active and hardware interrupts. So the max active one is pretty self-explanatory. This option is a way to control how many concurrent calls can be made to carry probes, to the functions that you hook and to the correct carry probe that you hook. And depending on the kernel version, this parameter is actually not configurable, which is an issue because under pressure, it's pretty much sure that if you just use a number of CPUs, you're going to have overlaps, and yeah, you're going to miss contexts and again, bypasses. So what this means for this is, again, you need to use raw syscalls instead of k-rate probes, and specifically the one that is about exits, the exit trace point. Hardware interrupts is a bit more involved. So the thing is, like, if you hook a function that can be called from the context of an interrupt, then this function in some very specific cases might, the k-probe that you put on it might not get called. And the reason for this is the classic reentry safeguard that the k-probe API has, which is just to make sure that one context cannot hook into multiple, cannot trigger multiple k-probe recursively. And the point is, yeah, if you do this, again, your k-probe is not going to get triggered, and then you're going to have this coverage. So one example of this is the TCP set state hook point. If you hook on this one, in some cases, it will not get triggered, which is a problem. All right, and the last one for this section is about hook points on kernel modules. So if a kernel module, if you actually hook on functions that are part of a kernel module, when the kernel module gets reloaded, removed, and so on, you will lose your program if you do not reintroduce it. And similarly, if for whatever reason you start before the kernel module is loaded, then you won't be able to instrument it. And then again, missing hook points means bypasses. All right, chapter 2. Next time, make sure you actually get the data you need. See, this one is pretty famous because a lot of people have been talking about it, specifically at Black Hat. But it's simply about the same old bypass of talk2 with pointers to values in user space from syscall parameters. To jump into, have a look at the talk at Black Hat. Is pretty self-explanatory, and it's very detailed as to how to do it. But essentially, the TLDR is, depending on when you actually check the content and the value in user space, well, the data may change compared to what the kernel has actually read. So the point here, and that's why I told you before that we have actually internal hook points in the kernel and not just syscall level ones, is because for the pointer values, essentially what you need to do is copy the data from the kernel and not copy the data from user space. This way you know that what you get is actually what was used by the kernel and not something else. All right, so this one is another one that is actually pretty common and that you can't do much about. It's about lost events. So essentially, when you have a fixed size ring buffer to send event to user space, under pressure, at some point you are bound to start dropping events and losing coverage. There is not much to say about this apart from try to push kernel filters as much as possible to reduce the number of events that you bring back to user space as much as possible. But yeah, this one is really depending on the workloads that you're trying to monitor and how accurate your kernel space filterings are. All right, I don't know what happened. All right, so until I get there, the last one is interpreters. So this is a famous one because for all or any other solution that only looks at syscall parameters, you are actually going to miss this completely. The point here is, when you have rules that actually look at executable path or stuff like that, you're not going to actually look into the script that is getting executed. And for that reason, what you see from the syscall point of view is that xyz.sh script is getting executed, but you're not looking at the interpreter. And the problem is the interpreter itself could have been something that you would have triggered a rule for. And just looking at syscalls, it's not enough. So that's another point why it's very important to have more involved kernel space hook points. Otherwise, you're just not going to have this context. Yeah, so essentially, don't forget to write rules on interpreters, and also don't forget to actually, collect the data around interpreters. All right, so the last chapter is about the environment. So essentially, make sure not to destroy the environment you work with, and also make sure the environment cannot stop your solution from working. So we've actually already talked about this one at CiliumCon this year with Hemanth. Essentially, there was an incident between Cilium and Datadog where the two products were canceling each other. It was based on a race because of the TC subsystem. Again, I'm not going to take too much time talking about this one, but what it means is if you want to use TC, you need to be aware that other people are using TC, and you need to follow a couple of guidelines if you want to be nice with them and make sure that you're not going to bypass whatever infrastructural use case or security use case they have implemented. So the rules are pretty simple. Never enter TC act OK. The reason is you want other filters to be called. It's not because it's OK for you that it's OK for others. Second one is never hardcode the handler of the filter, because we don't have a unique source of truth containing all the handlers of all the different vendors out there. So if you let the kernel decide and if you accept the value generated by the kernel, then well, it's much better because you don't have conflicts with other products. Never delete the CDS act QDisk. So again, this one is self-explanatory, but because this is a racy system by design, by the time you have decided to, between the time you have decided to remove the QDisk and the time you actually do it, another product might have loaded kernel filters. And the last one is make your priority configurable so that multiple products can actually be organized depending on what users are actually deploying in production. All right, hoopsie number 9. So this one is about out-of-memory kills. Right, again, it's pretty random because it's completely it only depends on the tool you are actually writing and also how you are deploying it. But essentially, if you set memory limits to an agent that you use for security, then depending on the memory pressure and the load that the machine is on, it is likely that at some point memory will need to be reclaimed. And well, bad news for you, if you reclaim an agent that holds kprobes, then essentially you're gonna lose coverage and you're gonna lose your kprobes. So what this means is it's really just about trying to find a balance, and it's ultimately a product choice between system availability and system security. Yeah, so there is no real solution for this one, unfortunately. And the last one, but not the least, there are a couple of kernel parameters that can be used to disable tracing, so specifically kprobes or other function tracing features, and which is, by the way, great. There is no reason why we should remove them, but the issue is it's very hard to monitor them. We found kind of a workaround to do it, but without this workaround, you can't really know if the system is enabled or not, because regardless of their value, you will always be able to load the kprobes. So even if kprobable disarmed and ftrace enabled or ftrace disabled are set to true or false, depending on the case, you will always be able to load the kprobes, and no one will tell you if those kprobes are actually working. So the workaround that we found to try to check the values of these different parameters is simply to send what we call an LPC call. So it's a very barbarous name to say that we just fake a syscall that is intended to a very specific hook point and a very specific function that we implemented. I mean, eBPF program that will just send a ping back to user space saying, hey, this is the values of those different parameters. And also, we're still working, we're still, up and running, so all good. Yeah, so I mean, the answer to this is switch to BPF at SM when you can, and when your compatibility metrics allows it. But apart from this, the other option is to do what we did. All right, and that's it for me. Hemans, take it away.
Thanks, Will. So in this section, I'll be talking about some of the challenges we ran into while using eBPF for networking, primarily through Cilium. So quick intro, like I'm an engineer on the compute data plane team at Datadog, so which means that we are responsible for all things container networking at Datadog. And at Datadog, we run most of our infrastructure on Kubernetes, and we use Cilium to power the networking layer in our Kubernetes clusters. And Daniel spoke about most of this earlier today, but a quick introduction. So Cilium primarily has a component called Cilium Agent, which runs on every single node in your Kubernetes cluster and is responsible for doing things like installing BPF programs, assigning IP addresses to pods and things like that. And Cilium mostly installs TC or XTP BPF programs, and Cilium allows us to get rid of kubeproxy. So using Cilium, we are able to use eBPF instead of IP tables for most of the service implementation. And in addition to that, we also use Cilium for things like policy enforcement, IPAM, and other eBPF-related speedups. So in this section, I'm going to talk about 3 different issues that we ran into. So the first one is service connectivity issues. So this started as an incident where one of our users reached out to us saying that they were not able to access one of their Kubernetes service. And quick background on Kubernetes services. The Kubernetes service of type cluster IP is the default Kubernetes service, which basically gives you a virtual IP that represents your entire cluster, and you can use that virtual IP to access the service from anywhere in the Kubernetes cluster. So Cilium basically implements this client-side load balancing logic using eBPF maps and BPF programs. And there is a completely unrelated feature called graceful termination, where Cilium also watches for pods that are entering terminating state and proactively removes them from the services backends, so that the workloads that are getting terminated do not get any new requests. But there was a bug in the cleanup logic. If the Kubernetes service was deleted when one of the backends was in terminating state, some of the backends were left behind. What makes this harder is that Cilium actually maintains an in-memory count of total number of backends in the BPF map. It does that because it's actually expensive to calculate the map size. So when we use the Cilium CLI, Cilium CLI told us that the backends V2 had only 3,000 entries. But when we use BPF tool on the node, we were actually saturating the BPF map. So we reported this issue upstream, and it was fixed pretty quickly. And this was really a corner case with a race condition that happens very rarely. But the learning from this incident for us was that we realized that we had no monitoring on BPF map usage whatsoever. So we were looking for a metric that allows us to track our BPF map usage. And at the same time, Cilium was in the process of building a new metric called Cilium BPF map pressure. This metric is actually interesting because it doesn't actually cover all the BPF maps that are currently used by Cilium. This is primarily because of a few limitations with LRU BPF maps. The limitation is that if the kernel evicts an existing entry to make room for new ones, there's no way for the user space to know about it. So for a long time, any map that uses any feature that uses LRU BPF map was not included in this. And connection tracking was one of the features that was using LRU BPF maps. But luckily, I think Song implemented a new API which allows you to batch requests and use batch API to measure the size of the map a lot more efficiently. And Cilium started using this batch API to basically estimate the BPF map size on the real BPF map size using this API, and it is a lot more efficient. And on top of this, Anton also built a new feature that allows you to export native stats from the kernel directly. And using both of these features, now you can have full observability into the total map size on your nodes. And this is not yet included in Cilium, but I think it'll make its way soon. And there's also a detailed talk about this entire topic by Joe in one of the previous LPC sessions. If you're interested, check it out. And a few more gotchas. So if you want to help your users right size their BPF maps, Cilium has this interesting flag called BPF map size dynamic ratio, which basically allows you to look at the total amount of memory that's available on the host, and it'll proportionally size your BPF maps on startup. And depending on how big users' Kubernetes clusters get, and depending on how many workloads they have in these clusters, your users might eventually want to resize their BPF maps for different reasons. And in our environment, we realized that whenever these BPF maps were being resized, we were seeing a few packet drops, and packet drops due to missed tail call events. So I don't fully understand the details behind this, and I think it's being worked upstream to get this addressed. But the takeaway here is that resizing BPF maps, especially the tail call maps, is tricky in production, and I think it's racy. So the next one is Cilium identity corruption. This also started with one of our users complaining that they were seeing some unexpected packet drops from the Cilium's policy enforcement engine. So the Cilium identity is basically composed of two components. So the first one is the local pod identity within a cluster, and the cluster ID. There's one unique cluster ID for every cluster you can allocate during the provisioning time. And our Kubernetes provisioning system internally assigns a random number between 0 and 255 for every Kubernetes cluster we create. So in Cilium's data path, this identity is basically serialized into the kernel's SKB mark, and it's restored at a later stage in the data path. And unfortunately, and this is an example of how these bits get shuffled around from the identity. So at the top, you can see the two parts, which is the local pod identity and the cluster ID, and they get shuffled and serialized to the kernel's SKB mark. And so unfortunately, there was a completely unrelated feature to support multi-node node ports in AWS CNI, where that feature was also using the same 8th bit, a single bit, but sometimes this 8th bit would get restored, and that would basically mess up the cluster ID part of it. So we were seeing these packet drops only in clusters that were using cluster IDs greater than 128. So there's an unofficial registry that's being maintained by folks at Isovalent that basically documents every project that's using the kernel's SKB mark. So the takeaway here is if you're planning on using the kernel's SKB mark, make sure you take a look at who else is using it and or add new entries to that. So the last one I wanted to talk about is trying to use SK reuse port in combination with BPF SK assign. So Cilium has a feature called 2FKDN network policies, which allows you to basically have have network policies against a fully qualified domain name. And Cilium implements this by having a DNS proxy. So Cilium intercepts all the DNS requests that are coming from your pod using a DNS proxy, and it intercepts them using either BPF SK assign or I think a legacy way of using tproxy. But once the DNS requests are intercepted, the DNS proxy would make the upstream requests. And once those DNS names are resolved, Cilium would plumb the data path with the corresponding CIDR policy, and then the response would be sent back to the Kubernetes pod. And the pod then tries to connect to its destination service, and the policy would be enforced. But the problem with this approach is that the DNS proxy's lifecycle is very tightly coupled with the Cilium agent's lifecycle. So whenever we do a rollout of Cilium agent, the DNS proxy would also go down, and that was problematic, and we wanted to solve for that. So we We were building a standalone DNS proxy that would run alongside the Cilium agent's DNS proxy, and so that we can load balance between both of these proxies. And even if Cilium agent is unavailable for some reason, the request would still go through. And we wanted to take it one step further and try and use a BPF program on the reuse support group to basically customize the load balancing behavior and send requests to the Cilium agent's built-in DNS proxy if it's available and running, and send it to the standalone DNS proxy only if the primary agent is unavailable. So we built a POC and tested it out, and everything worked great. But when we plugged it into Cilium's data path, things did not work. So we wanted to understand why this is happening. So we wrote a small BPF trace script to basically trace the reuse port select sock function. And we realized that in Cilium's data path, the SKB variable is being wiped out. And turns out there is actually a limitation in the kernel, which has been addressed very recently by Lawrence. So if you try to use SK reuse port BPF programs with BPF SK assigned, the SKB value would be wiped out. And the function that actually triggers the reuse port BPF programs looks at the SKB value, and if there's nothing in it, it would basically default to round robin load balancing, and your BPF program never gets invoked. So with this patch, everything works as expected. Yeah, so it's just a gotcha. Yeah, thank you. That's pretty much all we had for today.
Okay, I got one question for the, you mentioned earlier the TCP set state doesn't work. Can you give more details why it doesn't work?
Oh, okay, cool. Yeah, so essentially the idea is, you know how K-probes right now have, I mean, they've always had, but like, they have a fail-safe when you actually trigger a K-probe, and like, when a K-probe is called, you actually have a check to see if a K-probe is already running in the context of the CPU. And essentially, the idea is hardware interrupts are a way to, I mean, depending on how the priorities work, the the resolution after a hardware interrupt can be piled on a soft interrupt handler. And the thing is, if this resolution will call another hook point that you have hooked a K-probe onto, since you still have a K-probe running, it will not be triggered. And that's essentially what happens with TCP set state, because you can actually check it right now if you want, just by actually printing to screen the K-probe on TCP set state. You'll see that sometimes it is run within the context of an interrupt handler. And the point is, this means that, well, when this happens, the second K-probe will not get triggered. And this is a loss of coverage, depending on your use case and what you do with it again. But yeah, the TCP one is an easy one because networking is obviously more likely to have these kind of things happen. But that's the TLDR.
Yeah, makes sense. But I think the talk Jury did this morning may help. He has.
Okay.
You can try trace point on some other things.
Yeah, absolutely. I mean,
which will have less chance that you will get.
Yeah, for sure. I mean, the underlying issue for this here is that we don't. I mean, maybe there are solutions with trace points again, but like if you need to use K-probes and you don't have a choice, then really trying to avoid these functions is the only way to go. And most of the issues I presented today, honestly, is based on the fact that we had to be compatible with old kernels, which means that we had to use K-probes. If we were to build it today with the technologies that are in the kernel right now, we would pretty much likely not be using K-probes.
Can you elaborate again on the K-probes disarm thing that you mentioned
Yeah,
earlier? Like, so
sure.
what happens? So basically, it will unload all the K-probes or trace points that are currently attached, right?
So I would need to double check it. Honestly, I don't remember, but like I know that K-probes will be affected by the K-probe disarmed for sure. I think they are also affected by the ftrace enabled knob. And then the ftrace disabled one is because of, when you have a fault in the kernel, just to protect itself, or at least that's my understanding, the kernel will turn on this knob, and from this point on, no more kpros will be triggered. This one is more of a security feature. You can't do anything about it. The only way to recover is to restart. But yeah, so I don't know if that answered your question, but essentially, if one of these parameters is set either to true or false, depending on the case, your hook points will no longer be called, and you have no way to know or monitor that someone has actually changed the values. Yeah, because they are just variables in the kernel.
So how did you overcome it? I mean, you're monitoring that, or
yeah,
or like should there be an LSM hook or anything like that to potentially prevent something?
Yeah, so maybe what I said wasn't clear enough, but the idea is from /proc/klsims, you can get the address of those different values, and those different variables, and then from there, essentially the goal is to periodically check the values at those pointers using an eBPF program, and to do this periodically, we could either had used a perf event that could have been triggered every second, for example, or and this is what we did. You trigger a fake syscall. I mean, it is a syscall, so you do an IOCTL syscall with very specific parameters, so that a kprobe on one of the internal functions of the IOCTL syscall will realize, if you check for those parameters, that this is actually an API an API call to do this check, but it will essentially, when it recognizes those magic parameters, it will look for the values of those different knobs and then send an event back to user space. And the point here is two things. First, if you have an event, this means that your kprobes are still enabled. And second, we can also check the other values. I mean, you should have all of them to make sure that everything is still working properly. So yeah, it is definitely a hack. It is not great. It's not real time. We don't know who changed it, if it got changed, but at least it's a way to know that you're up and actually running, and not just up without knowing if your hook points will fire.
There's another question from Lawrence. You mentioned that the number of CPUs for setting max active doesn't always work. Have you found a better heuristic?
The bad news is no. The heuristic we use today is set it to 512 and hope for the best. No, I don't think there is really a fix here. Or if there is one, I don't know.
Any more questions? Okay, thank you. We're going to have a break. We'll come back at 4:30.
Huh?
Thank you.
Super. Yeah. Why?
I just saw him. I remember he was using also command.
Yeah. Yeah. I asked him if he's coming as well, but he said I don't know, too much trouble. I mean, I don't know.
Yeah. He's depressed.
Depressed?
What?
And they.
Did you?
No, he's fine.
Hi, can you hear me okay?
Just found out that on Wednesday we have to strike this room also. Gotta put those two big screens in Potomac.
Oh, so you got the call?
So the system is like 1 or 2.
Yeah. Somehow I feel like the mem cache suddenly doesn't have a chance to read the song. Let me know. Yeah. Hi guys, let's get started. So next we have Barrett talking about the awesome kernel scheduler in BPF. 1 second.
I've got control if that helps already. So we might be good to go.
Do you have control? Do you have control?
Yep.
Okay, awesome. Because I was trying to give you control.
Yeah.
Okay, all yours.
All right, thank you. Hi, everybody. My name is Barrett. I'm going to talk to you about some of the scheduling where I'm writing in BPF. Basically, there's this intro to this thing called Flux. It's a framework for writing schedulers, and it's written purely in BPF. I'm going to talk about that mostly to give you some ideas about what we're trying to do, but then mostly just so you can understand what we needed to do to make this work in BPF. So the stuff that might be really interesting would be like some of the data structures and how we did object-oriented programming without function pointers and some other stuff. But first, let me just talk about Flux in maybe about 5 minutes or so. For those of you that were here last year, I talked about how we do scheduling in Ghost. Ghost is a system we have. It's a kernel scheduling class where you have a BPF agent that makes scheduling decisions. And you can do things like talk to user space and talk to an application through BPF maps. But the general idea is that BPF makes decisions and user space has a role. But I just mentioned that just as a framework for you to understand where we're coming from on this. And Ghost is really similar to SCHED-EXT, for those of you who are familiar with that. The problem I was given is that I needed to design a scheduler, given that we had large multi-core machines, possibly with crazy cache topologies. And likewise, we're working on applications with different classes of threads or workloads. For instance, I might have a set of threads handling RPCs and another set doing housekeeping or something else. And the other interesting thing about this is that the set of available CPUs that I have access to as the kernel scheduler may change at runtime. For instance, we often yield to CFS kernel threads and workers. You could also be running in a paravirtualized guest, or you're sharing a machine with another important application. The approach I took to solve this was to decompose the scheduler. I know that we have multiple CPUs. How about we make them a central component of the scheduler itself? Then the idea I had was, how about we dedicate certain CPUs to certain classes of threads in an app? And this is basically a way of partitioning a CPU so that threads of the same type run in the same partition. And these types are things like the RPC threads or housekeeping or something else like that. The idea then is that we can have what I call subschedulers for each of these thread types. And each subscheduler has its own policy. So RPC threads, for instance, I might want an earliest deadline first policy. Housekeeping threads, just give them FIFO or a fair share or something like that. But the important part is that I don't need to have a magic policy that works for all the thread types. And then I will have something like, what is my overall partitioning policy? Like I have maybe 100 CPUs. Let's give housekeeping 5. Give RPC threads the rest. But wait a second. Where does that partitioning policy come from? The 5 versus everything else? Well, the idea is that the CPU partitioning itself is scheduling. When I said give 5 CPUs to the housekeepers, well, that's an allocation of CPUs to subschedulers. And that itself is a scheduling decision. So you end up needing a scheduler of schedulers, which is always fun. And the way these schedulers are going to coordinate is through the CPUs, sort of as a unit of currency. So whenever we're making requests or allocations, we're talking about CPUs. I actually think this is kind of a universal scheduling concept whenever we talk about like end-to-end scheduling or even paravert scheduling. But so the end result was this framework I put together called Flux, where you compose an overall scheduler from a hierarchy of smaller subschedulers. And a given thread belongs to a single subscheduler at a time. CPUs themselves are allocated to subschedulers in a hierarchy. And these subschedulers I keep talking about, they're really just blobs of code and data, like a little bit of functions and maybe a run queue and a spin lock. And they exist in a parent-child relationship. And each subscheduler, when it gets its turn on the CPU, it either schedules a thread, one of its own threads, or a separate child subscheduler. Let me just give a quick picture of, here's our hello world scheduler with a global FIFO policy. And you got these 3 boxes here, each of which is a subscheduler. Rossi is one that's just a CPU scheduler, and it hands out CPUs. And it's a really dumb policy. It gives the BIF scheduler whatever it wants, and everything else goes to idle. BIF is another scheduler, and you'll notice I've got really short names for these things. It's because each one of them is really kind of a short blob of code, and it's not really super complicated. BIF is just a thread scheduler. It's global FIFO. All it is a run queue. And the idle scheduler is just, it's sort of a half-baked scheduler. All it does is halt the CPU. And the way CPUs kind of flow through the system, like the CPU lifecycle, is BIF will make a request, and Rossi will get a callback saying, hey, you got a request for CPUs from BIF. And you pick a CPU and you send maybe an IPI. So there's a bunch of little function calls where Rossi grants the CPU to BIF. BIF will either run it or yield. So you can sort of imagine how this works. So that was just a whirlwind overview of Flux. There's not enough time to talk about Flux. And I wanted to focus on how we do this on BPF for this talk. And you can imagine all sorts of things from this, but just from what you've gathered so far, you can tell we have data structures of different types. There's different types of threads, different types of subschedulers. CPUs, they're important too in some way, so you're going to need structs for those, and we're going to have a hierarchy. So are we dealing with pointers? We've got to make decisions, so linked lists and trees. There's also stuff like callbacks. So there's a whole bunch of things that we need to do. So let me dive into what we do on the BPF side of the house to make all this work. The biggest thing we do is we do memory management through array maps. And just about every allocation we make is from an array map. Like, so whether we're talking subschedulers or threads or even like per CPU data blobs, and they're all unmappable. And specifically, the reason I like the M mapping is that I mentioned way back on one of the earlier slides is that our scheduler runs in BPF, but it actually communicates with a user space agent. And that can like adjust policy bits or something like that. And we also talk to an application who can tell us specific things. Like I mentioned, the RPC threads want to have a deadline. Well, that actually comes from the application itself. So it's really convenient to be able to M-map these data structures. But since I'm using an array map, well, there's no real pointers. So how do I get my pointers? Basically, a pointer is really a dense integer in an implicit array. So I do have pointers in the code, like flux sched rossi is a pointer. But it's really sched ID 1, for instance, or some thread foo that might just be in the thread array number 42. And we actually do have a map, because a very common operation is to say, okay, thread IDs, how do I find for a given PID what is my index in the array? So we have a hash table map for that. But for the most part, the idea is that pointers are kind of integers. And once you think about that, we can actually build our own data structures. So for an example, we've got one of those BSD style linked lists. I call them array lists, but the general point is the same, where you have your first and last pointers, but instead of pointers, they're integers. And each entry that you embed in your struct, instead of like next and prev being pointers, again, they're just integers. And you can embed the link just like usual. And you can, of course, do this numerous times. You can have an element be in a dozen lists if you wanted. And we have the usual operations like first, next, and prev and remove. But it is kind of ugly because we do have to pass the array and the array size to every one of the operations. I actually hide that with macros most of the time because the array size is pretty much always a constant and whatnot. But we also have for each iteration, but of course it's BPF, so you can't loop forever. So we've got a little macro that says, oh, I want to loop up to max number of times. But you can basically build a linked list. You're curious about why did we pass the array size? And we have to convince the verifier. Anytime we're converting from an index, like an integer, to a pointer, we have to make sure that the verifier is happy with that. It basically has to make sure we stay inside the array map. The thing I do also is say index 0 is no element. That just makes your life a lot easier. And so everything is really just -1 whenever I do the conversion. And we got a little helper to do that for the given an array and an array size and an index, give me the pointer. And it's got some inline assembly to make sure that the compiler doesn't trick me. But essentially, that's just, hey, what is the pointer for the array at index, foo? There's actually a very subtle point about locking with these arrays. So imagine you have this array map of the threads. And is it n elements of struct flux thread? Well, anytime you did that, you would need to do a map lookup element call, which you can't do while holding a spin lock. The thing about that is that anytime I'm doing these list manipulation operations, I'm usually going to be holding a spin lock. So what I did instead is I had it be an array map of a single item, and that single item is actually an array of n threads. The data layout is identical. In fact, user space, when I map it, I don't tell it that it's an array of one of a giant thing. That's just a little trick I do to have the verifier. So I'll basically do a BPF map lookup of that one giant array, do that outside the lock, and grab the lock, and then do my operations. It doesn't actually work for all the structures because some of my structures, like the flux sched, has a spin lock, and you can't put spin locks in interior structs, or at least you couldn't when I wrote this. And That was an interesting thing. But linked list isn't all you can do. We can do AVL trees. Basically, it's one of those self-balancing binary trees. I didn't do an RB tree, just a couple of reasons. The big one is that AVL is easier to implement. And the other one is that it's denser than the RB tree. And I did want to limit the max AVL height. If you ever look at the tree walking code, it's all while loops. But I replace those with something along the lines of like, wait, for I up to my max height. That does have the limitation that we can't stuff everything into the tree. So that's a little unfortunate. Don't really have that happen often in practice, but in case I do have an overflow linked list. And so on like my get min operation, what I'll do is I'll check the overflow list as well as the tree, just so that I'll eventually pull items out of the list. But it is one of the drawbacks of this style. We also have what I call a half-baked object-oriented programming style with unions. So I mentioned we've got threads and subschedulers, and they're all different types. But the BPF map can only have a single type. So if you think about the two classic ways of hooking specific objects to generic ones, we have the thing from the VFS where you'll have your generic struct, like your inode, and then you'll have like a private blob on it. And then that private blob points to something like your ext inode. Well, we don't want to have more pointers in general, so let's not go with that. The other style that you'll see people do is embedding the object in the specific object. So you'll have like your object foo, and inside it will be something else, and you'll use container of to get the generic thing. The thing about us in BPF, though, is that we need all our objects to be the same size. So what I did was I added a union to the object. So each possible thread type gets a union member. And overall, the struct of the thread, for instance, is going to be the same size for everybody, regardless of your type. Let me show you a picture. When I say, hey, we have this flux thread, the generic part is basically a struct at the top of it. And then everything else is in the union. So depending on whether you're a BIF thread or a doc thread, which is a different type of scheduler, depending which one you are, you will then use that part of the union. But overall, the struct flux thread is all the exact same size, so that I can have one giant map of all of them. This is a very different memory management than the K-pointer style. And that's kind of, the K-pointer style is more of like the managed memory where you do the object new and object drop. And if you do that, you do have access to like the list head and the RB tree stuff. And the verifier knows what you're doing, is kind of my understanding of that style. The style I'm dealing with is more of you have a blob of RAM, you can just build whatever you want. There's an overall array map. It's just up to us to allocate within it. It's almost like you started an OS from scratch and you just have all of memory and you have to make structure out of ones and zeros. And the verifier, its only role here is just making sure you stay inside the blob. And there's pros and cons for both of these. So on the K-pointer style, nice thing is it's dynamic allocation. And the other thing is that the kernel can enforce invariance about your structures. Like you can safely traverse the tree. For instance, I have to convince the verifier that I am, not running off the edge of my AVL tree, but the kernel kind of makes sure that your tree is fine for you. The downside, though, is verifier needs to know about your types. And you also need to associate your spin locks to your data structures, as far as I know. And there's some complicated stuff with the ownership model for memory. But the other one, at least from my perspective, it's a little tougher, is you need these K-funcs and stuff and the helpers built into the kernel. So if you need a new structure, you need a kernel. That's a little harder for me where I'm working. If you want a new operation, you need new kernels. And the biggest one that I think might be is you can't touch the managed memory. Like for instance, I talk about having user space manipulating data structures at runtime, just maybe like atomic ORing bits or something like that. You can't really atomic OR a bit in a CPU bit mask from user space. So that's one of the things that having it be just a blob of memory that puts it into our hands means things are a little bit easier to work with. But similarly, there's pros and cons to the blob of RAM style. The big one I like, as I mentioned, is it's mappable by user space, but there's no guardrails whatsoever. So if you corrupt a data structure, you're on your own. The verifier is just making sure that you stayed inside your blob. It protects itself, but not you. It's also hard to convince the verifier your code terminates, like that AVL tree stuff I mentioned. It's pretty branchy, so that's a lot of states. And I had to do a bunch of other little things just to make it past verification. By comparison, if you call kernel func, a kfunc helper for your your RB tree stuff, well, the verifier just knows it's good because it's kernel code. The other thing that is kind of a downside is we have a giant blob of RAM. Well, it's wasted kernel memory because I needed to pre-allocate space for all my threads. That could be a lot of threads. And I definitely would like to not map that in until necessary. One of the things we were talking about was that it is possible. We think we can make it so that you can fault in the array map on demand instead of populating it. That would be pretty useful. That means I would only waste as much RAM as I ever used. Still not that great, but so it is a con of this style. But that was about it on the data structure side. Let me talk a little bit about the function pointer stuff. Well, there are no function pointers, but you may be wondering how we get from a request for CPUs to like a callback. You'd expect something like, typically you'd say, hey, I have a function pointer struct called ops, and I want to call the request for CPUs. I don't have function pointers, but I do have every subscheduler and thread having a type. So meaning that a subschedule has an ID and every thread has a known subscheduler that it belongs to. So I have a lot of macros that generate switch statements so that I would say something like, hey, my pick next task function is really just a switch based on the scheduler's type. And then there's some other horrendous macro that your actual scheduler agent will define. And that'll look something like this here, where I'm generating the case statements for that switch. So if you were a type housekeeping, you want to be handled by the BIF scheduler is kind of what this means. And if you're an RPC thread, you want to be handled by this other scheduler called doc. And these are kind of similar to function pointers, but it's done with switch statements. And the thing that I find is interesting about this is that, with Flux, we talk about how we're composing our scheduling agent from subschedulers. You actually pound include the real C files themselves, which is always fun to do. Because ultimately, this BPF program is going to be just one blob of code that's all thrown together. So talk a little bit about our future plans. Big stuff. We do have some code, and it is sitting in one of our Ghost user space repos. Various things like the Flux headers and how you do like the queues and the AVL code and all that. It is built on top of Ghost. The linked list and AVL trees are actually independent of Flux, so anyone could just grab those. And if you wanted to just do the style of building data structures in memory, that's kind of independent of Ghost and Flux and anything else. That can be used in any programs if you like that style. But speaking of open source, even though it's not directly related to Flux or BPF, I was asked to relate to everybody that we are committed to upstreaming our changes in general, and that our cadence for our production kernel follows the LTS stable kernel. So whichever one is next, apparently we're going to be tracking. As far as open sourcing Ghost stuff goes, though, we do have this overall vision of building Ghost on top of SCED-EXT. And specifically, this Flux business I was talking about, we want to port it on top of SCED-EXT directly instead of using our existing like Ghost kernel code. I do have an open question, though, of whether do I want to stick with my existing blobs and memory style, or if I want to switch over to the K-pointers style. I'll probably in the short term keep with my style, but it is something that's interesting. And the ultimate goal I have is that any scheduler that we're writing for Flux on Ghost will work reasonably easily on Flux on SCED-EXT. But yeah, anyway, that's kind of the whirlwind tour of some of this stuff. But the takeaway is that we do have this framework called Flux. It's for building schedulers from a hierarchy of subschedulers. And there's a lot more to cover, maybe in some other time or some other venue when we can go into more detail on it. And for your own BPF programs, you can basically build anything out of a blob of memory, even in BPF. And it's just going with this pointers is really arrays plus integers style. And maybe if you have some patience and willing to dive into a little bit of macros, you can maybe even do some object-oriented programming. But if anyone's got any questions, I'll take them now. Otherwise, thanks a lot.
So hi Barrett, I had a question. So You mentioned that you use spin locks to synchronize access to these like data structures that you build out of the array maps. So do you also modify them from user space, or are you only modifying them from inside the kernel?
Typically just from inside the kernel, because otherwise it would be a mess with because you can't grab the spin lock. One of the people I work with was talking about, and he hasn't done this yet, but talking about one of those data structures that it can be like lock-free, heaps or something along those lines. I haven't seen the code for it yet, so I don't know what the deal is on that. But conceptually, if you had any shared memory data structure, you could do it between user space and BPF. In earlier versions of some of our scheduling stuff, we had some similar to BPF ring buffers. We had stuff where either BPF or user space could stuff things into a run queue, but it's not this style of run queue with like linked lists and integer pointers. But yeah. I see a comment in chat too. It says maybe take a look at using BPF loop over your memory blob. Limits for termination there are pretty high. And yeah, thanks for the pointer on that one. It is on the to-do list. The one issue is I forget if it's BPF loop or another one. I think BPF loop is the one that doesn't work when you're holding a spin lock. But there are open-coded BPF iterators that I need to take a look at that I think work while you're holding spin locks.
I think the open-coded ones will have the same problem, because right now the limitation is that you cannot do a function call while holding the spin lock. So the open-coded ones also do iter new, then iter next, and then iter destroy. So that might not work either, I guess.
Oh, good to know. I'll definitely have to play with it. But one of the things that we're looking to do is, I guess, help the verifier with stuff related to our array maps in particular. Like, for instance, I'd like to be able to hold a spin lock and then do an array map lookup. There's some weird niche reasons for wanting to do it, but given that the array map accesses are JITted, and if it gets JITted, it'd be nice to say, which I know they're going to be. If that's going to happen, then it'd be nice to not have the helper function check, because we're not actually calling the helper anymore. But so there's a whole bunch of little things like that, and then the open-coded iterators that'd be nice to do. And there is a comment in the chat about having open-coded spin locks. It is then, which that is something we've considered, because you can do at least a try lock, because you have atomics, so you actually don't have to use BPF spin lock. But that's pretty funny though. Any other questions?
Any questions? No? Okay. Thank you, Bharat.
Cool. Thanks, everybody.
Thank you for the presentation. So the next presenter will talk about a continuous BPF profiler, Sumir. Can you check you have control of the presentation?
Hi. Am I coming through clearly?
Can you hear me? Can you check whether you can go back and front of the slide? I just
Can
gave
you
you
hear me?
control.
Can you hear me?
Not that well. Yeah.
Is there noise or is it just?
Okay, now it's much better. Yeah, we can hear you. Yeah.
Okay, then I was just speaking very softly. Yeah.
Okay, it's all yours. Yeah.
Thank you. So hi, and good evening or good afternoon. I'm going to talk about developing a continuous eBPF profiler and what went into the entire effort. So here's the agenda. I'm going to talk about how we can take high resolution profiles, and what I mean by that, how we make it work across user space and kernel space and different architectures and for different languages, runtimes, and across the entire, across bare metal systems and servers in the cloud and what we have planned. And there's actually quite a lot of things that I want to cover here because we truly do work across the entire stack. There are some things we need to read registers for some things, and then we want to present the profiles in a very debugging friendly way and a very developer friendly way, so that you can just take a look at the UI and find what you're debugging and down to the line number. So there's quite a lot to cover, and when I actually prepared the talk, I rehearsed in the daytime. I think I'll be slower in the right now. It's 3:30 in the morning for me, so but I'll still try to zip through. Just bear with me. Anyway, since this is plumbers, before I move ahead, there's story time first. So it's a story of how I went from the pipeline of becoming a profiler maintainer from a newbie kernel contributor a few years ago. By few years, I mean just mid 2020s. I was very new to this, and I ended up very luckily doing an internship working with Julia Loal on Coccinelle, and then subsequently outreach you with the graphics subsystem, where I worked on some VKMS drivers, mentored by Daniel Vetter and Melissa Wen. So now coccinelle patches, they involve finding these patterns, sort of less optimal patterns or patterns susceptible to bugs maybe, and they're replaced with better code patches. And Coccinelle is a static analyzer that does this. And when I was doing this, I came across a lot of such patches in the kernel, and it was very easy to do these things with Coccinelle, but I could never understand what exactly was the impact that was happening kernel-wide and how this was making a difference. Then in the next internship, which was the graphics subsystem, I was working for these something called the VKMS driver. It's a virtual kernel mode setting driver. What it tries to do is emulate your normal graphics driver, but it does so with the intent of being able to eventually run in like a headless or CI sort of environment. And this again involved learning a lot about shell, basic shell, C, Kimu. Like I said, I was very new to this, and also like everything about how the graphics driver worked. And again, I found it very, very intimidating. And I didn't really understand data structures. What was most overwhelming to me was how functions call each other, which functions calling which one, where is the memory leak happening, how am I supposed to like navigate the whole system? You know, you have your DMSH logs, you have your tracing systems, and you can take snapshots also, but how do you link all of this together? And the entire debugging process was sort of looked somewhat like this for me. The only tools I knew then were ftrace. It gives you dynamic tracing, but it's a lot to keep up with. Especially, you can't do this without using grep also. Then you have logging in real time, and I didn't actually know about flame graphs then. I learned about it much later, but they're also like a pretty cool tool. However, I always wished I could get some of these in like a single application, and something very developer friendly, I guess, or very debugging friendly for somebody who's new to the ecosystem. And I couldn't find anything back then. And next thing I know, I was also like looking for a job and everything. So yeah, then fast forward a few months, I came across continuous profiling. So this is basically what my day job is. I found that I went to an interview and the person was like, you know, we're trying to build a system that can tell you in sort of in real time what's going on. It can tell you which function's calling which one. It can show you an infra-wide overview. And then I ended up at Polar Signals, building the continuous profiler. The profiler I'm talking about is Parka. And what you see on the right is actually supposed to be inverted stack traces here, and we'll get into more detail on that. I've been working as a junior software engineer here and been working on this for like 2 years, and I'm very excited to tell you about all the things I've been working on. So what's Parka? We just saw flame graphs in the previous slide. I want to introduce you to what I call, or what we call, icicle graphs. They're called icicles because they really look like that. But when we named them, we didn't really realize that they would be, they're sort of like also the opposite of, or inverted flame graphs. And I think the flame and the ice thing, or the fire and the ice thing really goes very well with that. So now we're at the first thing on my agenda, which is high resolution profiling. But before we get there, again, I want to just look at this. What this does is it shows you, like I said, an inverted stack trace, or the stack trace. You can, in this one particularly, you can see the root, and then you can see a Go program. You can also see the Go runtime, and we'll get into more of this later. And the next thing is, this is an architecture diagram for Parka. And Parka has two components. One of them is the server, one of them is the Parka agent. And the Parka agent is the part that where we use eBPF to get all this information that we ultimately convert into stack traces. And we'll come back to this diagram later. As I continue showing you all the parts of Parka, we'll keep referring to this. Now, about high-resolution dynamic continuous profiling. So what do I really mean when I say high resolution? When I say high resolution, I mean just the amount of details we can see in a stack trace, or so if you notice carefully, you can see, you can of course see the stack trace. The graph that you see, it's all the lines represent a different binary, and you see it over a certain period of time, and this one's configured for, I think, the last 15 minutes, and this keeps updating frequently. So when I took the screenshot, it was I was just looking at the last 15 minutes. So this is a sampling profiler, which means that we are not really tracing this. It's taking samples like 19 times per minute, so at like 19 hertz frequency, and then it sends this information every few seconds to a server where we symbolize the stack traces, and we can see them. And because it does this so often, we call it a continuous profiler. It changes. It's not a static snapshot of a profile like we usually get with flame graphs, which is why it's dynamic as well. And the high resolution part, that's something I want to talk about a bit more. So if you notice this box, I'm not sure if it's fully readable. I'm hoping it is. But if you'll notice, there's a lot of information you see when you hover on these, hover on different parts of these graphs. It's a screenshot of when I was doing that. And here it's the screenshot. It's landed up on a part where we are profiling an Erlang app. So you can see you can see Beam here, I think, and you can see the process ID number. You can see this is running in a container, so you can see the pod name. You can see the process ID host names. You can see the C group. You can see the name of the binary, and more useful information. Then there is, if we go to the next slide, you can see this is when you click on a certain point in the icicle graph. Like I said, we try to give profiling information down to the line number. So these frames that you see, they actually are indicating how much of CPU is being consumed by them. And these are actually functions. Each frame represents a function. And so when you click on something, you can see the file it's coming from. You can see the line number here. You can see the memory address. You can see whether it's like inlined or not. You can see the name of the binary. You can also see the build ID. Now, something else that is important here is how does this help us? What do you want from a continuous profiler? Like, where do you draw the line between information that's helpful? Where do you draw the line between information that's actually noisy? The good thing about Parka is that we have tried to have an interface that helps filter these things. So you can, in the query box that you see here, you can actually specify something, all of these labels. This was very clearly inspired by Prometheus, because the writer of this is one of the major contributors to Prometheus as well. And right now we only have CPU profiling, but then you can group by function names, you can sort. There's a legend that I'll be showing you later. It usually has, it can highlight certain paths. You can search for a function. And then there are other ways to see this so that you can actually cut down on the noise and only see the parts that you care about. You can also search for like a certain binary, just a certain process, and by just using that information. And you can also like search by, I think, compiler versions in some cases. This is one, like, so icicle graphs. Another way of seeing this information is, there's a table form, and you can see like what's the cumulative amount of CPU usage by every function, and we call this the table view. The next thing I want to show you is, so I think this is, yeah, so this is all the things, some of the things that you can filter using the query box. And yeah, you can see compiler versions, I think. And so yeah, that's for an overview. The part that I'm mostly going to focus on next is what does it take to actually make this work from kernel space to user space and get a very infrastructure wide, and that in a way that you're able to like just profile everything on your machine, every process that runs, every binary that runs. So how do we do this? A bit about profilers for the cloud native environment. I say cloud native, but actually this is something that's that can be run on bare metal and any other environment that has Linux, as much as it can be run on cloud native. So first we have, we start with the discovery mechanism. Then we have a mechanism to collect these traces, and by discovery mechanism, I mean, for targets, I mean, our targets here, we are actually looking at the processes mostly and the binaries. And here we want to target all processes, and that's what we want to do with packaging. We were very intentional about it. Once we know what we want to profile, and in this case, we want to profile everything, I think, we have to think of how do we collect information about these so that we can have stack traces. So we collect stack traces across kernel, across user space. So everything that's running beneath the kernel, everything that's running in user space as well. So we also have like not just like a wide infra wide view, we also have like an infra depth view, if that makes sense. The next thing is we need to have an idea of what we want to save, how we want to save all this information, how we want to store all of this information. So we do have a specific profile format. We try to compress profiles and then send them to the server. One of those profile formats is pprof. We use like a slightly custom format, which is basically just metadata containing like locations, functions, the address mappings, but not really the function names. We symbolize these addresses on the server. We collect all of this stack trace metadata into a profile format, so that it's easy to send it over a server. And then on server side, we do the symbolization and the visualization, and that's how you end up with the icicle graphs that I just showed. Now, Today, we're mostly going to be focusing on the collection part, because that's the part where we majorly use eBPF. So as you can see, that's why there's the B there. And a bit about what goes on in user space and what's in kernel space. It's only the eBPF part that runs in, we run in kernel space only through the eBPF bit. The rest of it, the discovery of the processes, knowing how to, where to get the information for the stack traces from, and then putting all of that into a profile format, sending it to the server, all of that takes place in user space. Which is why, one of the reasons why we're able to do this at such a low overhead. For running the agent, the overhead is actually like less than some 1%. Or at max, we have seen sometimes for very, very heavy workloads, we have seen 4 or 5%. But compared to how much continuous profiling usually saves you while debugging and being able to optimize the infrastructure and different parts of infrastructure, it's not, you gain a lot more than you're losing. Again, we're returning to this diagram just to make sure that everything I've said fits into this and makes it slightly clearer. The rest of the talk is mostly going to be about Parquet Agent. And so let's first talk about what we do in user space. Like I mentioned earlier, we only do the eBPF bits in the kernel space, and which is reading sort of the stack or walking the stack. But the discovery mechanism for targets, it's in user space. So how do we discover targets? We discover, we look into the, look for the PIDs. We do process-wide discovery. We also look at everything that is in a Kubernetes or in a cloud-native environment. So we look for containers, we look for pods that might be running, and we attach that metadata as well. So there's also a lot of binaries, production binaries especially, come with debug information. We care about the debug information as well. This is basically what we use to get information. There are some places that strip away debug information, or that have debug information that's separate from the binaries. So there's we also have something that can take care of that, because symbolization usually happens on server side. So so there's some amount, but still there's some amount of debug inflows that we extract in the agent itself, which brings us to extracting and winding information. So binaries usually are ELF binaries. That's what most popular executables are. And Dwarf is the specification or the standard in which debug information is encoded into the binary. Usually, the way we would walk a stack is using frame pointers. But a lot of compilers, a lot of production binaries, what they do is they strip away the frame pointers to save, I think, to maybe save a few bytes, or it's just built into a lot of compilers. This basically causes a lot of pain for us, because with frame pointers, it's very easy. Without frame pointers, there are additional complications, sort of. but we thankfully have the dwarf format to save us. There are several tools, inbuilt tools in the Linux kernel usually to read ELF and dwarf information. You may be familiar with some of them. Read ELF, object dump, but the dwarf information is typically also encoded in the binaries. So it's encoded in the EH frame section of the binaries. EH frame stands for I think, exception handling frame. And that's also what gives you the exception handling, the stack trace that you get if a C++ program panics. So let's, what we do in PowerPy agent is we build an unwind table from the information that from the dwarf information that we get in this EH frame section. Here's an overview of what the unwind table looks like. So we have like a location. We take the program counters and we have a location, memory location associated with all of these, with the program counters. Then there are certain rules in the dwarf specification that tell us the offset of the stack pointer register and the frame pointer registers. Then we also have an extra register or an extra value that we need, which is the return address. If you think about it, stack trace is essentially sort of a collection of return addresses of the functions that are being called. And we need to calculate the return address in both x86 and ARM64, but the ARM64 dwarf specification and the hardware architecture actually has a separate register where it stores the return addresses. So we use that for ARM64. It's kind of optional. We don't really need it in x86. Some more about it. So in user space, in agent user space, we extract EH frame information. We use that to get the unwind table rows, and then we further put it into a format of compact unwind table rows. The compact unwind table rows just takes like the program counter, a link register offset, which the link register offset is set to 0 for ARM64. We don't really care about it in x86. Sorry, I misspoke. It's set to 0 for x86. We don't really care about it. We care about the program counter. We care about whether the dwarf information is calculating an offset from the stack pointer or the frame pointer. And so that's why we have the CFIT type that's essentially giving us information about the stack pointer. Then we have the RBP type, which is telling us about the frame pointer, and we have the offsets for both of these, which help us calculate the memory addresses for these values. So this is what actually the unwind tables look like, or this is one of the snippets for libc. It's on x86. If you'll notice the RBP type's 0, in which what this probably means is that this is like a stripped binary, so we don't really have frame pointers. And the CFA type is 2. This means we're using just stack pointers, and we can use the CFA offset to calculate the stack pointer. And then we use this information along with the instruction pointer information that we get to calculate the frame pointer and unwind.
Time check. Samir, you have about 4 minutes left.
Oh, wow. Okay. I'm very, so, okay, I'll zip through. So there's, this is also like, next we have the architecture, the unwind table for ARM64. You can see that there is the LR offset there for ARC64, which is extra. And now, okay, what do we do in kernel space? In kernel space, the way Parquet agent works is it profiles, it uses, it attaches a BPF hook, attaches a perf event hook using BPF, and we sample every 19 times a minute, and we put this information into the BPF maps, and we sort of put it into, we update this in user space every 10 seconds, and then we send it to the server also like every 10 seconds, which is why it's a sampling profiler. It's not like continuous. Okay, this is how we basically send them from user kernel space, from user space to kernel space. We use a very simple buffer to only send the unwind table row information that's updated in BPF on the BPF side, and then walking the stacks. So, okay. Walking the stacks, usually what it means is that we are trying to keep track of we're reading the registers and trying to figure out the return addresses for each function. And this looks slightly different for x86 and ARM64. I've linked the code, but there are other things. So I'll again just leave the slides, skip over a bit. The next thing I want to talk about is compilers and runtimes. So we support a lot of compile languages. We recently added support for just-in-time jittered stacks also. So Node.js, Julia. We very recently added support for Python and Ruby stacks. You can see a Python stack trace. I think this is Fibonacci. Same thing for Ruby. And there is, this is for jittered runtimes. We had to write like a toy interpreter because we were not sure what jittered stacks actually look like. Even GDB doesn't do this fully correctly, so we were very unsure here. So my colleague wrote a toy binary that actually emits JIT code. You can see ahead of time and JIT sections here. And then I never thought I would be able to look at VS Code stacks, but there it is. The thing is, this is not fully correct. This is like a very old image when I was still developing JIT unwinding. And so it turns out that there are some gotchas here, and which mean extremely cool things that we learned. So the VS Code uses like V8 engine underneath, which is also like used in a lot of JavaScript ecosystems. It's also used in Electron apps, which was VS Code. We discovered something that V8 engine emits its own assembly code, which is why our usual jittered unwinding wasn't working. There was a fix for it, and there's a blog post linked in the correctly profiling Node.js part.
Sumir, Sumir, your time has run out. Do you want to wrap it up in like 30 seconds?
Yeah, cool. Okay. So I'm really at the end of it, actually. So something I wanted to talk about is that we also run, a large part of our end users are people who run production systems in the cloud. So these are the major providers they used to run. We try to support versions 5.3 plus. But we recommend version 6.3 plus because there are some very bad kernels or kernel bugs in the 5.19 to 5.6 to the 6.1 versions. And Alexei has actually sent a fix long back, and it's backported, but most distros don't update. Custom kernels don't backport fixes. Even if upstream goes very fast, this is not something that's reflected in most of the platforms that end users use. Update your machines, I guess, to whoever's watching this. That's all. I think there are a lot of things we want to have in the future roadmap, language support. We have a lot more languages coming up. And then we want to improve all the code coverage.
Your time has really run out. I don't want to run off too much at night. Thank you for your presentation, Sumia.
Yeah, thank you. And I'm so sorry. If you have any questions, do drop them in the chat. I'll be happy to answer all of them. Thanks a lot.
Thank you.
How do I... How do I quit, like untake control of this? Okay, it's done.
Hi, Alan. Can you hear me?
Yeah, I can hear you. Let's see
Okay,
if
I can hear you too. It's all yours.
Okay, great. Hello, my name is Alan Jarrett. I'm a developer at Microsoft. I'm one of the maintainers on eBPF for Windows, uBPF, BPF Conformance, and a few other projects. So today's presentation is about a tool we created to validate not only just the BPF ISA, the draft BPF ISA, but also how it allows us to validate other BPF runtimes. Quick overview of the agenda here. Introduction, overview what this is, the reason we created it, how it works, and then time for Q&A. So some of this stuff may be known to a lot of folks, but essentially BPF is a synthetic ISA, meaning it's not actually backed by any specific hardware. It is in the process of being standardized as part of an IETF working group. There are a wide variety of BPF runtimes, the original one being the Linux kernel, but there are also now hardware offloads for BPF, as well as a variety of other BPF implementations. The big challenge here is that if we want BPF programs to be portable across platforms, then all of the platforms need to agree upon a specific ISA. So what the BPF project is, essentially was designed and written to initially validate the IETF BPF specification. Our thinking there is that we want to make sure that essentially the Linux kernel is authoritative, and we want to make sure that the draft ISA matches the Linux kernel. The BPF conformance tool gives us a great way to be able to measure the actual behavior of the Linux kernel, as opposed to just merely examining the source code. The project itself was built reusing test collateral from the eBPF project, with eBPF being a user mode BPF runtime implementation. It can be used as either a CLI, a standalone CLI, or as a library in another project. And as part of our CI/CD, we actually run it against the Linux kernel, with the goal there being that the tests should all pass the Linux kernel, implying that the tests are correct. We of course assume that Linux kernel's implementation is authoritative. So any tests that fail then when running against the Linux kernel imply that the test is buggy. So some background on why we're doing the conformance testing here. One of the, as I mentioned, the original goal here was we want to validate the IETF draft specification. Essentially make sure that what's implemented in the Linux BPF runtime matches what the draft spec has, as well as identify gaps in the IETF draft. Interesting enough here, this is one of the areas where we ended up identifying things through this. One of the examples was the behavior of the division operator in BPF. It wasn't super clearly defined what the behavior would be for division by 0, and different BPF runtimes implemented it differently. But through this, we were able to identify what it is exactly that the current Linux kernel BPF does, and define that as part of the spec. One of the sort of big goals there, of course, is interoperability. We want to be able to make BPF bytecode portable as much as possible. There are certainly some things about the BPF bytecode that are not going to be portable. For instance, dependency on things like kfuncs, which is going to be very much platform dependent. But for the ISA itself, we want that to be as portable as possible. So yeah, the other goal there, of course, is for people implementing BPF runtimes. It provides a fairly comprehensive tool to be able to detect whether or not they've implemented the BPF ISA in, or at least the implementation matches what the draft spec has. Longer term, we want to be able to use this for standards compliance. So essentially, people can be able to authoritatively say whether or not their BPF runtime does actually match the IETF specification or not. In addition, we also use this for security testing. Specifically, what we use this for here is we verify the preval verifies behavior against the ISA. This is an interesting use case simply because the preval verifier has assumptions about what the ISA is supposed to do. And as a result, we can then check based on its assumptions or based on processing a particular sequence of BPF bytecode, it can then reason about what the resultant variables or registered values are, and we can compare that against what the expected values are, giving us greater confidence that what the preval verifier is reasoning about is actually the ISA as opposed to variant thereof. And lastly, it's a great tool for when we're working on the BPF ISA draft, in that we can easily experiment and understand exactly what the behavior of various BPF bytecode sequences are, without having to dig into the Linux BPF runtime, which has complications being GPL and conflicts with other projects some of the people maintainers or some of the authors of the IETF spec are working on. Quick overview of the BPF ISA. It's RISC-based. It uses bytecodes in a series of 11 registers. So yeah, some background here. It's originally used for packet processing. It is now being used for safety and security. The in-kernel variant uses the verifier to ensure safety and security of the BPF bytecode, with constraints being there that the bytecode will halt and will not access any memory that has not been directly granted access to. BPF itself was initially used in the Linux, or developed in the Linux kernel, but has now been adopted by a wide variety of other platforms, as we've seen in the various presentations the last couple of days. So here's what we mean by conformance testing and what the approach we've taken. The test starts by declaring the initial state for the VM. This essentially currently means the context memory being passed to the bytecode. Context memory in this case merely just being a flat array of data, giving an initial state for the BPF program to work on, as well as pre-populating, well, this is more of a future one, but we intend to be able to provide the ability to pre-populate maps with specific data to test with. The test then declares a sequence of BPF instructions to execute. We declare them in a GCC style assembly. This was picked over the Clang assembly simply because our view was the GCC style assembly was slightly easier to parse. Not as readable as the Clang assembly, but easier to parse. And lastly, the test then declares what the expected return code, or in other words, the value of the register R0 will be at the end of the test. So an example here would be, this is a, this was a particular test that tests the left shift and right shift operators. As I mentioned, it contains the list of assembly instructions followed by the expected result value. The way the BPF Performance Suite is built is it consists of three things. Essentially a runner, which is something that parses the test code, invokes a plugin, and then edits or gathers the data of the results. In this context, a plugin is merely just a mechanism, a wrapper around a BPF runtime, so that we can pass it the bytecode and initial state, and then get back the resultant value. In the case of Linux, the plugin is just merely a fairly small libbpf-based program that accepts the BPF bytecode, creates a program in the kernel, loads the bytecode, and executes it. The tests themselves are, as I mentioned, small snippets of BPF assembly, along with initial value context and expected exit code. The plugins then are very much runtime specific, with the only exception there being that the goal is we want a sort of meta plugin for libbpf. So any BPF runtime that implements libbpf would, in theory, then be able to share a single runtime. I haven't quite got there yet, but that's one of the sort of goals. One of the challenges we faced here when testing the various runtimes is, apart from libbpf, a lot of the other BPF runtimes expose different APIs. So uBPF, RBPF all have a different way of invoking and running the BPF runtime. In addition, OSs have a wide variety of IPC mechanisms, so what might work for one platform might not work for another. We ended up coming up with the sort of lowest common denominator of IPCs and platform interfaces being the CLI, where we use the input and output streams as well as a list of arguments. Essentially, this allows us to stream the BPF code to the input stream, and for the list of arguments, we can pass things like the initial context values and things like that. The BPF conformance runner then interacts with each per runtime plugin by launching the plugin, streaming the data to it, and collecting the value of the R0 register from the output stream. Then the runner then gathers the data from each of the tests that are run. In addition, it will also keep track of what instructions have been tested and what instructions have passed, essentially which instructions have been used and tested that pass. This gives a fairly easy way to assess which set of instructions this particular runtime is conformant with. So one of the interesting things there, of course, is we want to keep the design of the plugin as simple as possible, because the plugin is just purely a overhead from this point of view. We end up creating plugins for a wide variety of platforms. The first one is obviously for the Linux kernel itself, where we use libbpf to load the bytecode. In addition, we have plugins for the preval verifier, where in the case of the preval verifier, it doesn't necessarily execute the BPF bytecode, but preval essentially then will emulate the bytecode and examine its post conditions. And if its post conditions are sufficiently narrow, it can then evaluate whether or not the post condition for the register R0 matches what the expected value was. The RBPF, uBPF, and WASM uBPF ones are all fairly similar in that they use a CLI-based approach. The only one that's a little bit different here is the eBPF for Windows one. It in turn actually has a slightly different way of processing BPF bytecode in that it upconverts it from BPF bytecode back to C, compiles it as native executable, and executes it. So a couple of things that we are sort of looking for, or we're working towards for future enhancements. Today, we pass the raw BPF bytecode to the runtime. We're looking to enhance that so that we can pass the ELF file. The reason for that is it becomes increasingly challenging to parse things like map definitions, as well as cases where we have multiple local calls in the BPF program. Parsing those across as raw BPF bytecodes becomes significantly more complex. In addition, we would like to end up enhancing our test cases somewhat. We have reasonably good confidence in them, but there's always a possibility we may miss some behavior that would be important. As I mentioned, the test cases themselves are all derived from the eBPF runtime, but we've extended it with, I think we've now have covered most of the V3 instruction set, and we're in the process of adding the V4 instruction set. Currently, we have a hand-rolled assembler that processes the GCC style assembly, and ideally, if possible, we'd prefer to just use the real GCC for that. The last challenge we have here is our daily CI/CDs run in GitHub, and GitHub, even its latest runner, has a fairly old Linux kernel. That makes it a little bit challenging. We can't test anything more newer than the CPU v4 instruction set. So yeah, I figured this is a fairly short presentation because I figured I'd leave some time for any questions and see if folks have any additional input or insights or feedback.
Hi there. Do we have any kind of timeline for IETF approval?
That would actually, I don't actually have a good date on that yet. There are actually a series of different IETF drafts in progress. The IETF BPF ISA specification itself is the furthest along. There's a working group processing that right now. Dr. Thaler is probably the contact I know who's working on it most closely, but don't have a good data for when this is going to be finalized.
Thank you.
We have questions? If no, we can end early.
Okay.
Okay, no? Okay, thank you, Alan. Thank you for the presentation.
Thank you very much.
Okay, I think that is the last one. Tomorrow, I think we will start at 9:30. I'll see you guys tomorrow at 9:30. Thank you.
you.